everyone, welcome to CVPR 2020's Computational Cameras and Displays Workshop. Although we can't be together today, we're so happy you're joining us remotely for a day of exciting research in the area of computational imaging and photography. We have an excellent program, 9 fantastic invited speakers from around the world that will be speaking about their work, along with 23 spotlight talks that will quickly show you a glimpse into other work that's being done in the area. We're so grateful to our speakers for putting lots of work into their talks in the last couple of weeks to get them ready for you to see them virtually. And so please watch the talks online, join the workshop in our Zoom telecon link live, ask your questions in the Q&A windows below every talk on the website or in the live telecon. Before we get started, I want to just introduce ourselves, the organizers of this year's CCD workshop. My name is Katie Bouman. I'm an assistant professor at Caltech, and I've had 2 other amazing organizers that helped to put together today's workshop. Professor Achuta Kadambi, an assistant professor at UCLA, and David Lindell, a graduate student at Stanford. We couldn't have put this together without both of their help. And so we hope to get to know you more throughout the day, but in the meantime, let me pass it off to David.
Thanks, Katie. So first, just a little bit about what is CCD. Throughout its now 9 years as the Computational Cameras and Displays Workshop, and for almost a decade before that as the ProCams Workshop, CCD has aimed to bring together researchers in academia and industry working in the field of computational imaging. The workshop is a chance to hear from senior researchers and rising stars in the community, and to present and learn about new or recently published work. Our community is broad and diverse, with relevant topics encompassing new types of displays, VR and AR systems, sensors for autonomous vehicles and robotic navigation, 3D sensing technologies for applications from mobile phones to industrial assembly lines, new camera designs and algorithms for photography, methods and sensors for 3D fabrication, and applications in remote sensing, medical imaging, and more. This year is unique in that we come together in a virtual format, yet we are excited to be able to still meet together, share our research and ideas, and move the field forward. We're fortunate this year to be supported by 3 generous sponsors. I want to take a moment to publicly recognize and thank Adobe, Algolux, and Google for supporting the CCD workshop. And with that, I'll hand it over to Achuta to talk more about the program that we've put together.
Thanks so much, David. We're fortunate to have a tremendous lineup of invited speakers. The speakers span a range of topics in computational cameras and computer vision, and just as importantly, they span a range of seniorities in the community. I want to just take a brief moment to highlight Shumian, Mark Sheinin, and Atul Ingle. These are our junior speakers who will carry the field forward, who have graciously volunteered their time. Once again, as Katie mentioned, I'd like to thank all the speakers for volunteering their time during this busy and uncertain circumstance we find ourselves in. We have a terrific schedule from 8:45 a.m. to 4:45 p.m., all Pacific time. There will be a Zoom TCON link. We highly encourage all of you to participate in the Zoom chat, not just during the talks, not just after the talks, but also during the breaks. Hopefully you'll make some new friends and you'll add them to your email address books and on social media. Enjoy the workshop. Our first speaker is Michal Irani. Michal Irani is a professor in the Department of Computer Science and Applied Math at the Weizmann Institute of Science in Israel. Michal has made many contributions to computer vision, signal processing, image processing, and AI in general. Michal, feel free to say some remarks now.
So first of all, thanks for the nice introduction and thanks for inviting me to this workshop. I wish I could be there in person and see you all live, but I guess that's not possible. So maybe next year. A month ago, the organizers asked me to record my invited talk. I fretted and I worked so hard for 3 days. I recorded and re-recorded parts. Believe me, it was not easy. Only to find out a few days ago that I can give my talk live. So I figured, hey, if I suffered so much recording this talk, we might all as well watch it together. So I'm here watching it with you, and we'll be around to answer any questions you have immediately after my talk in live, of course. So see you all in 25 minutes or so. So please.
Excellent. So I will now play the video, and then feel free to ask any questions in the chat, and I will moderate them and ask questions at the end of Michal's talk. And we'll do that for the other speakers in the session as well.
Hello, my name is Michal, Irani, and I would like to tell you about something I'm really excited about, something my group has been working in the past 3 years, what we call deep internal learning. What we mean by that is how we can train a deep network in a totally unsupervised way without ever having seen any prior examples, simply by training on a single image, the test image alone. Why is this interesting? Well, we're all used to external training. That is to say, we train on many previous examples external to our test data, and then we apply it to the test data. But what happens if we don't have enough training examples? Or what happens if the statistics of our test data is very different than that of our training data? In those cases, deep learning fails. I would like to show you how we can often resolve these problems by replacing external training with internal training. Now, because I'm limited in time, I will restrict myself in this talk to show only how deep internal learning can be applied to computational photography related tasks. But this paradigm goes well beyond computational photography. But how can a deep network be trained on a single image? Well, it turns out that there's a lot of internal redundancy inside a single image, both within and across different scales of the image. When I say within scale, I mean that if you see a small patch once inside the image, you will almost surely see it many more times inside the same image. And this property has been used by us and by others for lots of applications, including image completion, image denoising, and many more. And while I'm showing here large patches, in practice I'm talking about much smaller patches, 5 by 5 or 7 by 7 pixels. Now, patches occur also across scales of an image. That is to say, if you scale down the image, then almost any patch in the original image will almost surely be found in coarser scales of the image without scaling down the patch, which means that small patterns inside the original image appear in multiple resolution in the original image. Now, this property has again been used by us and by others over the years for lots of application, including fractal image compression, super resolution from a single image, image deep learning, image dehazing, and more. Now, this may look like a very contrived image to you with lots of repetitions, but it turns out that if you go to small enough patches, as I said, 5 by 5 or 7 by 7, this is true for almost any patch in almost any natural image. And we have shown this empirically in our 2009 paper. We tested it for hundreds of images, indoor, outdoor, man-made, natural. And it turns out that this fractal-like property is a very strong property of natural images. Now, the nice thing about these old patch-based methods is that they're totally unsupervised. They require no prior examples. The internal patch redundancy inside the single test image provides all the information we need to solve many ill-posed problems. The bad news is, in the past few years, these methods have been completely outperformed by deep learning methods, which is really depressing. So for a while I was really depressed about this, but then I said, well, if you can't beat them, join them. But there was something really disturbing about it. On one hand, we have this very powerful tool, deep learning, which performs amazingly well, but is very data hungry and we don't really understand what's going on inside. And on the other hand, we have this nice property, the internal redundancy, which is totally unsupervised, requires no prior examples. We understand what's happening, but unfortunately doesn't perform as well. So for a while I was asking myself, is there any way to bridge this gap, to combine the power of those two complementary approaches? And luckily, 3 years ago, my PhD student, Asaf Shocher, came up with this brilliant idea of doing deep internal learning. That is to say, let's train an image-specific CNN at test time on examples extracted from the test image alone. As you will shortly see, this can often be done quite efficiently. So in this talk, I will cover 3 deep internal learning papers related to super resolution, starting from our initial paper in this area in 2018, continuing with a recent NeurIPS paper, and finally, a totally new work, unpublished yet, on applying internal learning to video data for obtaining super resolution in time. So let's start. Now, in image super resolution, our input is a low resolution input image, and the output is a high resolution version of it with a higher density of pixels. Now, every pixel in the low resolution image is affected by a certain region in the high resolution image, what induces a linear constraint between the high resolution image and the low resolution one with a super resolution kernel K, a blur and subsample with K. Of course, the pixels in the high resolution image are unknown, so even when K is known, when the super resolution kernel is known, this is an ill-posed problem because the number of unknowns in our high resolution image is greater than the number of measurements in our low resolution image. The problem becomes even more difficult when the kernel K is also unknown, because now we have to recover both the unknown kernel as well as the high resolution image. And this is known as the blind super resolution problem. Now, I will not review the literature on super resolution, but by far the leading methods are deep learning based methods, or what we call external methods, external super resolution. And the idea of external super resolution is you take lots of pairs of low resolution, high resolution images, and you train a network to obtain the low resolution image as an input and to output the high resolution image. And you can train it on as many images as you want, because all you have to do is take a high resolution image, downscale it, and you have a low resolution, high resolution pair of images. And these networks are trained for days or weeks, and once trained, they can be applied to a new low resolution image they've never seen before, and out comes the high resolution image. And this does amazingly well. In fact, these methods perform 2 or 3 dB better in PSNR than any of the methods prior to deep learning. However, when we checked them, we found out that they work well only under ideal conditions. And when I say ideal conditions, I mean that the downscaling kernel that was used to downscale the high resolution image into a low resolution one is usually fixed for the entire data set, and it's usually an ideal low pass filter or something close to it, for example, bicubic downscaling. But the world is not ideal, and these networks, all they learn is how to upscale images that would downscale bicubically. But when I take a picture, I slightly move my hand, and the image that I get is not with an ideal low-pass filter. It's some non-ideal low-pass filter. And when I'll take another image, I'll move my hand slightly differently, and it will be a different non-ideal downscaling kernel. So this kernel, it varies from image to image. And once you give those networks non-ideal downscaled images, they don't perform any better than regular bicubic interpolation. They also ignore other various artifacts like noise, JPEG compression, and so on, and when these are introduced, they perform quite poorly. So in the past year or two, methods have been developed for doing blind external super resolution. That is to say, train a network to be agnostic to the downscaling kernel K. And this is usually done by training the network on lots of downscaled images using a variety of downscaling kernel. And this, of course, improves the results. However, these networks are still restricted to those specific kernels and to the specific data, statistics of the data they were trained on. And once taken out of their comfort zone to a different kernel or a different data type, they no longer perform well. And this is where we come in. We can solve these problems by replacing this external learning with internal learning and adapt the network to the image-specific degradation. We call it ZSSR, zero-shot super resolution. And the idea is the following. Given a single low-resolution input image, we have never seen anything before. What we do is we downscale it even further to generate an even lower resolution version of it. And in a moment, I'll say how we downscale it. And now we train a light image-specific network to upscale this image back to its original size. And this is the loss. Please recover the original input image. Once this light network is trained, it can now be applied to the original input image to generate the super resolution output. And the rationale here is because of the strong recurrence of patches between those two images, between the image and its downscaled version, whatever network is good for increasing the resolution of the patches in this small image will also be good for increasing the resolution of the patches in the original input image. Now, of course, training a network on a single pair of images is a bit stretching it too much, and so we generate many pairs by performing augmentations on this particular image. We flip it, we rotate it, we scale it down, and this generates hundreds of low-resolution, high-resolution pairs of images, all with the same patch statistics for which we can train this specific network. And this generates a light image-specific CNN. Now, how do we go about downscaling this image? After all, we said that the downscaling kernel is image-specific. Indeed, it is. But it turns out that this downscaling kernel can also be recovered directly from the low-resolution input image itself. So we published a paper in 2013 that shows how this can be done with old nearest neighbor based methods. Recently, we found a way of doing this also with deep internal learning, and I'll explain this a few slides down the line. But you can of course ask, well, how can a CNN be trained at test time? Doesn't it take forever? Well, let's see what kind of information we have inside a single natural image versus outside in a large collection of images. Inside, the patch entropy is very, very low, whereas outside in a general collection it is very high. And we showed this empirically in our 2011 paper. What this means that the internal image-specific network can be very light. All it has to do is how to increase the resolution of these particular patches. Externally, on the other hand, the network has to be very heavy. It has to know how to increase the resolution of any patch it will ever encounter. And since the entropy of patches in a general collection of images is large, these are very, very heavy networks. They tend to have hundreds of layers, tens of millions of parameters, and therefore they're very slow to train. In fact, they take days or weeks to train. In contrast, the internal CNN, image-specific CNN, is very fast to train. In fact, it takes 8 seconds on a single V100 GPU, both for the train and test time. So this really gives us super resolution in the wild. We can apply it to any data type, to any kernel type, to any scalar aspect ratio. All of these can be determined at test time and computed at test time. So let's see some results. Here's a low resolution image which was downscaled in a non-ideal way. This is a result of simple interpolation. Here is the result of the state-of-the-art external super resolution, EDSR+. Now, if I'll flicker between the two, you won't be able to tell the difference. There's barely any difference. Now, EDSR+ does amazingly well on images that were downscaled bicubically, but this low-resolution image was not downscaled bicubically. So on those kind of images, it doesn't perform any better than interpolation. In contrast, here is the result of internal super resolution. And if I'll flicker between the two, you'll see the tremendous difference. And the reason internal learning here does so much better than external learning is because it exploited the image-specific downscaling kernel, as well as the image-specific repetitions. Here is another example. This is an old photo we downloaded from the internet post-World War II, Checkpoint Charlie. We have no idea how it was generated. This is when it's bicubically interpolated. This is external super resolution using EDSR+. If I'll flicker between the two, you probably won't be able to tell the difference. And in contrast, here is the result using internal super resolution. And let's flicker between the two, and you can see the tremendous difference. For example, I hope you can see my mouse. Look at the legs over here, the difference between external and internal. And you can see that we really recover information that is subpixel, that goes beyond the Nyquist limit of the camera. Okay, or look at the back of the motorbikes here. Okay, so internal super resolution really allows you to go beyond the Nyquist limit by exploiting this internal redundancy within a single image and the image-specific kernel. Here's an example of a JPEG compressed image. When you apply external super resolution to it, this is what you get. As you can see, external super resolution methods enhance both the signal and the noise. They can't tell the difference between them. In contrast, here is the result of internal super resolution, and if I'll flicker between the two, you'll see the difference. Internal learning enhances the signal, but not the noise. How come? Well, the signal has this nice cross-scale recurrence of patches. The noise does not. Therefore, ZSSR does not learn how to generalize for the noise. Similarly, here's a different type of noise, again, unknown to our network. This is it's speckle noise. Here is the result of external super resolution. Here is the result of internal super resolution. And again, I'll flicker. It's not perfect. It doesn't eliminate the noise completely, but you can see that it super resolves the signal while almost eliminating the noise. And again, the reason is the signal recurs across scale, the noise does not. And we've, of course, empirically evaluated it on hundreds of images. We did an evaluation both on ideal images and on non-ideal images. So images that were ideally downscaled and with no artifacts, ZSSR does reasonably well, but of course not as well as external methods. After all, this is the bread and butter of external methods. But we perform reasonably well, not too bad. But once applied on non-ideal images, whether downscaled non-ideally or with various artifacts like noise or compression artifacts and so on, even though the artifacts are unknown both to us and to the external methods, our methods, our internal ZSSR, does 1 to 2 dB better than the state-of-the-art external methods. But remember, we're dealing with a blind super-resolution problem. All we have is the low-resolution input image. We don't know what the high-resolution image looks like, nor the kernel relating those two images, the downscaling kernel. And we need to know this downscaling kernel because we need to downscale the input image using this kernel in order to generate the pairs of images to train our ZSSR. So how can we go about estimating it directly from the image? Well, in our 2013 paper, we showed that the correct super-resolution kernel is also the kernel such that when you downscale the low-resolution input image with it, will maximize the similarity of patches across scales in this low-resolution image. And you can find the analytic proof of this claim in our 2013 paper. And back then, we solved it using a regression with nearest neighbor search on patches. Recently, we found a way of estimating the kernel directly from the low-resolution input image using internal learning. We call it kernel GAN. It's an internal GAN that estimates the kernel. This is a recent NeurIPS publication. It was an oral presentation in NeurIPS. And the idea is the following. We have a single low-resolution input image, and our generator and the GAN is going to learn how to downscale this image correctly. What is correct downscaling? Correct downscaling is the one that will maximize the recurrence of patches across scales of the low-resolution input image. How can we guarantee this? Well, we're going to feed those images into a discriminator that will try to tell apart patches that came from the real input distribution and the ones that came from the fake image distribution. And it's going to generate a map that says for each pixel in the generated map whether it came from the original input distribution or whether these patches came from the generated distribution. So the generator gets better at fooling the discriminator to believe that these are the input patches, and when it converges to the correct downscaling kernel that maximizes the similarity of patches across scales of the low resolution input image. Now note that the generator cannot be any deep network, because a regular deep network might just generate a garble of patches from the low resolution input image. The discriminator thinks it's fine, the generator will be happy, but this is clearly not what we want. We want the generator to satisfy this constraint. We want it to imitate downscaling with a blur kernel. So how can we guarantee that the generator will satisfy this form, blur and subsample with a single kernel? Note that this is a linear operation. In fact, it can be realized with a single-strided convolution layer. So we tried just that. We replaced our generator with a single-strided convolution layer, but that worked miserably. For example, if these are some ground truth kernels, then this is what our generator converged to, and nothing we did helped. We couldn't figure out what we were doing wrong until it struck us. Deep networks work well because they usually have no bad local minima. No matter how you initialize the network weights, it usually converges to a good local minimum. But this is not the case here. In our case, there's only a single good global minimum, the correct downscaling kernel K. Note that the error surface of our generator is highly non-convex since it must satisfy the GAN loss in order to fool the discriminator. So if we initialize our network with random weights, it will never converge to a good minimum. So this can never work. What does work, however, is replacing G with a deep linear network. What's that? A deep linear network is a network with no ReLUs and no nonlinearities whatsoever. Note that multiplying the weights from all the layers by each other yields the same kernel K. So have we gained anything by going deep? The answer is yes. Remember, the single-strided layer had only a single solution, a single good minimum. But in our case, with a deep linear network, we have infinitely many decompositions of the same kernel K. For example, if this is a good decomposition, then so is this one, multiplying the weights of one layer by a matrix A and the other layer by its inverse will give rise to the same kernel K. And this is true, of course, for any invertible matrix. In other words, there are infinitely many weight combinations that will give rise to the same kernel K. Therefore, there are infinitely many good local minima to this network. And this solved the problem. No matter now how we initialize the weights, the network converged to a good local minimum. For example, if these were the ground truth kernels, and these were the results obtained with a single linear layer G, then these were the results obtained by the deep linear network G. And as far as we know, this is the first practical use of deep linear networks. So far, they have been mostly used by theoreticians for analyzing network properties, but here we show that they actually are practical. In fact, we believe that deep linear networks can be used to solve many other linear regression problems under nonlinear priors. So let's see comparisons of blind super-resolution methods. This is an old photo of John Kennedy downloaded from the internet. These are the results of the winners of the blind super-resolution entire challenge. Although those external methods performed very well on the entire challenge dataset, they actually performed quite poorly once taken out of their comfort zone, outside the statistics of their training data. In contrast, here are the results obtained with internal super-resolution, once using our old kernel estimation method and once using our new kernel GAN method, which provides the best results. Here, let's look at another example. And of course, we have performed extensive empirical evaluation on hundreds of images, and you can find the details in our paper. The bottom line is we outperform all blind super-resolution methods at the time of our submission, at least, by half dB to 1 dB. And while these results are by now a year old, and many new blind super-resolution methods have come out since then, I just now heard that the new winners of the new entire blind super-resolution challenge this year at CVPR 2020 have used our kernel GAN code to estimate their image-specific kernels for their super-resolution methods. So I'm really happy about that. In the last few minutes of my talk, I would like to show you something totally new, unpublished work yet, how we can extend the notion of deep internal learning into video data. We started by looking at the problem of zero-shot temporal super-resolution. What's temporal super-resolution? Well, in spatial super-resolution, we wish to increase the density of pixels, thus recovering details that are smaller than a pixel size. In temporal super-resolution, we wish to increase the frame rate of the input video, for example, from 25 frames per second to 200 frames per second. However, we don't want to just temporally interpolate the video. We want to be able to recover dynamic events that occur faster than the input frame rate, and hence are invisible in the input video. In other words, we want to go beyond the temporal Nyquist limit of the input video, thus undoing both motion aliasing as well as motion blur. This is an example of motion aliasing. The fan is rotating clockwise faster and faster, but because the frame rate is too low, at some point it appears to be rotating counterclockwise. The other effect is motion blur. The moment the shutter of the camera opens until it closes, the fan moves very fast, inducing motion blur. Note that these effects cannot be undone, cannot be removed by temporal interpolation methods, no matter how sophisticated they are. Temporal interpolation cannot produce new information that does not exist in the input video that was already lost in the sampling process. In contrast, in temporal super-resolution, we aim to resolve both of these effects when upsampling the frame rate. In this work, we performed temporal super-resolution by training a CNN on internal examples extracted directly from the input video. A variety of useful augmentations are described in our paper, which can be found on arXiv. One very useful augmentation is obtained by taking coarser scales of the input video by blurring and subsampling it in time. If this was the original video, then at coarser temporal scales, the fan will move faster with more motion blur, and at some scale, it will also exhibit motion aliasing. In other words, coarser temporal scales simulate higher speed, more motion blur, and more motion aliasing. We can now train a video-specific CNN on such pairs of videos in order to learn how to undo motion blur and motion aliasing. Once trained, the same network can be applied to the original input video to produce the desired high temporal resolution output. Another very useful augmentation is based on our new observation that patches recur not only across scales of the video, but also across different dimensions of the video. For example, here is the original space-time volume of the input video sequence XYT. Its spatial slices form the video frames. If we now take this space-time volume, rotate it so that one of its spatial axes becomes the temporal axis, and now slice it, these form the temporal slices of the space-time volume, where one axis is the temporal dimension that contains the temporal aliasing. Note that the patches in these temporal slices bear similarity to patches in the original spatial frames, but contain aliasing in time. Therefore, the spatial slices provide high-resolution examples teaching how to undo the aliasing in the temporal slices. So let's see some results of temporal super-resolution. This is the fan video that you saw before, super-resolved by a factor of 8 in time. At the top left is the input sequence. At the bottom left is our output. You can see that we resolved motion blur and motion aliasing recover the correct motion of the fan. In contrast, NVIDIA Slow-Mo, Dane, and Flawless failed to recover the correct motion and shape of the fan. Here's another example of a real video, a rotating disc. At the top left is the input. At the bottom left is our result. It's not perfect, but it resolves most of the motion blur and motion aliasing, while other methods fail to do so. And another example. The top left is the input, the bottom left is our output, the bottom right is the ground truth. And one last example. And you can find many more videos on our project website, as well as quantitative evaluations and comparisons to other methods in our paper. To conclude, I hope I've convinced you that there's a lot of redundancy inside a single image or a single video sequence, and that it gives rise to deep internal learning. It combines the power of deep learning with image-specific or video-specific priors. The nice thing about it is that it's totally unsupervised. It needs nothing but the input video or input image themselves. It adapts to the unknown imaging conditions and degradations of the input image or video, and it provides state-of-the-art results for super resolution on real non-ideal images. Deep internal learning also gives rise to other applications, including image dehazing, segmentation, transparency separation, retargeting, and more, things I could not go into in this short talk. Finally, I would like to mention all the wonderful people who worked with me on the things that I presented today, and primarily Asaf Shocher, who is the driving force behind the idea of deep internal learning.
Great. Thanks so much for the talk. Wonderful.
Thank you. So I'll be happy to take any questions if there are any.
So I'm going to ask a few questions. I'll just start by drawing them from the chat. So Kathy has asked, when you do the data augmentation, presumably in the earlier half of the talk, did it include color augmentation?
You're referring to the video super resolution? When you said the second part of the talk, you meant the video super resolution?
Oh, sorry, the early part of the talk. Given that the question was asked at 9:16.
Color augmentations, no. We don't do any switching of the color bands or anything like that. No, remember, we're trying to learn the statistics of this particular image, the statistics of the patches of this particular image. So doing any color augmentations may be good for other images, but we don't need them for this image. It will only confuse the network.
Great. I have a quick question on the image-based, just to continue on that topic. Can you comment a little bit on the real-time performance, given that you're training a network on the single image that you get?
So as I mentioned in one of the slides, but I saw there was something wrong in the recording. It currently takes us 8 seconds on a V100 GPU to train and test. I mean, both training and inference on a single image. And it's, by the way, independent of the image size, since the training is done by taking crops from the image, which is, by the way, not true for external methods. Their forward pass is very, because the network is huge, the forward pass, it gets larger and larger as the image gets larger. And in our case, because it's a light network, even the forward pass is very fast. So in fact, we actually, when we compared it to EDSR plus on a 800 by 800 image, our train plus test took as long as their forward pass only. Beyond that, we were actually even faster. So it's not real time, but it's reasonable time.
Okay, excellent. Great. So we've got a lot of interest in your talk, a lot of questions here. So I'm just going to curate. I won't be able to get to all of them. Ewa Nawara has asked, does temporal super resolution work when the motion is not repetitive, periodic?
Yes, it does. In fact, in our website, there are many examples of flickering fire, splashing water, things that are not repetitive by nature. But by the way, in an older 2013 paper, we've explored the repetition of space-time, small space-time patches within and across scales of a single natural video. And this is also a very strong property of natural videos. Even though you don't see the repetition, it's not at that scale, okay? So if I move my arm even once like this, okay, this part of the arm, the patches here move fast. The patches here move slowly, but they're very similar in appearance. So these provide examples for this, if this is more blurry and this is less. Okay, so there's a lot of repetition that is beyond the resolution that we see, the coarse resolution that we see across space-time patches, and definitely across dimensions, which is something new we detected and provides a lot of information.
Excellent. So just one more question. I'm going to combine two questions into one. Michael and Kusher have asked, a question about the data augmentation. For the, again, going to the first half of your talk, for the image-based super resolution method, you mentioned how you do data augmentation with spatial rotations and warps. Doesn't warping the image kind of change the distribution of your training and test data? For example, you introduce additional blur kernels due to the resampling in warping the image.
So remember, first of all, there are 8 types of augmentations that don't introduce any interpolation. These are the flips and rotations by 90 degrees, 180. This already produces 8 types of augmentations without any need for interpolation.
Yeah,
okay. Now, if you, in terms of scaling down, if you don't know the kernel, we don't use these types of augmentations. If you assume that the kernel is not known, don't use these types of augmentations, because the problem is not so much interpolation. Remember, we were talking about repetitions of patches across scales of the image, okay? So you do want to generate these cross-scale examples, okay? When we do know the kernel, for example, when it's bicubic and it's easy to perform various types of downscaling at various factors, we use this to generate hundreds of augmentations. But when in the blind super resolution case, when we only compute the factor, the kernel at factor of 2, we don't use any augmentations other than the regular ones.
Great. So I'm going to just take one last question here. This is from Kiros. So GANs are used a lot for image generation and synthesis these days.
I'm sorry, could you go back? I didn't hear the first.
Sorry. So
yes.
GANs are used a lot for image generation these days. Have you checked if the images that you're getting possess the internal structure that you have been exploiting in natural images?
No. Here my GAN does not synthesize. In this particular example, we've had GANs synthesize images. Okay, we've had a different work called InGAN, which we presented at ICCV 2019, which generated new images with the same statistics and so on. This is not the work here. Here our generator does not reconstruct images. Our generator computes the blur kernel. Okay. It generates, as I showed, it's a linear operation. It's a blur and subsampling by kernel. So that's all the generator in this particular kernel GAN image, kernel GAN work, that's all it does, okay? It just computes the kernel. It looks for the kernels such that when you downscale the image by a factor of 2, the discriminator cannot tell apart the patches that came from the original image and the patches that came from the downscaled image by a factor of 2. And the generator downscales it correctly so that the discriminator cannot tell these apart. Okay, so it's not any network. It cannot generate whatever it wants. It has to downscale the image by a factor of 2, but using any blur kernel that it has to find out so that the discriminator cannot tell apart the patch distribution in the original image and the patch distribution in the downscaled image, downscaled by the generator.
Okay, excellent. I think offline, a follow-up to that would be ways to actually...
In order to guarantee this, this is why we use the deep linear network and not the deep nonlinear network, in order to guarantee that this is a downscaling operation. Sorry, that was maybe what you asked.
No, it'd be great in a follow-up. I'm going to actually, there's a lot of questions that are coming also privately to me, which is great. I'm going to copy these and email it to you offline. But thanks again for your talk. Really enjoyed it.
Okay, thank you very much. And thank you for the lovely audience and for all your questions. And I'll be happy to answer any other questions.
So our next speaker is Mark Sheinin. Mark is a postdoctoral research associate at Carnegie Mellon University Robotics Institute. Before CMU, Mark was a PhD candidate, received his PhD successfully from the Technion, supervised by Professor Yoav Shechner. Mark has received numerous awards. It's difficult to list them all here, but one of his notable awards is the Best Student Paper Award at CVPR 2017. So Mark will be sharing his screen directly with the video, which saves me some hassle. So welcome, Mark. Please feel free to say hi and go ahead and share your screen and play the video.
Hi, everybody. It's great to see all your names in the Zoom chat. As like Michal, I'm going to play my pre-recorded video. If it's good enough for Michal, I think it's good enough for me. And yeah, super excited to be here. And before I start, I just want to, before I forget, I want to thank the organizers for inviting me to give this talk. And let's start. So this talk is about AI, but not the AI you are thinking of. Today, I'm going to talk about artificial illumination. Artificial lights are everywhere. In computer vision, we extensively use artificial illumination as well. But usually, to make life easier, we add some sort of structure to the artificial lights depending on the application. So for example, we can add a spatial structure, and this is usually called structured light. Or we can add temporal structure by emitting pulses of light or a temporally modulated signal. While adding structure to light is a powerful tool, sometimes instead of adding structure, we can utilize some existing hidden structure. So today, I'm going to talk about 3 projects that span this complementary approach to using artificial lights in computer vision. The first project I will present uses structured light to enhance depth recovery in wide aperture imaging, while the other 2 projects exploit some inherent property of uncontrolled artificial lights. So the first project is called Depth from Texture Integration and is an example of the Yang approach, where we use controlled illumination and add a task-specific structure to our light. This work was done in collaboration with Yoav Shechner, who was my PhD advisor. So let's talk about the role of aperture in depth recovery. Depth recovery methods that rely on triangulation, such as shape from stereo and structured light, prefer a narrow aperture because they rely on the pinhole camera model. However, methods that rely on defocus, like depth from focus and depth from defocus, require a wide aperture. Now, using a wide aperture has some advantages. First, for the same exposure time, it gathers more light on the sensor, and thus we get better signal-to-noise ratio and can do faster imaging. Second, it gives us a higher spatial resolution by narrowing the diffraction-limited point spread function. And finally, a wider aperture increases the axial depth resolution by raising the discrimination between in-focus and defocused image content. So a wide aperture is great, but there's a trade-off for making it wider, because the resulting shallow depth of field in a single wide aperture image can severely limit the dynamic range of depth recovery. So one way to increase the depth range is to capture a focal stack. A focal stack is a sequence of frames where each frame images a different focus plane. Now these blue bars above signify the exposure duration of each frame. So from a focal stack, depth can be recovered using depth from focus. But capturing a focal stack is relatively slow due to the multiple exposures and increased bandwidth required to capture the frames. Therefore, if we try to squeeze the entire stack at the same exposure time of a single wide aperture image, as illustrated above, the resulting frames would be underexposed, and thus we will lose our high SNR advantage. So here's a new imaging method called texture integration that can potentially keep the advantages of a wide aperture while also extending the dynamic range for depth recovery. So what is the trick for doing this? So instead of capturing a focal stack, we capture a focal sweep image. And unlike a focal stack, a focal sweep generates a single frame, so it is not underexposed. In a focal sweep, the camera's focus plane is swept through the imaging domain during a single camera exposure. What you are seeing here on the left is the instantaneous camera image intensity, which is integrated by the sensor. So here is our method. First, we add an illumination source to the scene. Then, we do a focal sweep while simultaneously projecting different textures at different times within the sweep. Each object depth is illuminated by a unique texture, and this texture is only completely in focus on object surfaces corresponding to this depth. The resulting image contains time-integrated textures which encode object depth. So, to decode the depth from the texture-integrated image, we use a pre-calibrated dictionary that holds the integrated textures as a function of depth. So that's the basic idea of texture integration. Okay, so now let's see some results. So here are the actual patterns that we project, where each focus plane has a different projected pattern. And here is the decoding dictionary, where we show the texture integrated images for a planar object located at a depth range of 10 millimeters. So here's a small object, its corresponding texture integrated image, and the recovered object shape. And indeed, in a fair comparison, for the same acquisition time, texture integration that uses a single image was superior over depth from focus that uses a stack of images. Okay, so in this work, we added the structure to the illumination. But what about all the lights that already exist everywhere around us? What if we can treat them as pixels in a huge room-sized projector? And just like in a projector, we could change their color or turn them on and off at will. If we had that ability, we could perform some computer vision tasks in the wild without the need for controlled illumination. So now we are entering the yin domain, where we ask ourselves what type of structure already exists in everyday lights. I will talk about two projects that belong in the yin domain. The first project is a joint work with Yoav Shechner and Kiros Kutulakos. And before I get into it, I want to tell you the fascinating origin story for this project. So, back in 2016, when going outside was still normal, Yoav had an idea. He wanted us to build a camera that would enable astronomers to image the night sky from a busy metropolitan area. But as you probably know, near cities, we don't see the stars when we look at the sky. This is because the weak starlight that reaches our eyes and cameras is mixed up with artificial light that bounces back from the atmosphere. But we knew that most of these artificial lights are powered by alternating current. And we wondered what happens here, where the AC voltage crosses the zero and is thus very low. Is there a brief moment in time where the lights are dim enough for us to capture the stars? But capturing this moment with a high-speed camera will not do, because the required short exposure would result in a very poor SNR. Rather, to overcome the read noise, we needed a camera that would collect signal from many such moments during a single exposure. So with this mission, I went to Kiros's lab at the University of Toronto to build the A-Cam, a camera specifically designed for imaging under AC illumination. So after a while, we finally had the camera working. So we pointed to the city for a test run. And what did we get? We get this result. There's no moment of darkness, and all the lights seem to be flickering with different phases. After further investigation, it became clear to us that different bulbs flicker differently. But we also found that this temporal structure, which is hidden from the human eye, is very useful. So to understand why bulbs flicker, we need to know a little bit about the electric grid. Power plants supply AC voltage in 3 phases separated by 120 degrees. This voltage is approximately a sinus of frequency 50 or 60 Hz, depending on the country. Different bulb types connected to the same AC phase have different flicker profiles. We call a single period of this profile as the bulb response function. Connecting identical bulbs to AC phases 120 and 240 causes a corresponding phase shift in their response function, which means that we can treat the scene as if it has 3 different sources, each with its own unique temporal profile. So the first thing we can do with the bulb response function is to identify bulbs in a scene. For example, if this is the measured flicker for this bulb, and we have a dataset of bulb response functions, we can use it to identify not only the bulb type, but also its AC phase. Repeating this method for every bulb in a scene, we are able to do bulb type and phase recognition in the scale of a city. Such city-scale phase information is highly valuable for power grid analysis and monitoring. And recently, we started a new and exciting collaboration with researchers at UMass's STEMA lab with the goal of using the A-Cam to analyze power grids in developing countries such as Sub-Saharan Africa and India. Things become more interesting when we look at scenes like this, where multiple lights are all mixed together. So how can we leverage flicker in such a scene? This is an image sequence captured using our A-Cam system. This sequence spans the flicker cycle. It might be hard to see the flicker, so here's a digitally amplified version of it. Now, using our bulb dataset and the image formation model under AC illumination, we can solve an inverse problem and recover the single source images of the scene. The single source images of the scene show how it would appear in a standard exposure if only that source was active. Now you will notice that we only decompose the scene into three sources. These three sources correspond to the three AC phases that power the ceiling bulbs, which are all of the same type. And once we decompose the scene, we can recompose it under illumination that had not been present during acquisition. For example, here we simulate an image where all bulbs connected to phase 240 are swapped with sodium bulbs. So here's a street that has four sources, a fluorescent bulb inside the parking lot, and sodium street lamps connected to all three AC phases. So let's decompose this scene. Here's the recovered fluorescent. Here's sodium 0, sodium 120, and sodium 240. And our method also works when one of the sources is constant, like in this scene, where the girl's reflection comes from indoor flickering lights, while the outdoor scene is illuminated by sunlight. So, the original ACAM was giving us nice result, but it had a somewhat uncomfortable form factor. So the next step was to make the ACAM simpler. Now, in order to do that, I need to tell you a little bit about how the ACAM works. Essentially, the ACAM has three major components: a camera, a programmable mask, and a controller. The controller's job is to sense the AC voltage in real time from an outlet and trigger the mask to expose the precise interval within the flicker cycle that we want to capture. So the challenge with using a smartphone is that we don't have our synchronization signal anymore. But we are lucky, because it turns out that we can use the next best thing, which is the actual bulb intensity. And the reason we can do that is because most smartphones have a rolling shutter sensor. In a rolling shutter sensor, rolls are exposed one after another with a constant but very short delay. This delay causes artifacts when imaging fast motion, but for us, this delay provides a high temporal sampling rate for the scene's flicker. Depending on the camera, the roll delay enables between 200 and 1600 samples per flicker cycle. So when we capture an image under AC illumination using a rolling shutter sensor, each image row samples a different time within the flicker cycle. Our new synchronization signal is now embedded within the image rows. Of course, one frame only gives us one sample within the flicker cycle, but capturing multiple frames allows us to recover the full flicker sequence of the scene. For more details, please see our ICCP paper from 2018. So in the last part, which is still in the yin domain, we're going to exploit another inherent property of light, which is mostly invisible in our everyday experience. This work is a collaboration with Matt Atul, Srinivas Narasimhan, and Dinesh Reddy from CMU. So many computer vision tasks rely on artificial lights as visual markers. For example, motion capture systems often use suits fitted with small LEDs. Car headlights can be used to track cars at night, and 3D scanning of an object can be done by sweeping it with line illumination. Now, in all these applications, the first core task is to position the markers in the 2D camera image plane. Artificial light markers are especially good for fast applications, because as we increase the capture speed and therefore reduce the exposure time, our markers remain visible and are even easier to find. But while short exposures are easy to do, increasing the capture speed further is limited by bandwidth. As you can probably see in these examples, our markers occupy the image plane very sparsely, and most of the pixels we are reading out are just dark pixels. So can we design an imaging system that is more efficient? So here's an idea. Let's save bandwidth by throwing away most of the camera pixels and only reading out the center image column. Since we're only reading out a single column, we effectively have a 1D camera or a line sensor. Line sensors have very high throughput and usually operate at tens of thousands of lines per second, while also being light efficient due to their large pixel sizes. So what type of optics should we use with our 1D camera? Well, one option is to use a cylindrical lens that would focus the points into lines intersecting our sensor. Notice that in this configuration, the 1D sensor directly measures the point's y image coordinates. Adding a second sensor allows measuring both x and y coordinates for sparse points. But the cylindrical lens approach is limited. The problem with cylindrical lenses is that their measurements can yield many possible solutions. For example, the acquired measurements for the scene on the left fit 6 different valid solutions. Moreover, this approach is simply not applicable to other scenarios like sources in the wild and line projection. So let's go back to our single 1D camera solution. Is there another way to encode the missing x coordinates? Well, our solution uses color, and this is done by placing a diffraction grating in front of the lens. A diffraction grating is an optical device that functions much like a prism. An incoming beam of light that passes through the grating is split into different wavelengths traveling in different directions. Therefore, when viewed through the diffraction grating, each seen light source creates a rainbow streak on the image sensor. The streak's vertical position on the line sensor corresponds to the y position on the 2D image plane, while the point's x coordinate is encoded by color. So let's look at an example. Here's a motion capture glove fitted with 8 LEDs. Here are the rainbow streaks created on our sensor plane. Here is what our 1D camera actually measures. And here are the recovered 2D marker positions. Okay, so I'll finish by showing you some cool results. So here's a fan mounted with 2 LEDs rotating at 1,000 RPMs. Now, on the right, the white LEDs were captured using a 2D camera that is capturing at its maximum speed. And in green, we overlaid the point positions recovered using our system. Here, using the same exact camera, our system recovers the LED positions 16 times faster. Because our method does not require controlled sources, it works for light sources in the wild, like these car headlights. Our method is also not limited to point sources, but can handle continuous curves as well. Therefore, it can be used for fast 3D line scanning. Here, we see an object being scanned on the left, the view from the sensor plane in the middle, and the sensor line measurements on the right. These sensor line measurements are created by a single column in the middle view. And here is the recovered shape using a standard 2D camera and our result that uses a 1D sensor. Now note that to the best of our knowledge, our system is the first structured light system that uses a 1D source and a 1D camera. Finally, here we scan our fan using static line illumination, like the ones used in a conveyor belt. Here we see a video from a 2D camera at 60 frames per second. Note that the camera is unable to capture the fan's real motion, causing the fan to appear to rotate backwards. And here we overlay the roll disparity measurements using our system. Once again, using the same camera, we are able to recover the disparity 30 times faster in this case. So to conclude this talk, here's my humble take-home message. Sometimes more is more, and by carefully adding more structure to our light sources, we can achieve ever more difficult goals. But sometimes less is more, and by digging under the surface, we are able to find hidden structure in seemingly unstructured artificial lights. In this talk, we've seen two examples for such structures. A temporal structure that comes from the bulb response function, and a spatial spectral structure that comes from light diffraction.
Thanks so much for the great talk. This is awesome. So we're running slightly behind schedule, just a few minutes behind schedule. So we're going to have kind of a little bit compressed Q&A. I'm going to start with a question from Maolin Gao. If the rolling shutter approach can help in inferring the phase of electricity, does it mean that you can also use it to estimate the light intensity and or direction?
Oh, that's a great question. It actually depends on whether the flicker profile or the bulb response function changes with the intensity. So for some bulbs, I imagine it's not changing with intensity, but for other bulbs, for example, LEDs, if you dim the LED a little bit, it starts to flicker in a very significant way. So for example, for that type of LED, you will definitely know just by looking at the duty cycle of the flicker, how much it was dimmed. And about the directional light, I'm not sure about that. Again, it's the same answer. If the light direction, if the flicker depends on the light direction, then you will be able to detect it, but I'm not sure if it does. So.
Great. I'm going to interject with my personal question here, kind of a philosophical question.
Yeah.
When you were presenting the talk, you kind of started with the motivation of the flickering light problem to actually do astrophotography in environments with light pollution.
Yeah.
Was that the initial motivation? And B, how did you feel as a PhD student when you noticed that all the lights were at different phases?
Oh man, it's a great question. So that's why I wanted to include this thing, because I went to Kiros's lab with a clear idea, with a beautiful thing to do, and then it was not easy to build this camera. And once this camera was ready, I'm seeing all these lights flicker differently, and to be frank, my heart sank in that moment. But then it was good that we had two great professors to say, well, this is not a bug. This is actually a great feature. And so, it turned around to be a very interesting thing. But it was definitely a big surprise, and momentarily it was not so pleasant.
Yeah, it's remarkable how you took that insight, something that could have been crushing defeat, and turned that into a big win. So that's
a lot thanks to my great collaborators, Yoav and Kiros, who were there with their experience to basically see that the hidden gem that we found.
Great. So last question is coincidentally from Yoav. He's seeing the new work at Carnegie Mellon for the first time, and he's wondering what the limitation and trade-off of the 1D diffractive approach is.
Okay, great question. So first of all, there is, if it didn't come clear from the video, there is some sparsity assumption here. Obviously, for a scene which is, where every pixel in your image is giving you information, then this will be a very challenging. There is a sparsity approach, assumption when using this thing, and basically this is sort of like a line between very, very sparse system, it will work great, and as you increase the density, then you will basically start to see at some point a degradation in the performance.
Okay, wonderful. Thanks so much for your talk, Mark.
Thank you for inviting me.
Great to have you. Our next speaker is Ulugbek Kamilov. Okay, Ulugbek, if we can share his video, fantastic, is an assistant professor and director of computational imaging, the computational imaging group at Washington University in St. Louis. Ulugbek has, again, received numerous awards. Notably, he's the recipient of the IEEE Signal Processing Society Best Paper Award in 2017. On a personal note, I think among the many reasons that Ulugbek's work is very unique is because it blends the modern ideas of deep learning with a highly principled respect for the physics of the imaging processes, which allows superb performance in imaging systems that range from radar to microscopes to autonomous sensing. So Ulugbek, it's great to have you here. And why don't you feel free to say hi while I pull up your video.
Yeah, thank you everyone for joining in. I also just pre-recorded my video and decided to just go ahead and use it. So I'll be here to answer any questions. Hello everyone, welcome to my talk. My name is Ulugbek Kamilov. I'm an assistant professor at Washington University in St. Louis, where I'm also at the director of computational imaging group. Today I want to talk to you about the techniques that we have recently developed, and that technique is called regularization by artifact removal. And as you're going to see, it's going to be very much related to a recently developed technique called regularization by denoising. And I'm going to explain you a little bit what does this new perspective of regularization by artifact removal bring us and its benefits. What we're going to talk today about are imaging inverse problems. So I assume many people watching this presentation are at least vaguely familiar with imaging inverse problems, but let me go over what the specific formulation we're going to consider. So in the formulation we're going to look at, we're interested in unknown image X. So this is what you see here, which is acquired through an instrument that's represented through this operator H, which can be linear, which is very common, and in application we're going to consider it will be linear, but it could also be nonlinear. But beyond the instrument, there's also some noise that comes in through sensing or through some other mechanisms, and we're going to end up observing Y. So this mapping from unknown X to Y is what we call the forward problem. And forward problem is pretty straightforward to solve, so long you know the physics of the instrument and you know your statistics of the noise. Now, what we're really interested in are the inverse problems, and this is a practical problem of trying to recover the unknown X, the true object, given the measurements Y. And the reason I'm very interested in this formalism of linear inverse problems is because many, many problems in biomedical imaging and beyond can be formulated as inverse problems. And here's a little table with several applications, and for each application you can see the forward model, where you can see the same language being represented over and over, where what we care about is recovering X given Y. So if we develop a nice set of algorithms for inverse problems, then we can address all these problems in a pretty unified way. Now, in today's talk, I'm going to focus on one application, which is going to be magnetic resonance imaging. Now, MRI is very broadly used in medical imaging, and the way that modality, so imaging modality of MRI works, is by collecting information in the spatial frequency space. What does this mean? This means that unlike traditional photography, you don't collect your images directly in the spatial domain, which you see on the right-hand side here, YX, but we collect the information in the spatial frequency space, which is this K space here. Now, as you see, by collecting more and more information in the frequency space, we end up with better and better quality image or higher and higher resolution image in the spatial space. Now, notice another thing is that data collection is sequential. You don't end up with the image right away. You need to collect the data, which basically means that the speed of collection is proportional to the duration of MRI scan. And this is something we're going to talk to more about. So what are the typical challenges when considering imaging inverse problems? So let me highlight you 3 challenges. There are many other challenges in inverse problems. It's a pretty large area and many people work there. So 3 challenges I really want to highlight today is the first one is slow acquisition. Now, by slow acquisition, I mean in particular for modalities where information is collected sequentially and indirectly. Okay, and this is becoming pretty common even in photography. Nowadays, photography has shifted to computational photography, where images are collected in bursts, what I also collect in some sense sequential and in some sense indirect, meaning you don't do a full exposure and get one high quality image, but rather get a lot of low exposure images and you try to fuse them with algorithms. And this is some issues that has to be addressed, and in particular, slow acquisition might be inherent to specific modalities. For example, MRI is one of those modalities. So here's an example of MRI. So we need to collect a sufficient amount of case-based information in order to obtain high-quality image. So a second challenge that is very common is imaging artifacts, and there's several reasons for having artifacts. The first reason could be subsampling, and if you don't collect enough frequency information or enough burst photographs or anything of enough. The second could be model mismatch, where you think your model of the instrument is something, but in reality it's something else. And finally, noise, which could be measurement noise or anything else. So these are three common sources of artifacts. And here's an example of artifacts that you can observe if you try to accelerate MRI image. So what you see here is a running application that we're going to see, where we collect a free breathing MRI scan, which is a three-dimensional MRI scan, and we try to separate it into 10 motion states. Okay, so 10 breathing states. And what you see here is a single slice of the image. And then that slice, you can see, I show it across 10 phases. So it's a 1 minute scan. Now, those lines you see here are called striking artifacts. And the reason they exist is because we're collecting radial lines and we're not collecting enough of them. So by doing 1 minute scan, we're heavily subsampling the data. And this is something that we're interested to address. And finally, there is a high computational and memory requirements. As I said in the previous MRI application, what we're dealing with are in fact 4D imaging problems where we have 3D plus time. And for example, to give you some examples, this data sets that we work for MRI are typically hundreds of gigabytes in size, but they could be even larger. And the reason the current sizes are limited to that is because that's a practical amount of processing that we do, and we're always looking for ways to process higher scale or larger scale data sets. Okay, so basically, it's also the three things we would like to address. So how do we want to address them? Now, the philosophy we're going to adopt is a philosophy that has getting a lot of exposure nowadays in the area of computational imaging, and the idea is try to fuse physical information coming from modeling the instruments with learned information, typically through deep learning. Okay. Now there are different ways to approach this problem. Let me give you broadly two classes of algorithms, that methodologies that do this, and I won't have time to cover everything. So the first approach tries to bring learning to models, and what I mean by this is where we try to have learned units embedded in the model-based image reconstruction. Okay, so there are many examples for this one. Very famous one right now is plug-and-play priors. Then there's regularization by denoising, which we're going to talk about, and finally the algorithms that we're going to talk about, which introduced by my group called regularization by artifact removal. But there are many others, and you can go to the literature and see many, many different ideas around bringing learning into model-based image reconstruction. Now, there's also a reverse side of this, where we try to bring models into learning, and this is kind of built around the concept of unrolling or algorithm unrolling, and it really was spun off by the algorithm called Lista, where you take an iterative algorithm, you unfold it, where each iteration is a layer of a neural net, and finally you end up training it with some data. And there have been a lot of developments in the area of unfolded algorithms, and I will not at all review this thing, but if you're interested, feel free to take a look at any of those papers. So there are many more papers that have come out meanwhile. Okay, so what I'm going to focus on next is regularization by denoising, because I find that a very particular elegant approach to do model-based and learning-based image reconstruction. Okay, let's go over this idea of regularization by denoising. So it was actually introduced by Romana Elat and Milan Far, and in particular, RED, that's how we're going to call regularization by denoising, was developed at Google Research when Michal was spending time there and working with Fermat. So the original reference came out in 2017 in Science Journal of Imaging. Now, the philosophy of RED can be divided into three important steps. So the first step in RED is to get the denoiser. So we're gonna today focus on deep learning based denoisers, but RED is compatible with other types of denoisers also. Now, for example, in the case of deep learning, the denoiser can be obtained by training a prior or CNN, convolutional neural network, to denoise images. So you're gonna take a set of images, you're gonna add additive white Gaussian noise to them, and you're gonna train your neural network to remove this to give you noise-free images. Okay, so that's one approach to obtain a denoiser, and this has been a very broadly used approach which got some success in practical applications. Okay, now once you get this denoiser, and typically what we do is we end up with denoisers that could be trained for several noise levels or could be one noise level. There are different authors in literature try to different approaches. But in any case, once you have a denoiser, what you do is you formulate an iterative image formation algorithm that resembles gradient descent. So here's an algorithm. So you can see it's an iterative. We go from xt minus 1 to xt. And then you can see instead of the gradient here, I put quotes here, we use something else. And this operator G, in fact, is a combination of the gradient of the data fidelity term, which models the physics of the instrument, and this kind of residual mapping of the denoising neural net. What do I mean a residual? It's a difference between the input and the output of the neural net. Okay, so this is really how the RED term infuses the information from the neural network. Okay, so this is the second step. We're going to discuss a little bit more about this algorithm in a few slides down the road, but let me give you a very interesting interpretation offered in the original paper in terms of an objective function. So under some conditions that have been specified in the original paper and discussed also in the paper by Richhorst et al., you can in fact say that the algorithm, this RED algorithm, is minimizing an objective function, where there is G here, which is a data fidelity term, where regularizer is specified explicitly from the denoiser. So you kind of reverse engineer regularizer from the denoiser, and note there are two terms. So what you're really trying to do is to push that residual to be orthogonal to the xt. And there's a lot more theory about it, and there's some condition when there's a valid. So I invite people to take a look at those papers if you're very much interested in the theory of RED. Okay. Now today, what we want to do is we want to push RED a little bit further. And what I'm going to discuss is a framework called regularization by artifact removal, which is an extension of RED, and an extension that leads to some new insight. And this is in fact our publication that was just recently accepted to be published in Journal of Selected Topics in Signal Processing. There is a special issue on domain-enriched deep learning, and you'll be able to soon read the full manuscript there. But you can also get the latest preprint online on arXiv. And this was done in collaboration with several people. Now, there are three things I want to address when discussing the RARE, and when I'm going to explain you what the RARE is. The first thing is regularization by artifact removal. Notice the artifact removal instead of denoising. Okay, it's a slight change, but it's a slight change, in fact, fixes a misconception somebody might have about RED, and we're going to discuss this a little bit more. And that misconception, once fixed, makes RED and RARE applicable to a broader class of problems. The second thing I want to discuss is once you accept this paradigm of RARE, now you can, in fact, start learning priors directly on undersampled data without any ground truth. And there we're going to discuss the scheme called artifact to artifact, which is essentially a noise-to-noise concept pushed again beyond the noisy. Okay, and finally, I want to discuss some new theoretical results and new interpretation provided by this RARE perspective. Okay, so let's get started with the first out of those three bullet points. So first of all, RED is artificially restricted to denoising in the name. So it's called regularization by denoising, but in fact, nothing in fact restricts it to be a denoising based prior. Okay, so here's a conventional view of RED where you try to get lots of noisy images and train a neural net to remove the noise. Now, there is one problem in this whole perspective based on denoising, so the denoiser-centric perspective, is the fact for many, many applications, it is really impossible to have data to be so clean that the only thing you're doing is adding white Gaussian noise. In fact, in many applications, the images, unfortunately, are already artifact corrupted. And what you end up training is not the denoiser. And this is a reason I invite people to take this broader perspective by considering artifact removing CNNs, which are the CNNs going beyond additive white Gaussian noise. So how is it more practical? In fact, if you take this perspective, you can realize that very often, instead of having a pure denoiser, what you can end up doing is given an instrument, and you can do two types of acquisitions. So with more subsampling and less subsampling, you can try to train your neural network to remove imaging artifacts rather than noise. Okay, so it's a minor shift, but this shift of perspective now makes it possible to start thinking about training things in a practical settings. And we're going to talk about this a little bit more. So all we're really doing here is still staying within red framework, but replacing the denoiser by the artifact removing neural network. Okay, and the really motivation is the fact that for many applications it is impossible to have fully sampled data, and specifically in free breathing MRI, there is unfortunately no ground truth ever. So it's impossible to get very clean data because whenever people breathe, there's always heavy subsampling because of motion, because of the fast collection. So we always have to deal with the fact that we're removing artifacts instead of the noise. Okay, but once you accept this artifact removing neural network, the next step is you can simply integrate it into the same RED algorithm. So I'm just calling it RARE algorithm, but in fact it's exactly the same algorithm where we replace the denoiser by this artifact removal. So now instead of looking at the residual of the denoiser, we're looking at the residual of the prior. Now, by taking this perspective, now we can try to see, okay, what does this really mean? So if I look at these two terms, what are we trying to solve here, right? So if you simply look at this algorithm, what are the fixed points of the algorithm, okay? The fixed points of this algorithms are all the vectors x for which g becomes 0, because as soon as g is 0, your algorithm converges, it obtains a fixed point, right? So I'm going to call the set of all zeros of the operator g to be 0g, okay? So that's a set that contains all x's for which this is 0. Now, if we take this, we can give a very interesting fixed point interpretation of RARE, which has been discussed in our full paper. So now, if there is some image x star, which is at intersection of the 0 set of the gradient, okay? So this is a data fidelity term, and the 0 set of data fidelity term are the set of vectors that minimize the data fidelity term if it is convex, right? An intersection with the fixed points of artifact removing neural net. So what are the fixed points? In fact, fixed points is when the input and output are the same, meaning x minus rx will be 0, okay? So if there is something at the intersection, it is obvious that gx will be 0 for any value inside the intersection, okay? Then that x star will definitely be inside the 0 set of g, okay? So this gives an interesting interpretation. So in some sense, when there is an intersection, what you're really looking for are vectors that both satisfy the physical constraints coming from the model of the instrument and the learned prior, in the sense that they're artifact-free according to the neural network. When its input is the same to output, it is when, according to that neural network, that X doesn't need to be modified. Okay, so that's an interesting interpretation. On the other hand, if there is nothing in the intersection, meaning that the intersection is empty, then you can still interpret the solution of RARE, so X star, as an equilibrium point that tries to control an equilibrium between those two operators, the residual of the neural net and the data fidelity. Okay, so this is kind of the an interpretation of RARE/RED, meaning the RED framework where you extend the prior beyond the white Gaussian noise denoisers. So now let's talk about this artifact-to-artifact scheme, which now beautifully combines with the RARE to enable a new approach to train the priors for the RARE algorithm. So what is an artifact? It's a very simple recipe. So imagine the scenario where you do not have access to the ground truth. So for example, in MRI case, right? You do not have access to the ground truth image, but what you can easily do is to collect two independent views of the object. What does independent mean? It simply means two sampled objects, two versions of measurements sampled in a different way. For example, in the case of MRI, you can collect in the first case set of lines that are different from the second set of lines. Okay, so what you do have access are two measurements, Y1I and Y2I, and I meaning an element of the whole data set. Okay, so now once you have those two measurements, it's very straightforward to take the pseudo inverse. So if you take the pseudo inverse of each of the measurements, what you're going to end up here are the images which are corrupted by artifacts. Okay, when we saw the example of it in earlier slide for a 1 minute scan, you're going to end up with two images with artifacts. But if the data collection was different for each one of them, artifacts will not be the same, meaning the artifact patterns will change across the whole data set. Now, the principle of artifact to artifact, which was inspired from noise to noise, is to simply train the neural network to map one artifact corrupted image to the second artifact corrupted image, with an understanding that in principle, the neural network will end up learning more of the object rather than of the artifacts. And in practice, this happens very nicely, and I invite people to actually read the full paper to see a lot more examples and the discussion on the artifact to artifact network. In fact, the underlying assumption here is that the expectation of artifact corrupted images has to be the same as a true ground truth image. So if this is roughly the case, which is the case in our MRI example, then this neural network will be able to remove or reduce amount of artifacts. But on its own, typically, it will not be enough, and we're going to see this in a second. It will be a very nice prior to be integrated within the RARE algorithm. Now, finally, let's discuss some theoretical perspectives of RARE, and in fact, it is completely backward compatible with RED once you restrict artifact removal to wide Gaussian noise removal. So it might look heuristic, but you can really build theoretical framework around the algorithm. So the first theorem I want to mention is the fact that under simple assumptions like the existence of a fixed point, second, the convexity of data fidelity term, and non-expansiveness of the denoiser, you can really prove the convergence to the fixed point as a 1 over t. So you can see this is a constant divided by t, meaning you get O1 over t convergence, which is the same type of convergence as a traditional gradient descent algorithm, which is quite interesting. Now, the second theoretical perspective is quite intriguing. It says that if I replace my artifact removal network by any proximal operator, or meaning that network is an implicit proximal or maybe even explicit proximal operator, then what's going to happen is the algorithm ends up minimizing approximately an objective function f, where g is a data fidelity term, h is a regularizer, and you can minimize this with accuracy, any desired accuracy, because you can see there is a tau here, and that tau is a parameter within the proximal operator. So by controlling that thing, you can get arbitrarily close to the minimizer of a function f plus h. Now, the reason this is quite interesting is that it raises a subtle point. So in the original RED paper, there is an interpretation of RED with a specific regularizer. But in fact, it's one interpretation of the algorithm. You can run exactly the same algorithm, and if your denoiser corresponds to something else, you might end up minimizing a completely different objective function. In fact, that objective function can have an arbitrary convex regularizer h, which is quite intriguing. And if you're interested in this, I'm very happy to discuss this in the future. Okay, so there are a lot of examples to cover, and I have very few minutes left. But let me just give you a very rough idea. So overall, when we validated RARE both on experimental data, where we collected real MRI data, and on simulations. So what you see here are some experimental results, where the numbers you see here are relative PSNR, where relative means with respect to reference that was collected over 5 minutes. Okay, we never have ground truth. The best that we have is a reference image, and it was collected over 5 minutes and reconstructed using sparsity promoting regularizer. So if you train a UNet with this, you would get something like this. If you train just artifact to artifact network without any reference images by mapping simply artifact corrupted images to each other, you get something like that. Now, if you plug this into a rare algorithm, you're going to see it cleans up and reduces the amount of artifacts within the images. And there are many more examples in the papers that you can see. And here's a little illustration that algorithm is in fact quite fast. The reason it's quite fast is that we initialize it with the output of the neural network, which gives us pretty good solution, and we just simply run it across iterations. We also validate it for simulations, and here's an interesting one where you have, in the simulations, you actually have a ground truth. If you use RET with DNCNN trained on ground truth, you get a set of results. Rare pretty much matches those results, although it never sees the ground truth, which is quite an interesting practical implications. So to kind of wrap up my presentation today, we increasingly rely on implicit regularizers based on learned operators like deep neural nets. Rare is an algorithm which has a very elegant principles based on regularization by denoising, but also some new theoretical principles that we have been discovering over the past years. And it can be really combined with a scheme like artifact to artifact to enable image reconstruction with priors that have been learned without ground truth. And this is a moment to thank everybody for watching this video. And if you're interested, please reach out to me either on Twitter, through email, or come visit the website of my lab. Thank you very much.
Excellent. Thanks so much for the talk, Ulugbek.
Problem.
So there's some questions in chat. I see you've already been proactive in answering some of them, but just so,
one and the left, the others all.
just so that we can say it orally. So Lei has asked, good to see you, Lei. Lei has asked, what is the reason to flip the measurement operator in the pseudo inverse? So Ulugbek, do you want to give your answer orally?
Yeah, so I realized actually on my slide, it's not, I guess, well elaborated. The flip doesn't mean you do any flipping of any kernel or anything. The flip just means, you have two views or two subsampled views of the same image. Now, to train that network, you use a second, just like in a noise-to-noise scenario, use this output of, one to train the other, and you can just flip them around and repeat the process. So you never have fully sampled data, but you use subsample data to guide the training.
So Chris Metzler from Stanford has asked, how many measurements do you need to train a network using only measurements, without ground truth? Do you need more examples than if you trained on ground truth, for example?
So I cannot, unfortunately, answer generally to this because I don't have any theoretical understanding to that specific thing, but I can tell you in the context of MRI. So in the context of MRI, we used roughly the same amount of measurements. Actually, it was exactly the same number of measurements. We have 10 participants we scanned, and the same 10 participants we used for training, both supervised and then supervised with the artifact corrupted images versions of the network. But it probably will depend on the specifics of the measurement operator. I can imagine in optics it's being much more challenging, for example.
Okay, great. Usman has asked a question of, why does the neural network not memorize the noise? Is it because the prior is stronger for the image than the noise, or is it because of the independent noise in the second image?
Yeah, I have to say, Usman, this is a fascinating question. I think this is something we're all kind of trying to realize now. If somebody has read the deep image prior paper or other types of papers in that area, right? Many convolutional neural networks seem to be memorizing image-like features much better than random noise. So specifically, completely random additive white Gaussian noise is not very easy to memorize. You cannot really memorize it because it's high complexity, right? However, you can memorize image structures. Now, what we see here is our patterns, artifact patterns and noise are pretty randomized across images if you look at them. And then when you train, the real image features are much more, similar and consistent. So you do end up memorizing them much more easier. But if you really want to look into more, I guess, theoretical explanation of this, I think noise-to-noise paper gives some taste to more formal explanation of that.
Okay, great, fantastic. One last question here, just as a general question. You overviewed a lot of physics-based learning methods, and absolutely, the field has been very fascinating over the past few years. Where do you see this field heading, not just in the next few years, but maybe the next 10 or 20 years as well?
Oh, you see, the world is too heavy-tailed for me to predict this, unfortunately. You know, I do linear extrapolation, but the progress changes. So I'll restrain myself from really answering this thing. But I do expect a lot of benefit. I mean, I really love other talks today too. You can think along those same lines where you boost the learning by learning only what you need to learn and leveraging other types of information where you can leverage. And I think, you know, putting those things together, we'll all get a lot more interesting algorithms in the next few years. Unfortunately, 10 years is too far for me to predict the trajectory. Sorry.
Okay, excellent. So thanks so much for your talk. Really appreciate it. Don't leave yet. There's before we head to the break, I'm going to pass it off to David, who will talk about taking a group photo.
Okay, great. So at this point, we'd like to do a little group photo. And if you'd like to participate, you can go ahead and turn your video on. If you don't want to do that, that's fine. We can actually see many of your names here. If I just switch to the grid view, so your name would be recorded. And afterwards, we'll take this and we'll put it on the group website just as a little memento. And you can say that you're at this historic CCD.
Okay, welcome back from that very, very short break. But I think we want to try to stay on time, so let's get started again. First, I just want to say I'm so incredibly thrilled to see how many people we have participating in this year's CCD. I think, you know, we all wish that we could be together and see each other in person, but one advantage is that I think that we can, you know, bring together people who wouldn't have been able to make it to CVPR otherwise. So very excited to see that. So, and just so you know, David is putting a link to the photo that we just took in the bottom screen, and that will also be posted later on the CCD website. It was such a great set of talks in the last session, and I know that going on, we're also going to have some really great talks. This session is going to have an invited talk from Sabine Susstrunk, and also the first set of spotlight talks, which spotlight talks are 3.5-minute talks on a variety of different topics that were submitted to us. So let's just get started then. Okay, so Sabine Susstrunk is a professor at EPFL in Switzerland, where she leads the Images and Visual Representation Lab in the School of Computer and Communication Sciences. Her research area is in computational imaging, computational photography, color image processing with an emphasis on spectral sensitivity domains, and computer vision. And Sabine is also director of the Digital Humanities Institute. So with that, I would like to, maybe Sabine, you can just say hi briefly, and then I can play your video afterwards.
Okay, well, hello everyone. So it's a real honor to be invited to this workshop. I've been enjoying what I could. Unfortunately, I had to be a little bit late because I had another meeting going on. That's the one thing. But the good advantage is it's now late for me, so I'd be happy to actually listen to the rest of the talk. So like everybody else, I chose to actually pre-record my video and play this one then instead of me talking a second time around it. So please, Katie, go ahead.
Thanks. And yeah, just like the other talks, please put your questions in the chat during the talk and afterwards, and we'll have live Q&A at the end. Okay.
Hello, everyone. My name is Sabine Susstrunk, and I'm professor in the School of Computer and Communication Sciences at EPFL in Switzerland. I would like to thank Katie, Achuta, and David for their invitation to present some of our work on denoising. Yes, denoising again. This will neither be the first denoising talk you have listened to, nor will it be the last, I am quite sure. My motivation to bring up this topic at the Computational Cameras and Displays workshop is that many of you are working on displays, making them bigger and better. Here's an example of an installation at EPFL. In the Heritage Lab, which is within the Montreux Café, which is within the Art Lab, which you saw on the title page. It's the only place in the world where you can watch almost the entirety of the Montreux Jazz Festival, so all the concerts of the past 50 years. The Montreux Jazz Festival is one of the oldest and most famous jazz festivals in the world, and EPFL has digitized the audio and video archive of the festival. So if we were making bigger screens and better immersive experiences, what does that mean for the images and videos we acquired a long time ago, such as this one?
So we'd like to just do a little impromptu thing, and thought maybe this would fit in with the theme. Okay? You know. Or would you rather do the blues? Do the blues? Huh? Oh, you don't know the blues? Okay. All right.
These videos were captured in low resolution, under low light conditions, and suffer from compression and digitization artifacts. Quite frankly, when watched on a big screen, they do not do the artist of the time justice. So in my lab, we've been looking at image and video restoration, again, but this time also considering the deep learning approaches out there that are very promising and can provide, under certain circumstances, better visual quality than traditional signal processing methods. No, I cannot yet present you a full image restoration solution. We are still working on the problem. But one of the pieces of the puzzle is actually denoising, and I would like to present our work on that one. Specifically, I'll talk about our paper, Blind Universal Bayesian Image Denoising with Gaussian Noise Level Learning, that was published in IEEE Transactional Image Processing this spring. It is the work of my brilliant PhD student, Majed El Hello. So, let me get started with some of the basics for those not that familiar with the topic. Denoising is an image restoration task where we want to recover X given Y. X is the original signal, or the denoised image, if you will. Y is the noisy image, and N is the noise. Rarely, but sometimes, we also want to estimate the noise. Denoising, though, is an ill-posed inverse problem, as there are many possible solutions for X and N given Y. Additive white Gaussian denoising is a special case of denoising, where N is sampled from a white Gaussian process. In other words, the noise is the same for all signal frequencies, has zero mean, and its noise level is determined by the standard deviation sigma. Additive white Gaussian noise is not necessarily the best model in practical scenarios, such as denoising raw images or restoring the video I showed you before. However, images with other noise distributions, potentially data dependent, can be transformed into images with Gaussian noise and back. And maybe even more importantly, in today's publish and perish world, a large part of the denoising literature focuses on Gaussian denoising. Here's the Google Scholar search, and as you can see, the Gaussian denoising term resulted in over 103,000 results. Probably not all related to images, but still. By the way, for the purists here, I'm cheating a little bit, of course. Gaussian noise and white noise is not necessarily the same thing, but I'm going to skip it for now to make my point. So let me also define blind and universal denoising. So blind means that the method's going to work on any kind of image with unknown test noise level. And the noise level, by the way, just to reiterate, is basically the noise standard deviation sigma. Universal means that only a single model suffices for all noise levels. So you do not need to have different models for different noise levels or different algorithms or solutions for that one. So what are then non-blind and non-universal? Let me give you some examples. So non-blind, non-universal will be class-aware denoisers that require the noise level or denoisers trained per noise level. Blind and non-universal are class-aware denoisers. Non-blind and universal would, for example, be the FFD-net, which was recently published, which is, by the way, the work of the same authors who also authored DNCNN, the second reference here by Zhang et al., which was also published in the IEEE Transaction on Image Processing in 2017, and which we actually will compare to. Now, DNCNN is very popular. As you can see, it came up as the first entry of my Gaussian denoising search, and it has been extensively cited. It is a very, very clever method because it basically is a network that does not try to actually predict the denoised image. So it's not going to give me X directly. It actually gives me a residual image, which is supposedly the noise. So here, this is one of these methods that actually tries to estimate the noise and not the image. So the image restoration is actually of the form that X, the clean image, is going to be Y, the noisy image, minus the residual image, the noisy image learned. Now, one last introductory comment is actually how do we actually assess an image denoisers? By definition, and for better or worse, if one will, we have used these image quality metrics as mean square error, PSNR, or also SSIM. However, there's a problem with this. What is the optimal quality in terms of MSE? It's actually the identity map. With zero mean noise, i.e. white Gaussian noise, that would be the identity map. So that, of course, is not what we want. We want actually a denoised image, not the same image back. And so for a long time, we have actually used the idea of image priors to actually force the denoising or in general image restoration to get to a good result. And image priors can be anything, can be assumptions on gradients, sparsity, self-similarity, network site, etc., etc., etc. There's a huge body of literatures on image priors. But what is actually an optimal image prior, and in what sense is it optimal? And that's actually the question we try to answer in this work. So let me give you the two contributions that we actually have. So the first experiment we did is that we made the assumption that X, i.e. our original signal, if you will, per image, has, just like N, a Gaussian prior. So in the Bayesian framework, the conditional probability distribution of the noise lists data X given a noisy observation Y, where again Y is equal X plus N, is given by the shown relationship, where capital X and capital Y are the random variables corresponding respectively to small x and small y. Now, if we're interested in the conditional distribution as we search for the maximum a posteriori probability map estimate X hat of X. But in addition, the trick for now is that we also model the data prior on X as a Gaussian distribution, centered on the mean of X. And now the solution of our problem, which I'm not going to talk too much about it, I'm going to kind of refer you to the paper, is, we can solve for X hat and get the following expression. So X hat is basically the mean of X over 1 plus S, where S stands for the signal to noise ratio, plus Y, i.e. the noisy image, divided by 1 plus 1 over S. So how do we implement this solution now? So our FusionNet architecture is basically built on the DN-CNN architecture. So we incorporate the basic structure of the optimal solution into the architecture of the DN-CNN, and we call it the FusionNet. We really truly leverage the same architecture as the blind DN-CNN shown on top. The CNNs are all composed of a sequence of convolution layers, ReLU units, and a batch normalization logs. Note that Fs is inversely proportional to the SNR and proportional to the noise level. The FSCNN thus predicts 1 over 1 plus S, seen in the previous slide, where S again is the SNR of the input image. And the prior CNN predicts the mean of X defined in the previous slide too. So, how do we evaluate this? So, we trained both of the networks and tested, of course, both of the networks with data generated synthetically according to the Gaussian image prior assumption defined before. The image pixel intensities for the training data are drawn at random from a Gaussian distribution with a mean of 127 and a standard deviation of 25. The standard deviation of the Gaussian noise is chosen uniformly and at random within the interval of 5 to 25, as indicated in red on this slide, during training. For testing, the networks are evaluated on test images where the added noise is also Gaussian with a given standard deviation, so 5, 10, 15, 20, or 25. Now, the optimal fusion, which you saw on the first row, is the exact mathematical solution of the X hat I showed you before. In other words, we give exact S and mean X values and derive the optimal fusion. Now, when you look at the results given in PSNR here of DN-CNN, you can see that basically both networks perform similarly and they're basically quasi-optimal in terms of expected square error. The two-sided t-tests, that's what the p-values were calculated for, also show that there are no difference in the results. They really, on this kind of, on the, training noise levels, so the levels I've seen in training noise, they are basically the same. Now, what about now on data not seen during training? When we look at these results, you can see that the fusion net remains almost optimal while the performance of DNCNN decreases. So in general, we can say that the fusion net, our fusion net generalizes better than DNCNN. And the drop, if you look at the noise level of 70, is actually quite substantial. It's over 3 dB. So this is now on totally synthetic image data. Images do not follow Gaussian prior. This is not what we can use. So we've also extended our network now to real unknown priors. And we do this by actually learning the fusion function for a data-specific non-Gaussian prior. So our new network is actually called Blind Universal Image Fusion Denoiser. It's still very much based on the DNCNN architecture, but now we actually do have a product fusion and fusion layer to actually account for the non-Gaussian prior. The optimal fusion function takes as input here the noisy image, Y, the prior prediction, and the noise predictions. And both are outputs of the respective CNNs. Now, the product fusion is inspired from the Bayesian solution. It creates the same inputs to the fusion layer as in the Gaussian case. The optimization loss is a function of the concatenation of all the inputs listed here. So F sub n, F sub b, so the outputs, the prior outputs, and then also the multiplication and the product fusion inputs, which are very similar to the Gaussian priors that we looked at just before. The network architecture is again the same as the DNCNN, and I'm actually referring you to the paper for all the details. Now, what are the results on grayscale BSD68? That's the well-known Berkeley dataset, and which you can see in this table. So I'm just going to talk about the results for the noise level, which we train up to level 55. You also see the noise level, the results for noise levels trained up to 75, and the comparisons with BM3D, which is probably nowadays one of the best, if not the best, non-deep learning denoiser out there. So, training noise levels up to 55, and now the results for DNCNN and our blind and universal fusion denoiser. So on the very, very low noise level, 5 and 10, you can see that actually DNCNN outperforms our fusion. But starting from a noise level of 15, we are actually doing better. Now on noise levels not seen during training, we are actually doing significantly better than DNCNN. And again, at the test noise level up to 75, sigma of 75, we actually again do more than 3 dB better. So the takeaway messages are, first, that the generalization improvement of over 3 dB that we've actually seen in the theoretical experiments is also matched in the real experiment. Again, we generalize better than DNCNN. And second, we can also say, but even on the seen noise level during training, we also improve denoising. So let me show you a few results. Here are original noise level and whatnot, and considering that we're all going to look at this over the video, we're not going to see anything, so I'm just put them one after the other. So here's the original, here is the noisy N image with sigma of 25. By the way, all these inputs are 256 by 256. I mean, they're tiny, so this is why it might look a little worse on screen than what you expect. Now this is the output of the prior CNN. Granted, we actually have no idea what it is, but what this actually represents is the image prior, is per pixel the expected value of the distribution out of which the pixel intensities were sampled. So that is basically the output of the CNN prior. Then this is the output of the noise prior, and this is the result we're getting, denoised. And we're using the our Fusion net trained up to 55 noise level, or C noise level during training is 55. And this is now DNCNN. So you can compare the two, and we can see that we do a little bit better than DNCNN. Now another example, let me just step through each one of the steps again. This is the original. This is a noise added, again, additive white Gaussian noise added up to a level of 75. Then this is the output of the prior CNN. This is the output of the noise CNN. This is our denoised image, again using our BOIFID version trained up to noise level 55, so it hasn't seen noise level 75 during training, and this is DNCNN. Ours has a bit more, can remove a bit more noise, does introduce some other artifacts though. And then, of course, at the end, there's also, we can extend the whole thing to color, and I'm going to leave you, I'll leave that up for you who are interested enough to read up on this on the paper. So, what's the conclusion? So we presented some fusion denoising, actually a theoretical framework for an optimal additive white Gaussian noise denoising solution. Again, we're not claiming that this is general, but I think it's a nice kind of like contribution to the Gaussian denoising. And we can say that the fusion net generalizes better to larger unseen noise levels. So the generalization aspect of our fusion net is actually quite impressive. Now our blind and universal image fusion denoiser improves the denoising performance both on training noise levels and on unseen noise levels for images, and shows a promising path towards integrating estimation theory within network architectures. Now, at this point in time, their new architectures are always probably better. I cannot claim anymore that we're state of the art, but it is a very nice contribution, and it can be implemented on other deep learning architectures. So in the paper, we also showed examples with MemNet, and actually it outperformed it. So now, this was just one paper. This is not the end of denoising by a long shot. You will hear and see, especially also at CVPR, quite a few new and very interesting and very exciting denoising papers. Image restoration is something that is just going to be around for probably ever, because it is an ill-posed problem, but also because we still have actually real applications where we need this, and real videos, images and videos to denoise. And with that, I want to give you another example, actually, of the end of the concert of Aretha Franklin given at the Montreux Jazz Festival in 1971, because it does absolutely deserve to be restored, and it might also give a message to us in these times.
We would like to thank you from the bottom of our hearts, right to the bottom of yours, for being so very, very important to us. We'd like to leave you with a little special message behind us. What we got to do is reach out and tell somebody's head, make it a better world. Yeah. I love you. We got to reach out, touch somebody's head. We gotta make it a better world. We got to do it. You gotta say anymore.
For the excellent talk. Please put your questions in the chat. And also, you talked about, this is denoising again, but as we saw, for instance, in Beck's talk, these denoising networks and these new denoising methods are being used in so many different kind of ways than just denoising of images. So they're becoming very widespread in how they're being used.
Well, that's basically what I meant to say with the again, right? I mean, it's image restoration is not going to go away. It is ill-posed, and there's still so much room for improvement, right? Somebody has a great idea, and it's going to get better. I mean, and again, it's almost a never-ending problem, right? I mean, and I again saw in CVPR some really great papers about denoising, and we're going to go ahead, and we'll have some more and good ideas.
Mm-hmm.
So the again is just kind of like a little, wink. Yes, have it again.
Yeah,
but that's okay.
So good to continue it. So I guess I had one question before we start taking questions from the audience. One is I noticed, I was just curious because when you went through the prior network, I noticed sometimes there'd be these little kind of sweepy lines that would appear, and that would appear kind of in the final output. And I was wondering why it was appearing in the prior network, but not in the noise network, or maybe I didn't see it. And I was wondering if you had some insight in why these could be caused.
Yeah, I think that has to be some, to be honest, I think that has to be, that's data driven. I think that has to do, I'm not totally 100% sure, but I think has to do with something with the resolution and that original Berkeley set from the beginning.
Yeah.
Having said that, we should run this on, and honestly, we didn't, to be absolutely frank, we should run this on other images to make sure. My suspicion was it has to do with the original Berkeley data set, the downsampling of the Berkeley data set, and this is where it comes from.
Okay.
But that's my suspicion, but it's an excellent question. We should run this on some other data and see if this is true.
Yeah, I'm curious because the other methods definitely got rid of the spotty noise, but yeah, it was just interesting.
Yeah,
Anyway, I have a question from Chris. Echoing Achuta's earlier question, do you have any predictions about the field over the next 10 years? I guess this is the ... again.
It's a ... again. I think one of my prediction is that we are very close, that we can start creating images, fake images that are undistinguishable from real images, right? The StyleGAN +++ is a development which I find unbelievable. Now, these StyleGANs or the GANs ++ can help us in our work in computational imaging, but there's going to be a moment in time where we have to ask ourselves what exactly in computational imaging is still done physics-based versus just hallucinating something, right? I mean, I'm really asking myself the question of, in 10 years, do we actually still have cameras on our smartphones? Or are we just going to take an image of, especially in now times that we don't even know if we can actually travel anymore, we take a selfie, You know, we might have to steal the front-side camera and say, put us into the Himalayas in Paris or in Venice. Now, to be absolutely honest, Katie, your work will always be relevant. But maybe the computational photography one, we have to kind of rethink our position.
It
so
is
I
really
think
amazing seeing these GANs, especially for faces, where I think for faces it's different than other things right now because they have lots of data. It's very aligned and everything,
yes,
but they're just amazing.
Yeah.
Yeah.
But I think there is something to be, you know, who would have thought that GANs can get to that point 5 years ago, right? So, you know, the question was in 10 years, where do you think we're going to be? So there's still going to be physics-based imaging because we just need to have the physics-based, you know, nobody wants to see a GAN in medical imaging, right? I mean, that I think, or, you know, Katie.
You have to have some real uncertainty bars on it.
Exactly. But in computational photography, you know, what do we actually want? I might be wrong, right? Might be people still want to take their pictures, but I think there's going to be a development there that we might have to really, really consider.
Okay, great. Let's go on to the next question from Nikruka, sorry. BM3D has maintained a state-of-the-art for so many years. So have you seen in your work what makes it competitive after so many years, and why current networks that have surpassed traditional vision in detection and segmentation are not really beating BM3D significantly?
Well, one of the things is that the reason I think BM3D is still being used is because it, you know, it doesn't depend on a kind of data set, right? It depends on, well, it depends in itself on the data sets because it's a patch-based method. But I think one of the reasons it has prevailed is because it is specifically not trained on one specific data set that might not translate to something else. It is an algorithmic-based solution. Having said that, it's also computationally relatively heavy, so that doesn't make it really that applicable to many you know, solutions either. But it is just, you know, it just happens to be, and then the other thing I'm also blaming a little bit, it just happens to be the baseline, the non-deep learning baseline that just does so well in so many situations that just everybody is still actually using it. Hope that answers your question.
Yeah. Next question is, any thought on changing the formulation from obtaining the best quality approximated by SSIM or PSNR to obtaining the best quality for a succeeding set? So I think something like sequential.
Yeah, exactly.
Yeah.
Oh, you know, do you have another 3 hours so we can discuss this topic about PSNR and SSIM? Okay, no, I'm just kidding. It's
so hard to use those as metrics, right?
Exactly. Of course. I mean, it's the worst metric, but it's the one that seems to at least work reasonably well in a denoising kind of thing. And by the way, I'm kind of telling you this, denoising maybe PSNR, SSIM, almost any other image restoration task, these are not the correct quality, image quality metrics. Yeah, you're totally correct. We should, it's a little bit of a cop-out using PSNR and SSIM, and actually even SSIM. To be absolutely honest, if you report PSNR, you don't even have to report SSIM because it's so correlated with PSNR, you know, doesn't make any sense.
I find that for really degraded images, it basically, they become meaningless. I wonder actually if deep learning can help with coming up with better metrics. I'm guessing people are working on that, but I don't actually know about that work. So I think that would be.
No, but that's a very good question. But I think one of the reasons that we have to get over it when we talk about better metrics is the real good metrics are application dependent.
That's true. Yeah.
What do you want, right?
What's the feature you want to extract from this? Yeah.
Exactly. And the other thing is also, do you want to look at the images, or are you going to feed it into a computer vision system or a machine learning system to actually learn something, right?
Yeah.
So do we want to have a good looking image, or do you want to have one that preserves the most of the original information that was there? These are two totally different goals. And basically at the end, it will be two different metrics. And so, yeah, I'm actually thinking, Katie, you're right. Some deep learning could actually help with this kind of question.
Interesting. So there are still a few questions. I'll send them on to you, Sabine, if you don't get them. But I think we should move on now to the spotlights. But thanks again for your talk.
Yeah, thank you all of you, and thank you for giving me the chance to present our work.
So right now we're going to move on to the spotlights. This is the first session of spotlights. There's 2 sessions. One will be in the afternoon. And these are, the authors submitted an abstract followed by a 3.5-minute video on their work. It's a little difficult to do questions. So what we think is best to do is that you send a private message to one of the authors if they do appear on the Zoom call. And otherwise, we can have asynchronous question and answer session on the CVPR internal website, which David or Achuta will link to in the chat. And just make sure to say, just to help identify the spotlight you have a question about, you can just write the spotlight number, which will be shown before every one of the talks. Okay, I could start that now.
Hello everyone, welcome to See Through.
I'm Daria Okainak, engineer and oceanographer at Harbor Branch in Florida.
I'm Tali Trebich. I'm heading the Marine Imaging Lab at the School of Marine Sciences, University of Haifa, Israel.
Thanks for joining us. As a physics-based color reconstruction algorithm, See Through was published in CVPR 2019. But the breakthrough that led to it was an image formation model derived specifically for the ocean. We showed that the previously used model was formulated for the atmosphere and could not work well if attenuation was wavelength dependent. What led to a revised model was our meticulous investigation of attenuation coefficients. These papers make up 3 of the 4 underwater computer vision papers in CVPR in the last 6 years. Let's start with some results. If you first heard about see-through on the media, you might have thought it needs a color chart to work. It doesn't. Even if you had one color chart in the scene, it wouldn't be enough to do a proper color correction. I'll explain why later. It also doesn't need the scene to be forward-facing. That's because it doesn't use watercolor at infinity to estimate air light. It requires natural light and linear images, but makes no assumptions about the optical water type. It's an RGBD method, so it takes range as input, which can come from any source. Here we use structure from motion. See-through also works for video, but the challenge there is to record with no in-camera enhancements and minimal compression. Why does the revised image formation model make such a difference? Remember that an underwater image is the sum of the scene with attenuated colors, the direct signal, and the backscattered signal, which is fog due to scattering from particles. Here's the old image formation model and how the direct and backscattered signals look for a Macbeth color chart. What makes it old is not its form, but that the coefficient in both the direct signal and the backscattered signal is the same. In the revised model, they're different, and their dependencies on range, reflectance, ambient light, camera sensor, and water properties is explicitly shown. Here's a color chart imaged from 8 meters to 30 centimeters. Using the gray patches, we calculate and subtract backscatter. Notice how the layer of fog is now gone. Using the color patches, we calculate attenuation. Now the light in all the images is standardized. Remember how I said one color chart wouldn't help? Backscatter changes with distance and the attenuation coefficient changes with distance. Unless everything in the scene is at the same range, you would need a minimum of 2 color charts at 2 different distances. The attenuation coefficient was assumed to be constant for the last 35 years. That's how we restore colors when we have color charts in the scene. When we don't is when see-through comes in. See-through is the first method to use the revised underwater image formation model. It takes range as input. It estimates backscatter using the darkest pixels in the image, similar to dark channel prior, but not the same. First, it knows range, it doesn't have to compute it, and second, it takes pixels that are dark simultaneously in all 3 channels, rather than the darkest in any given channel. Then it computes an estimate of spatially varying illumination from which it calculates the attenuation coefficient. Finally, photo finishes. Please have a look at the papers for details. Thank you.
Conventional imaging injects light waves inside a scene and measures light waves coming out of the scene. The movement of light inside the scene consists of various events. For instance, scattering, reflection, and refraction. This process is described by the transmission matrix of the scene, which records the contribution of each source point to each sensor pixel. All source contributions at a given pixel are added up to generate the final signal. This translates into multiplying the transmission matrix by a vector of 1s, giving an algebraic expression for the output. In probing, we seek to selectively mask entries of this light transmission matrix to measure certain properties of the scene, as represented by the matrix to the right. We perform this operation at micron scales in small scenes with complicated light transmission. For instance, this method allows us to perform optical matched filtering of light paths for descattering. Knowing an approximate pattern we want to detect inside the scattering medium, it helps us boost the SNR or accurately detect its location despite the blur introduced by scattering. This scene is a toy cup about a centimeter in size. One feature of light transmission in this scene is the specularity that goes around the mid of the cup, which is isolated in the figure in the center. We can choose to keep parts of the specularity that are, for instance, oriented in certain directions or of a given size, as shown in the two videos on the right. To achieve this, we built a modified version of a Michelson interferometer. This allows us to inject light with arbitrarily coded mutual intensity inside the scene and perform the probing operation described above with interferometry. Any desired probing pattern can be implemented as the mutual intensity of the illumination. The properties of the light source required in the interferometer are related to the mutual intensity by a simple Fourier transform. Therefore, given any desired probing pattern, we can implement it on the fly by computing its inverse Fourier transform and using that to program the source's spatial amplitude and phase profiles without needing any hardware changes. Using appropriate modulation, we can implement arbitrary probing effects either on the intensity image or directly on the underlying coherent waves. The most important application of our method is in medical imaging modalities like optical coherence tomography. Our method extends OCT, enabling the rich literature about OCT to be applied to the coherent probing case. Furthermore, our setup can be integrated seamlessly into a commercial OCT system with minimal hardware modifications. In combination with the right inverse scattering algorithms, we hope that this method will be a major contribution towards seeing through scattering. Thank you for listening. Please check out our paper in SIGGRAPH 2020 for more details.
Hello, I'm Chen Bar, and I will introduce my recent work, a Monte Carlo framework for rendering speckle statistics in scattering media. If we shine a laser on a scattering material, light waves will scatter multiple times and produce noise-like speckle patterns. Despite looking like random noise, these patterns have strong statistical properties, such as the memory effect. This means that the speckles shift when we tilt the illumination. While we can go and capture such speckle images with a real laser, the ones shown here are physically accurate simulations produced using a Monte Carlo rendering algorithm we developed in this work. This algorithm can facilitate imaging applications of speckle statistics in several areas, including medicine, security, remote sensing, and astronomy. In particular, statistical correlations, such as the memory effect, is very useful for being able to image through scattering media. In computer graphics, scattering is simulated by efficient Monte Carlo algorithms. However, classical Monte Carlo methods do not consider wave phenomena. As a result, they can only reproduce the smooth intensity of scattered light, which shows no speckles. In this work, we extend Monte Carlo tools to simulate coherent speckle statistics. Let's see how one could simulate speckles before our work. This required specifying the exact geometry and locations of scatterers, then numerically solving the wave equation. These numerical solvers are very accurate, but very slow. We can use this procedure to simulate speckles under two different illumination directions. It produces highly correlated shifted fields. We can visualize this correlation by computing the covariance matrix between all pixels across these two illuminations. The resulting matrix has a strong shifted diagonal component. The shift from the main diagonal is because the two scattered fields are most similar after appropriately shifted. This shift is exactly the memory effect property. Now I'll show you covariance matrices computed by our algorithm and compared to those from the web server. We consider a medium illuminated from two lighting directions and measured for many viewing directions. We show covariance for the case when the two illuminations are both at angle 0, and also when the second illumination is seated at 4 and 13 degrees. The covariance matrices our algorithm computes are identical to those from the web server. In both cases, as the illumination angle decreases, the dominant diagonal shifts due to the memory effect. We note here that computing these matrices using the web server takes several days on a big cluster, while using our algorithm, it only takes a few minutes. Finally, we can use our algorithm to simulate and evaluate imaging techniques, such as an algorithm by Atul for seeing-through scattering. Consider trying to image a fluorescent object when there is a scattering medium, like a tissue layer, between the object and the camera. The image we will capture will be a nose-like speckle pattern. Yet, due to the memory effect, the autocorrelation of the speckle pattern and the autocorrelation of the clear object are the same. This makes it possible to recover the object image. When we use our simulator, we can understand the strengths and the limitations of this algorithm.
This presentation covers our paper, Learning a Probabilistic Strategy for Computational Imaging Sensor Selection, which was published in the International Conference of Computational Photography 2020. In computational imaging, optimal sensing strategy is as important as image reconstruction algorithm, especially when we are severely restricted in the number of measurements we can make. For instance, in the fast MRI problem, where the scanning time is limited, the case-based sampling needs to be carefully optimized. Sensor selection design is also important for astronomical imaging problem, very long baseline interferometry, the technique used for taking the first image of a black hole. The location of telescopes, which controls the measurements in the Fourier domain, significantly influences the image reconstruction accuracy. In the future observations, we would like to add new telescopes to improve the black hole imaging quality. In many linear reconstruction problems, the optimal sensor selection could be analytically solved based on the compressed sensing theory. However, for computational imaging problems with nonlinear forward model or complicated noises, the sensor selection and the reconstruction algorithm highly interact with each other. So here, we propose to tackle the computational imaging sensor selection by a joint optimization of the sensing system and the reconstruction method using an autoencoder-like framework. The sensing system acts as the encoder, and the reconstruction algorithm acts as the decoder. Both the encoder and the decoder are represented by neural networks. However, the encoder's architecture is constrained to ensure it's physically plausible. The proposed encoder consists of two parts. The first part is a physics-based forward model that simulates all the possible measurement of an image. The second part is a trainable block that samples the sensors and therefore selects samples from measurements. Sometimes, many sensor network designs are equally good. So, we represent sensor selection strategy as a probability distribution. The probabilistic sensor selection strategy is modeled as a binary, fully connected Ising model. In Ising model, each sensor has an activity parameter to model its importance, and each pair of sensors has a corresponding correlation parameter. During the autoencoder's training, the Ising model distribution is sampled using a Markov chain Monte Carlo approach, which can be further unrolled as MCMC sampling network. The loss function of this sensing reconstruction autoencoder consists of three terms: similarity between true and reconstructed images, sensor sparsity, and sampling diversity. The sparsity term helps the encoder explore designs with fewer sensors, and the diversity term forces the encoder exploring as many good designs as possible. This general framework should be applicable to many computational imaging sensor selection problems. For different applications, we simply need to replace the decoder and the physics-based forward model in the encoder. Here is an experimental result for very long baseline interferometry new set selection. We consider 12 candidate set locations across the globe. Our approach can easily recover the optimal sampling distributions under different noise assumptions, leading to different array designs. Feel free to check our paper and the project website for more details and experimental results. Thanks for your attention.
We present dehaze glasses, optical dehazing with an occlusion-capable see-through display. Human vision often suffers from haze, small particles floating in the air. These floating particles lead to visual degradation that may hinder humans' correct decisions and actions. In machine vision community, dehazing attracts interest as a preprocessing step to aid high-level visual tasks. We consider re-importing machine visions of haze removal into human vision by presenting a first-person system, to enhance our eyes for further decisions and actions. To integrate dehazing in first-person view, using video see-through HMDs is most straightforward approach. However, this system loses resolution and dynamic range, and more importantly, VST may have a risk of blacking out the user's view under accidental shutdown. On the other hand, using an commodity optical see-through display can enhance brightness and edge for hazy scenes, while retaining the real-world light. However, light from display is always mixed with the background scene, thus loses the contrast of the scene. As a result, dehazing with OST HMDs needs to occlude the incoming lights. To occlude the incoming light, some researchers have proposed that a single spatial light modulators (SLMs), such as LCD and DMD, is installed in front of the eyes. By using such occlusion-capable OST HMD, we propose dehaze glasses, a first-person view optical dehazing system. By adopting a dehazing method for the displays, our system can selectively modulate the light to dehaze the real view. To realize haze removal using an occlusion-capable OST HMD, we first provide an image formulation for each display. Then designed objective function for dehazing by minimizing the differences between target images and reconstructed images via displays. Finally, we obtain occlusion and OST HMD images by two ways. One is basic computation by simply optimizing the objective function. The other one is alleviation method, which tries to reduce the number of completely occluded pixels while keeping the natural perception defined by perceptual metrics, LPIPS. These images show our hardware setup. We combine a DMD-based occlusion mask with a consumer OST HMD. To occlude the incoming light while keeping the see-through view from the eye, we implemented the polarized beam splitter (PBS)-based optical design. We evaluated our system by displaying 80 hazy scenes from reside dataset on a monitor in front of the system and capturing images by an user perspective camera. Quantitative analysis by perceptual metrics suggests that DMD only and full setup can dehaze the scene view to be perceptually the same as the original dehazed view. Moreover, the full setup is more effective in scenes with high saturation. In this work, we propose dehaze glasses, a see-through view dehazing system using an occlusion-capable OST HMD. We provide a computation method and a proof-of-concept OST HMD system that can optically dehaze the first-person view of the user. We conduct quantitative analyses of the system with a user perspective camera, which show that the system achieves perceptually natural haze removal. Thank you for watching.
Hi everyone, I am Varun and I will be presenting our work on lensless reconstruction. Lensless systems greatly miniaturize cameras by avoiding bulky lenses. This leads to promising applications in fields such as medical imaging and surveillance. In recent years, quite a few lensless cameras have been developed. In this work, we shall focus on two of them, flatcam and flatcam with a PH. So how does a lensless camera differ from a lens-based one? In a conventional camera, the lens focuses the scene onto a sensor. This results in a small point spread function and the measurement resembles the scene. In comparison, a lensless camera lacks a focusing element and results in a highly multiplexed measurement, no longer resembling the scene. Hence, we require reconstruction algorithms to recover the scene. Our method FlatNet is able to produce photorealistic reconstructions from highly multiplexed measurements. This video is captured by FlatCam and is reconstructed using a traditional algorithm and flatnet. We observe sharper quality and better temporal stability in our reconstruction. Flatnet is a physics-aware, data-driven framework for scene recovery. It consists of two stages, a trainable inversion stage and a perceptual enhancement stage trained in an end-to-end manner. The trainable inversion restores local structure and is based on the camera forward model. This output is further improved by the perceptual enhancement stage. The trainable inversion is implemented differently for separable and non-separable models. In our previous work, we implemented this as a learnable inversion in spatial domain for separable models. We extend this to non-separable models by using a learnable inversion in Fourier space. In the below figures, the learned parameters are depicted in orange. Observe that the inversion closely matches the forward model in each case. The output of the inversion stage has local structure but tends to be noisy. We use a connet to capture natural image statistics and recover a clean image from this. We use a combination of MSE, perceptual, and adversarial losses for this purpose. We use monitor acquisition to obtain training data for flatnet. We call this display capture. We further test the trained flatnet on real scenes. We call this direct capture. Here are some results on the separable model using flatnet. We observe sharper reconstructions on both display and direct captures from our approach. Here are some results on the non-separable model. We again observe that flatnet gives us better results on both captures. Flatnet can be extended to handle certain practical constraints. To work with smaller sensors, we propose a simple padding scheme to still recover high-quality reconstructions. Real measurements may differ from display capture due to issues like stray light. To tackle this, we collect webcam-flatcam pairs and fine-tune flatnet. In this work, we introduce flatnet, a physics-aware deep learning framework for photorealistic reconstructions from lensless cameras. It exploits both camera models and image statistics. We believe better reconstructions will help lensless cameras go mainstream.
Hello everyone, I am Cheng Qian and I will discuss using learning-based techniques for inverse scattering. Scattering materials are everywhere. A cup of milk, an engagement ring, a foggy highway, or our own skin are all made of scattering materials. Because of the ubiquity of these materials, applications related to scattering are critical in many different fields, such as medicine, AR/VR, and fabrication. Importantly, there is increasing demand for computational techniques that can infer scattering properties in real time, with minimum calibration and at the same time without sacrificing physical accuracy. In this work, we propose a physics-aware learning pipeline that we call inverse transport network. It works by concatenating a neural network and a physics-accurate forward scattering simulator. During training, the network outputs material parameters, which are used by the simulator to synthesize a new image. By requiring that this matches the input image, we force the neural network to act as the inverse of the forward scattering function. To train the network, we need to backpropagate from the reconstructed image back to the neural network weights. This requires computing the derivative of the forward scattering process with respect to the predicted parameters, which we compute by implementing our own volumetric Monte Carlo differentiable renderer. At test time, inference requires only a forward path through the network. Thus, inverse transport networks can predict material parameters efficiently without any geometry and lighting information, and in a physics-aware way, thanks to the integration of forward scattering in the training process. We additionally augment the design of our network to take into account so-called similarity relations, corresponding to ambiguities due to different materials parameters that produce very similar appearance. To this end, we take advantage of the fact that similarity relations are strongly dependent on geometry. Ambiguous materials look the same at thick and smooth surface parts, but they have different appearance near thin geometric features, such as edges. Therefore, we can mitigate similarity relations by training our network to emphasize appearance near geometric edges. We use both simulated and real images to compare our network to simpler baselines. From the error maps, we see that our networks reproduce both ground truth parameters and input appearance much more closely, reducing error by 40 to 50% compared to the baseline. To conclude, we have taken first steps towards enabling computational efficient, uncalibrated inverse scattering through a learning architecture that incorporates forward scattering physics and accounts for similarity relations. Please visit our project website for all the code and data. Thank you for your attention.
This talk introduces a new form of non-line of sight imaging, which we call keyhole imaging. The original work in non-line of sight imaging was motivated by the question, can you see around a corner using an open door? In this work, we instead ask, is it possible to see inside a room using the keyhole of a closed door? The latter problem is significantly more challenging because it can only sample light from a single optical path. To solve this problem, we propose transmitting a collimated laser beam through a door's keyhole. This laser hits a single point on the wall inside the room and scatters in all directions, thereby indirectly illuminating the objects inside the room. This indirect light in turn scatters off of the objects inside the room, and some of that light travels back to the sampling point on the wall, where it scatters and eventually makes its way back, all the way back through the keyhole to the detector. The scanning surface that is accessible in this unique configuration reduces to just a single point, and conventional wisdom says that we shouldn't be able to recover anything at all from such a setup. However, by leveraging a hidden object's motion, we develop an inverse method that estimates the object's shape and trajectory from these transient measurements. And note that if we can solve this problem, which we call keyhole imaging, it's useful not just for seeing through a keyhole, but also for search and rescue, navigation, and other applications where you don't have access to a large relay wall. The key insight underlying our method is that measurements of a moving object captured with a fixed sensor are equivalent to measurements of a fixed object captured with a moving virtual sensor. That is, with some slight abuse of notation, a measurement of a translated version of x is equivalent to a measurement of a fixed x with a translated sensor. This is the same insight that underlies other imaging technologies, like inverse synthetic aperture radar. With this insight in hand, we can turn to experimentally validating keyhole imaging. We set up the following experiment at Stanford. A pulsed laser and time-of-flight detector, in our work a single photon avalanche diode, is aimed through the keyhole of a door in a confocal configuration. The laser illuminates a single fixed point on the wall, and the hidden object, which is covered in retroreflective tape, moves to a series of unknown locations using a 2D translation stage. At each position, the laser transmits a series of pulses, which scatter off the wall, scatter off the object, scatter off the wall again, and are finally detected by the time-of-flight detector. Here's an example of a measurement we recorded with our prototype. When the mannequin is at an unknown location in the hidden space, we record a transient that contains time-resolved photon counts relative to the emission of a laser pulse. Without object motion, the information contained in such a measurement is insufficient to estimate the scene. However, as the hidden object moves, these transient measurements change. In doing so, the transient measurements encode information about the shape and trajectory of the mannequin. We feed these measurements into the expectation maximization algorithm, which forms estimates of the hidden object's shape and trajectory. For more information about expectation maximization, please see our paper. We tested our proposed method on a diverse set of hidden objects. It forms recognizable estimates of each object's shape and excellent estimates of each object's trajectory. With that, I'd like to thank you for your attention. If you're interested in learning more about our project, a preprint is available online.
Welcome to the Spotlight presentation on Modeling Defocus Disparity in Dual Pixel Sensors. I am Abhijit Punnapurath, and this is joint work with Abdullah Abu-Olaim, Mahmoud Afifi, and Michael Brown. Most modern DSLR and smartphone cameras use dual pixel sensors or DP sensors. Unlike in a conventional sensor, where each pixel site has one photodiode, on a DP sensor, each pixel site is split in half using 2 photodiodes. DP sensors can thus provide 2 views of the scene from a single image capture, one view as recorded by the left half dual pixels and another as recorded by the right half dual pixels. DP sensors were originally designed for autofocus. As seen in the animation, a disparity exists between the left and right DP views, and the camera's autofocus system analyzes this local disparity to determine how to move the camera lens in order to bring that region of interest in the scene in focus. A few recent works have demonstrated that the information contained in these 2 DP views can be used to solve other computer vision tasks beyond autofocus. These existing methods typically view the 2 DP views as a stereo pair and use stereo matching algorithms to compute disparity. At any given pixel, the stereo model for disparity can be represented using 2 shifted impulse kernels. However, DP disparity is not caused by view parallax as in stereo, but instead is attributed to defocus blur that occurs in out-of-focus regions in the image. If you consider an ideal DP camera, disparity is induced due to the circle of confusion resulting from an out-of-focus scene point being split across the 2 views, and this defocus disparity is proportional to the blur circle radius. In practice, the DP blur kernels are not perfect half circles. Here, we show the measured PSFs obtained by imaging a calibration pattern using a DP camera. In this work, we propose a parametric form of the DP defocus kernels as shown. The blur circle radius is the only free parameter. We apply our model to the task of depth estimation from DP data. Our model exploits the symmetry of the DP defocus kernels to construct an unsupervised loss function that does not require ground truth depth. Here are some depth estimation results on a Canon DSLR camera. We compare against recent deep learning based monocular depth estimation methods as well as an unsupervised stereo technique. It can be observed that our approach produces more accurate depth maps. Here are some more results captured outdoor or in more unconstrained settings. And finally, we show here some comparisons on data captured using the Google Pixel 4 smartphone. Thank you for visiting our spotlight.
Hi, I'm Yotam and I'll be presenting our work Monster, Awakening the Mono in Stereo. Stereo depth estimation is a widely used passive depth estimation method, but it suffers from a few cardinal issues. Our goal in this research was to use monocular depth map, a depth map from a single image, to improve some of the stereo limitations. 2 of the cardinal issues stereo methods suffer from are inferior accuracy and the very close depth range due to perspective distortions, and the need for an extrinsic calibration. So how can we improve these using mono? Let's start with stereo depth range. The blue line represents the relative stereo estimation accuracy. It can be seen that in ranges up to 1 meter, the accuracy degrades comparing to the ranges of 1 to 10 meters. The orange line represents the monocular accuracy. We understand that fusing the depth maps together can improve the overall result. Here is an example of our fusion result. The fused depth map in the right shows a more accurate depth map from each of the stereo and the mono methods alone. And now for extrinsic calibration. Almost all of the stereo methods assume the input images are rectified and the baseline is measured, that is, the relative position between cameras is known and corrected. In most cases this is achieved by capturing images of a known pattern and estimating the camera's relative positioning accordingly, an expensive and sensitive process. We present a method to perform online self-calibration or rectification with the help of the monocular depth map. This is an example for the output of the same stereo network for left and right images after different rectification methods. It can be seen that our method, to the right, is on par with the kitty calibration in the middle column, done with a checkerboard pattern. In some details, like the left man's hand, our method performed even better. Our system is comprised of 2 cameras that serve as a stereo set and as the source for 2 monocular depth maps. We use the left monocular depth map to extend the stereo depth range, and the right monocular depth map to calibrate the stereo set. In our experiments, we used two monocular methods, an image-based method, that is based on the image alone, and a phase-coded aperture mask method, that requires a special optical element in the lens, which enables estimating absolute depth map. To fuse the depth maps we used either a threshold or a fusion net. The fusion network uses a confidence metric each network outputs, to create a binary fusion mask. Overall, we show an improvement of 10% in relative depth on our generated simulative dataset. For the auto-calibration part, we developed the following method. We start with two non-rectified photos, left and right. We train a differentiable projective transformation, DPT, that learns the transformation needed to rectify the right image. Once the mono-stereo depth maps are consistent, that is, their difference goes to minimum, the DPT is trained and the transformation was found. Full calibration is possible with an absolute depth map, like the phase-coded based method. We measured the difference between the Groundtruth depth map and the result after different methods of calibration. Our method shows the lowest difference. The result can also be seen qualitatively on the example. Our calibration method shows its superiority over other methods on real-world photos as well, like the uncalibrated Kitty dataset. To conclude, we present a novel method to use monocular depth estimation to improve stereo results. We showed how fusion of the depth maps can improve the overall results, and how we can use the monocular depth map as a reference for calibration of the stereo cameras. For further details, see our paper, and please contact us for any question.
We present our work on spatiotemporal coded imaging for motion deblurring. Motion blur limits the exposure time while capturing moving objects. It is vastly researched. In this work, a computational imaging approach for motion deblurring is proposed and demonstrated. We capture a scene containing moving objects using a spatio-temporally coded camera that embeds color motion cues in the intermediate image. This image is then processed using a CNN trained to utilize the embedded color motion cues to deblur the image. The coding is based on a phase mask incorporated in the lens aperture. In previous work in our group, a phase mask is designed to generate focus-dependent color cues in the captured image, enabling both extended depth of field and depth estimation from a single image. The phase mask is composed of several rings, and it is designed to generate a color-dependent PSF for each defocus condition. These color cues enable defocus estimation, which is directly related to depth, and also help restoring the blurred image. In this work, we use a similar phase mask to encode motion cues and enable blind motion deblurring, but with a significant difference: focus variations are introduced during exposure, what leads to motion encoding. In our system, we assume an infinite conjugate imaging setting. If a point source is moving during the exposure, it generates a trace in the acquired image. If we add a focus variation during the exposure, a spatial blur will be added to the trace. However, if we incorporate the color defocus phase mask in the lens and perform a similar focus variation, the resulting motion trace is colored, thus containing cues to both motion direction and extent. To train the motion deblurring CNN, we generated a dataset based on the GoPro dataset released by Na et al. Each image in the sequence is convolved with the instantaneous colored PSF, and then the images are summed up to generate the motion colored image. After training led to encouraging simulation results, we turned to build a setup of our coded camera. We used an imaging lens equipped with a liquid focusing lens, and incorporated our phase mask in its aperture. The liquid lens is synchronized to perform the designed focus variation during exposure. As a first test, we validated the PSF encoding. An image of two rotating white LEDs was captured, and the color-coded PSF pattern can be clearly seen. The blue-green-red transition indicates both motion direction and extent, thus allowing blind shift-dependent motion deblurring. To check the deblurring performance, we performed experiments with a moving object. Our results are compared to an image acquired using a conventional camera in the same setting, and deblurred using the CNN of Na et al. In an additional test, a rotating photo is captured, demonstrating the deblurring performance of motion in all directions and various velocities simultaneously. To conclude, our joint optical digital processing scheme is based on color motion cues embedded in the optical image, which enable shift-dependent motion deblurring, without a limitation on the motion direction. For further details, you are invited to read our paper. Thanks for watching.
Okay, everyone, welcome back. I hope you had a good break. Let's get started again. We have another exciting lineup of talks in this session, and then followed by the second round of spotlight talks. So our first talk is going to be from Gordon Wetzstein. Gordon Wetzstein is an assistant professor of electrical and computer science at Stanford University. He's a leader of the Stanford Computational Imaging Lab and a faculty co-director of the Stanford Center for Image Systems Engineering. So Gordon's group works at the intersection of computer graphics and vision, computational optics, and applied vision science for a lot of different applications in next generation imaging, display, wearable computing, and microscopy systems. Gordon, I don't know if you want to say hi and
Oh, hi, everyone. It's really too bad we can't see each other in person this year, but I just wanted to thank the organizers, Katie, David, and Achuta, for doing really an outstanding job at putting this together last minute in this virtual format. I know it's probably been pretty stressful for you guys, but thanks a lot for making it happen. And yeah, I actually organized the very first and the second CCD workshop back in I don't know when it was, 2012, 2013 or something like that. And it's really great to see that it's still around, 8-9 years later, and that there's such a vibrant community. So I just wanted to thank everybody for dialing in and contributing to just creating a fantastic community that we're all part of, which is great.
Yeah, I'm so excited to see how many people we have calling in. And also thanks again to the speakers, Gordon, for putting together talks at last minute recordings that I know was challenging for the speakers as well. Okay, so with that, I'll share my screen, and then Gordon will be here for questions at the end. So please make sure to put questions in the chat.
Hi, I'm Gordon Wetzstein, an assistant professor of electrical engineering at Stanford University, where I direct the Computational Imaging Lab. What I'd like to do today is show you an overview of some of the recent projects that we've been working on in my lab. Before we dive into that, let me start by giving you a historical example for, innovations in photography. Back in 1878, Leland Stanford had a bet with some of his colleagues on, the question whether there was ever any time where the horse had all 4 feet up in the air. In order to prove his point, he hired the experimental photographer Edward Muybridge to capture photographic evidence, and what you can see on the upper right is that Muybridge was indeed able to capture this photographic evidence. And what he did to do that is he created this experimental imaging system. You can see in the background, these are many cameras mounted next to each other. They're all connected to mechanical shutters that are, again, connected to these tripwires. So as the horse runs across the track, it trips the wires, the shutter falls down, exposes a photograph, and by looking at all the different photographs captured by these cameras at slightly different points in time as the horse runs across the track, you can capture what looks like a high-speed photograph of the horse. So imaging has been part of Stanford's history since the early days, and we continue in Muybridge's tradition and build modern digital photography and imaging systems that use modern electronics and advanced algorithms. Some of the topics we work on include computational cameras, but we actually also work on computational displays, for example, for applications in augmented and virtual reality. Before I dive into these, let me just show you a couple of recent projects that we've been working on for applications in looking around corners or non-line of sight imaging. So here we also built on high-speed imaging systems, just like Muybridge did, but we can make them a lot faster today. Indeed, we can capture light at the speed of light and visualize how light transport operates in free space or in a medium. So here you can see an optical fiber. The optical fiber is kind of wound around in a circle to extend the path length. And what we did here is we take a picosecond pulse laser, connected that to the fiber on one end. And what you'll see is that as you shoot a laser pulse into this fiber, here shown as a transient image, we can actually visualize how this laser pulse propagates through the fiber, because at any point in the fiber, a few photons will actually scatter out of the fiber, and the camera can capture this. But it's only able to capture these dynamic nature of light if it actually operates at picosecond accuracy and it can timestamp the photons that reach the camera, which is exactly what we did. So here, again, we use a picosecond laser that, shoots short pulses of light into the scene at million times per second. These light pulses will sometimes be directly reflected to the detector. Sometimes the light bounces around in the scene before it reaches the detector. So this is the indirectly reflected light. We built on modern single photon sensitive detectors that are known as SPADs. And these SPADs can not only detect one photon of the returning pulse, including the directly and indirectly reflected light, but they can also timestamp it with picosecond accuracy using a time-to-digital converter. So this SPAD is able to timestamp a single photon event out of this entire pulse that returns to it. And by repeating the experiment many times, and maybe using an array of these detectors, we can build up histograms with each of them by repeating the experiment. And these histograms look very similar to the shape of the returning light. Building on this new and emerging sensor technology, we can then develop advanced algorithms to process this to enable new imaging capabilities that I'll show you in a second. So where is this useful? Well, pretty much all LiDAR and 3D imaging systems that you see out there use this principle of operation, this time-of-flight imaging, where you shoot a laser pulse into a scene, you measure how long it takes for the light to return to the detector, and that tells you how far away a point is. And then you can scan that over the scene to get a 3D image or a point cloud. So this is what makes autonomous cars drive and see the world around them in 3D, but they kind of fail if they can't see an object. For example, if it's occluded by some type of a light-blocking occluder. Well, we can build advanced computational imaging methods that can overcome this shortcoming and actually see around corners. So let me give you an intuition of how that works. We use the same pulse laser and time-resolved detector to shoot laser pulses into the scene. Some of the light that goes into the scene will be directly reflected, and some of the light will be indirectly reflected because it bounced off of the visible surface into the hidden part of the scene, back into the visible part, and then to the detector. So we don't know exactly what the shape is of this indirectly reflected light or the geometry of that scene, but we know that the time of flight of the directly reflected light, for example, in this case was 2.7 nanoseconds, which corresponds to a time of flight of about 40 centimeters. Looking at the time of flight of the other indirectly reflected light, we know that there's something behind the corner at a distance of about 24 centimeters, based again on this time of flight, but we don't know where it came from because all the light or all the objects on this arc would have resulted in the same time of flight. So we need to build inverse methods and advanced algorithms to disentangle these representations. And indeed what we do is we scan the indirect light transport on multiple different points on the wall over this imaging area that you can see here, and we digitally remove the directly reflected light because it doesn't tell us anything about the object that's hidden behind the scene. And then we get measurements that kind of look like the 3D cube on the upper left, which includes the time-resolved indirect light transport of the scene, in this case of the bunny. Here's an example of experimentally measured data that we published in our Nature 2018 work. And what you can see here is that this time-resolved light is captured. It doesn't really look like the 3D objects at all. And then using advanced algorithms like our light cone transform, we can turn these measurements into a 3D representation of the scene. And indeed, we can do so very efficiently and in real time. So these were some of the earlier results. Here's an updated version of our imaging system. On the left-hand side, you can see a hidden scene containing a statue, a plant, and a table. There's an occluder and our imaging system on a little card. On the right, you can see that the imaging system really just scans the wall. It doesn't actually see the hidden scene at all. Here we cheated a little bit and took a camera and put it behind the occluder. So what you can see here is these indirect reflections from the wall towards the statue, the plant, and the table. And these indirectly reflected photons are exactly what we're looking for because these carry all the information for us to be able to recover the 3D shape of the scene. The measurements here look kind of like this. You can again see these ripples, look like ripples on a pond when you throw a rock in them, but this is really just a time-resolved indirect light transport of the scene. You can also see the wall, and that is because we captured these data in indirect sunlight. So some of the ambient photons come in, don't really carry in information, and they actually corrupt our measurements. Nevertheless, our algorithms are very robust to ambient light and other artifacts, and they're able to estimate the 3D shape of the scene, seen here on the right, at a pretty high fidelity. So it's really possible to build an imaging system that can see around a corner today. So how do we do this? Well, in this particular case, we work with the time-dependent wave equation that you can see here, and what we realized is that this non-line of sight problem is actually a boundary value problem, where we measure one boundary value, one boundary condition, and we want to estimate the other boundary condition. So specifically, we measure the time-dependent light transport on the wall, x, y, but we lost the information over z. So z equals 0 is just the plane on the wall where we take our measurements. And what we want is the time-independent light transport of the hidden scene in x, y, and z. So this basically models the hidden scene as a set of point emitters that all emit a spherical point at time equals 0. And we have been developing fast range migration techniques to migrate with this one boundary condition to the other boundary condition for this 3D shape estimation. So here's another example where we take measurements of a full room-sized scene that contains a statue, a glossy dragon, a bookshelf with multiple different objects. And what's interesting here is that all these objects have different reflectance functions. For example, the statue is diffuse, the dragon is glossy, and the disco ball is highly specular and is composed of these little facets, of these little planar facets. So this is our hidden scene. Again, we measure x, y on a visible wall, not directly the scene, but we take these indirect measurements. They look kind of like this. I can play them back in time again. You can see these little dots in these measurements. These dots are actually the light reflected off of the disco ball in the hidden scene and reflected back towards the visible wall. So when we play this back in time, again, this measured data looks really incredible. We can see these ripples on the pond. This is the time-resolved indirect light transport of diffuse objects, but then we can see also these points that are basically the facets of the light reflected off of the mirror arriving at the wall at different points in time. So in our 2019 SIGGRAPH paper, we developed this range migration technique that's known as FK migration to then take this data and directly estimate the 3D shape of the scene. And the unique part here is that this method is really robust to all these different reflectance properties of the hidden scene. When Ramesh Raskar at MIT invented the idea of looking around corners back in 2012, what he had in mind was that you had a person inside a room and you had a camera outside the room, and the camera would take a picture of the door as it's open and basically see around the corner. So in some of our latest work, we take this idea one step further and ask whether you can see inside a room with the door closed. Now that seems pretty crazy, but it may actually be feasible under certain assumptions. So in this case, we again take a camera that's outside the room, and we only have access to a single optical path. So light that propagates through the keyhole and hits the rear wall of this room. And it directly reflects off of this wall. Some of the light scatters into the room. It scatters off of the person, back to the wall, and then some of the photons will actually come out the same optical path as they went in. And so we call this problem keyhole imaging, and it's significantly more difficult than non-line of sight imaging simply because you can't scan on the rear wall. You can only have access to a single optical path. Now, this seems impossible unless there's some kind of motion of the object in the room. And now the problem is to simultaneously estimate the motion of the object together with its shape. So it seems kind of crazy, but it may actually work, at least to some extent. So here's a physical object, this mannequin, and some measurements that we took for the mannequin. Again, when it's not moving, we just get a 1D histogram that shows how many photons arrived at what time relative to the emission of the laser pulse. And you know, that's too little data to really recover the shape of the object. But as soon as we move the object along an unknown trajectory, we get some diversity in these measurements. And you can see that the shape of these histograms actually changes. Now the thing is, like, again, we don't know where the object actually moved or how it looks. So we've been developing algorithms using expectation maximization to simultaneously estimate the 2D shape of the object and its motion trajectory, which you can see on the right. The motion trajectory is recovered very well, and it's surprising that we actually get a shape that resembles the mannequin, despite the highly ill-posedness of this inverse method. Here you can see a couple of other results of characters. Again, we use physical measurements to estimate the 2D shape of these objects, where you can clearly see the shape of the characters. You can make them out. And the motion trajectories are estimated simultaneously, and they all look pretty decent for such a challenging problem. Okay, let me introduce you to another topic that we're working on in the lab, and I call it deep optics. It's based on modern machine learning techniques that are used in image processing and computer vision. Typically, we learn an algorithm, represented here by this neural network. We have some training data, we send it through our algorithm, we calculate a loss function and backpropagate the error into the parameters of the network. So this is what pretty much everybody does in computer vision, and that drives modern imaging systems. Now we take this idea one step further to jointly optimize the physical parameters of the camera and the reconstruction algorithms, end to end. So this may be useful to optimize imaging systems for specific tasks. So for example, if the camera's only task in life is to classify cats, then maybe there is a better lens or better sensor or better low-level electronics that can help optimize the performance of this camera for this specific task, or that alternatively make it thinner, smaller, lighter, more power efficient, and so on. So there are many different benefits of this end-to-end optimization approach. Now, you can interpret this in multiple different ways. I typically like to think about it as a physical layer and a digital layer that we can train end-to-end in simulation. So that requires us to have a differentiable simulator of the physical layer. Once we've trained this physical layer, we can fabricate it, for example, by fabricating a custom lens that we may have optimized, or to change the sensor electronics. And during inference, the physical layer stays fixed and the digital layer does most of the work. So now, again, you can interpret this as an optical encoder, electronic decoder system, where the optics, encodes the information on the sensor and the electronics decodes it. Or you can think about it as a hybrid optical electronic neural network, where some of the computation is already done in the physics, in the physical layer for you, and the digital layer doesn't have to do that anymore. So this may be useful for saving power or improving the latency of your imaging system. We've looked into this topic for multiple different problems. Here I'm just going to highlight one where we optimized a thin diffractive optical element that you can see here. It looks kind of crazy, but this optical element is optimized by a machine learning algorithm. You can drop it into the aperture of a camera, and this camera will then do the following. It will take an input image that comes in from the left, and it will optically copy this image into, in this case, 16 copies of the image. Each one is blurred or convolved by a different convolution kernel in optics at the speed of light, basically. And what that does is it implements a single layer of a convolutional neural network in optics. We have an additional fully connected layer in the digital layer that then does the classification. And what that allows you to do is you can get twice the classification accuracy for the same power budget, which is really important for edge devices, for example, your camera on a drone, or you can reduce the power consumption by a factor of 2 for the same classification accuracy as a fully digital system. So this idea of deep optics really opens up a lot of different applications. The last topic I want to briefly discuss today is that of computational displays for applications in AR and VR, and also for wearable computing systems. So when Charles Wetzstein invented the stereoscopic viewing apparatus that you can see here in 1838, he had no idea that more than 150 years later, this is really a hot topic in engineering and one of the National Academy of Engineering's grand challenges of the 21st century. So enhancing virtual reality systems is important, and current systems that are available on the market actually operate in a very similar way to Charles Wheatstone's original systems. You have a microdisplay in your head-mounted display that you can see here. That's, for example, a phone screen, and you observe it through lenses that very much act like a magnifying glass. So what you actually see is a magnified virtual image that appears at a fixed distance away from the user. You can predict exactly where that fixed distance is using the Gaussian thin lens formula, and that depends on the physical distance between the microdisplay and the lens and the focal power of the lens itself. Now, this is not a natural viewing condition because each eye basically is looking at a plane floating in space in front of it. And this fixed focus design is different from the real world because in the real world we have 3D objects at all different distances from the user, and the user can focus their eyes or accommodate them at multiple different distances. If you don't support these focus cues in VR, that can lead to nausea, eye strain, and has many different problems associated with this divergence accommodation conflict. In our lab, we've been working on many different technologies to address this, including varifocal displays, near-eye light field displays, and accommodation invariant displays. I don't have enough time to really dive into the details of all of them, but I just want to highlight, one of the simplest and most practical approaches to solving this using varifocal displays. So a varifocal display is one that has a dynamic focal plane, and there are multiple ways of achieving this. One way is to actuate the microdisplay inside the head mount that you can see here. With a few millimeters of optical actuation, you can actually change the magnified image distance by a very large range, over the entire range that you want. Now, this assumes that you have access to eye tracking. So if I know what point the user is looking at and how far away that is, I'm just going to move the virtual image distance to that distance. We verified that this really achieves natural viewing conditions with an early prototype back in 2016, where we hacked a Samsung Gear VR with a motor and eye trackers, and we can dynamically drive the focal plane at the same rate at which the human visual system changes its accommodation, which is pretty slow, but 300 to 500 milliseconds for a change in accommodation over a pretty large range. We've also built benchtop setups that use reference machines or instruments like this autorefractor that you can see here to verify with many user studies that users using this varifocal mode can naturally accommodate at multiple different distances. It's really reassuring to see that some of this technology has in the meantime migrated into prototypes that, for example, Facebook's working on. So over the last few years, they've been announcing their half-dome prototype that actually uses this mechanical actuation mechanism I described earlier. And that's something that we'll probably see in upcoming products. So it's great to see this transition from research efforts into actual products slowly happening in the commercial world. Now, what I mentioned is that, these varifocal or other types of focus supporting near-eye displays can really give people with normal vision a much better experience in VR or AR. And much of that is driven by this idea that, when the eye is healthy and the lens inside the eye can deform to bring objects at near distances and far distances in focus, we just need to be able to present the optical stimulus to the user at these distances. And we can do that, for example, using these varifocal techniques. Now, one thing to note is that, what if you don't have normal vision? Many of us are wearing glasses, and the conditions that are most important here are nearsightedness and farsightedness. Well, these can be easily corrected using fixed focal lenses, for example, the ones that I'm wearing right now. So they just shift the accommodation range back into the normal range. And that's no problem. However, there's a condition known as presbyopia that hits all of us at a certain age, for example, after about 45 to 50 years of age. The problem here is that the lens inside of our eyes gets stiffer with age, and they at some stage can't deform anymore. And what that means is that we have a very limited accommodation range, and we can only see objects in the real world at one fixed distance in clear focus. So just to illustrate what that may look like, here's a scene that contains a book that's very close by, and another office scene that's farther away. So with normal vision, you can accommodate your eyes at all these distances, and you don't even notice how the autofocus mechanism of your eyes will dynamically adjust the focus of your eyes. A presbyope, on the other hand, may be able to see the far distance correctly, but they can't read at all. So because their eyes cannot accommodate or change the focal power to match this distance. Now, there are many existing prescription techniques that allow you to fix this. One of the most common ones include reading glasses. So you can buy inexpensive reading glasses in the store, you put them on, and now you can read. But the problem is that you've just shifted your focal plane forward. You can read, but you can't see the distance anymore. And that's a problem. So you need to put your reading glasses on and off if you want to look at different objects. There are progressive glasses that have a varying focal power over the lens itself, and that means if you look through the top part of your lens, you can see far well. If you look through the bottom part of your lens, you can see near well. The challenge with progressive glasses, however, is that they first of all distort the real world, and second, the field of vision, the part of the scene that you see at any given distance and focus, is severely reduced compared to the entire visual field that you once enjoyed. So progressive glasses are far from ideal. The natural solution is actually to just look at an object and that object coming into focus, which you can kind of see here. So we would like to have a technology that allows us to just look at an object and then do the refocusing for us. So this is something we've been exploring in our lab for the last few years, and we call this technology autofocals. It looks very much like a head-mounted display. This is one of our really early prototypes, which we've in the meantime miniaturized also. So this autofocals system includes stereoscopic eye trackers. This early system also included a depth camera that can image the 3D world in front of it. There's a focus tunable lens that can dynamically adjust its focal power. This lens has some aberrations that we need to correct with the second element. And then there's an offset lens holder that allows us to correct for nearsightedness and farsightedness or astigmatism that can be corrected for with fixed focus lenses. Now, the idea is that we just read the eye tracker, estimate the relative angle between your eyes that tells us how far away the object is that you're looking at, and then we adjust the focal power of the lenses to bring that object into focus, which you can see here. We have done a lot of user studies using this technology, and with these user studies, we've demonstrated that this technology is a lot better than existing prescription glasses by improving the visual acuity of the user over multiple different distances, and by improving task performance compared to other prescription glasses. So this is a really effective technology that's really exciting to think about in the near future. As I mentioned before, we're working on a couple of other techniques and areas like neural rendering, computational displays, and other things. So with this, I'd like to thank you for your attention. I'd like to thank my group for doing a lot of the hard work. And again, please visit our website if you'd like to know more about our latest projects and ideas. Thank you so much.
Thank you, Gordon, for the excellent overview of all this kind of different work that's going on in your lab. I'm very impressed at all the different topics that are being worked on. So I guess so anyone who has questions, please put your questions in the comments box. But I guess I'll get started. So I had a question related to the optimized camera work, the deep optics that you were talking about. So I remember as Michal Irani had said earlier today, and as with my experience with neural networks and stuff, they work well at finding local minima. And it's I think the story that a lot of people tell is that they have lots of very good local minima. So I was wondering, when you run them, do the answers change a lot depending on your initialization, or do you see this kind of effect?
Oh yeah, that's a really excellent question. And just to help you understand how ill-posed the problem is actually, so if you want to, for example, optimize an optical element that goes into the aperture of the camera, you have a forward simulator that simulates the point spread function given the optical element. And even the same point spread function could have many different optical shapes of the optical element that creates the same point spread function. So there is really no solution to that. Yeah. Okay. So once you have the point spread function, you still have to take your data set of images, send it through it, convolve it with the point spread function, and then you have another deconvolution problem on top of that. And deconvolution problems, as you know, are also not really well posed. So, there's a set of infinitely many solutions that really depend on, your optimizer, your learning rate, many different parameters, and there's really no guarantee to converge to like a unique or global solution. It's true that this is a highly ill-posed and nonlinear problem, and it's hard to know when you're at a local minimum or a good local minimum, I guess.
Yeah. No, that's interesting. But I guess it allows us to maybe in the future, or maybe you've done this already, so how to optimize these parameters to reduce things like cost or something like that as well.
Yeah, so this was, the project I showed was just like one example where we try to save power. And we that was this interpretation of, building a hybrid optical electronic computing system. But there are many different other examples, and other groups have picked up this idea too, including yours, I believe. You can, it's just an idea that applies to so many different aspects, and you could change the exposure times, the autofocus, the per pixel exposures of cameras for video compressive sensing. You could really change any hardware parameter you want. And think about not just your camera that has like 5-6 different knobs, but think about a scientific imaging systems that's used in astronomy or other systems where you have millions of different parameters and knobs that you can tweak. So this end-to-end design can really be helpful in automatically finding a good configuration of literally millions of different hyperparameters of the physical hardware.
Very cool. So I guess I have one other question. So for the keyhole imaging stuff, which is really cool, I was wondering, were there any assumptions that are made on the type of motion, or is it something like horizontal motion because you assume someone's moving around in a room, or were there any assumptions that you had to use for that?
Yeah, that's also an excellent question. There were many assumptions in there. First of all, we only recover a 2D shape of the object, so we're kind of restricting it to lie on a plane. And then the motion is actually in X and Z, so that means, it corresponds to an object moving away from the wall and laterally. But if you think about it, there's a duality between the single sampling point and the object motion, or a fixed object and varying the sampling point. And typical non-line of sight images basically sample over X and Y, a static image. But if you reinterpret this keyhole imaging problem, it's the same as having a fixed object sampling in X and Z. So it's a really degenerate problem that is pretty tough. And so any, better priors on the scenes could probably make this a lot better than what we have right now.
Okay, still incredibly impressive that you're able to get that from that
Sure.
one scene point. All right. Well, I think that anyone who has questions, put them in the chat, and we'll pass them on to Gordon later as well. So with that, I think we'll move on to our next speaker. Our next speaker is Atul Ingle. Are you here?
Yep, I'm here.
Okay, great. Let me just make sure I have your stuff queued up. Okay. Yeah, okay. So Atul is a postdoc research associate at the University of Wisconsin-Madison, and prior to joining the Computational Optics Lab at Wisconsin, he was a research scientist at Fitbit in Boston, and his research interests include statistical signal processing and optimization and its application to inverse problems, particularly in medical image reconstruction. And today he's going to be talking about computational imaging with single photon cameras. So do you want to say hi, Atul?
Yeah, I just wanted to say I'm kind of relatively new to this field. This is my second CCD workshop, and I had a lot of fun last year, and I'm hoping we'll be able to meet again in person next year. And just echoing what the previous speaker said, I really want to thank you, David and Achuta, for putting this together. I know it must have been a lot of work.
Well, thank you so much for agreeing to be a speaker. We're excited that you could join us.
Yeah.
Okay, so again, put your questions in the comments, and I'll share my screen now.
Hello, everyone. My name is Atul. I am a postdoc at the University of Wisconsin in Madison. Before I begin my talk, I would like to congratulate the organizers for putting together a great workshop program despite the challenging circumstances. And thank you for inviting me to present some of my recent work here. My topic for today is computational imaging with single photon cameras. There are many real-world applications where we need to capture images in photon-starved scenarios. Here's a classical computer vision application of detecting faces in an image. These photos were taken in a dark environment. You can see that if there is not enough light reaching the camera, it is difficult for an off-the-shelf face detection algorithm to find all the faces. On the other hand, if there was enough light, the algorithm detects almost all the faces successfully. Face detection is just one example. Here are a few more examples. A conventional camera cannot reliably operate in such photon-starved scenarios. If the camera does not get enough light, it can hardly make an image, let alone perform any high-level computer vision task. Fortunately, there is an emerging class of extremely sensitive sensors called single photon sensors. One way to think about a camera pixel is as a bucket that collects photons. The bucket needs to collect hundreds to thousands of photons to reliably create an image. In contrast, a single photon pixel can be thought of as a very small bucket, almost a teaspoon. It collects only one photon at a time. This makes them extremely sensitive. In addition to their extreme sensitivity, single photon cameras can operate at room temperatures. They don't require any special operating conditions. Perhaps more importantly, there are single photon detectors that can be manufactured with CMOS fabrication technology. That is the same technology used in almost all cameras today, from cell phones to machine vision to 3D cameras. This means it should be possible to manufacture single photon cameras at scale and at low costs. But for any real-world computer vision application, a camera needs to work not just in the dark, but in all light conditions. But a problem arises when we operate single photon cameras in bright conditions. Remember that a single photon sensor fills up after capturing just one photon. This means that in normal to bright conditions, most of these photons will be missed. It seems that all this information carried by these photons will be lost. Does this mean that single photon cameras are limited to only niche low light applications? Or can these cameras be used in a broader range of conditions, in particular for bright scenes? For the first half of my talk, I will try to answer this question in the context of 3D imaging. It turns out that in addition to being sensitive to individual photons, single photon sensors can also record the time of arrival of each photon with very high resolution. This makes them a natural candidate for 3D imaging using the time of flight principle. A typical time of flight camera has a laser light source which sends out a short pulse of light. This pulse travels towards the scene and comes back. There is a stopwatch that measures the total time of travel. The camera then estimates the scene depth using this round-trip time of flight and the speed of light. The precision of this depth estimate clearly depends on the timing precision, which is very high for single photon cameras. This simple time of flight principle is the workhorse of many commercially available 3D cameras. Now, it would have been nice if we could simply replace the conventional image sensor in one of these devices with a single photon sensor. However, a single photon sensor has a very different image formation model, so we cannot simply replace it. Let's see how it works. Suppose that the scene is illuminated only by the 3D camera's laser source. There is no other light source, so for example, there is no sunlight. Since the laser source emits a short pulse, the light received by the sensor is simply a time-shifted version of this pulse. From the perspective of the sensor, the waveform looks like a stream of photons. Remember that the sensor can only detect one photon at a time. so it will only detect the first arriving photon. This is an important property and we'll keep using it. Now only one photon may be noisy, so we repeat these measurements over multiple pulses. Each time we capture only the first returning photon. We then make a timing histogram which will resemble the shape of the incident waveform, and by locating the peak of this histogram, we can easily estimate the time of flight. Now, because these sensors are so precise, just a few photons are enough to give the exact scene depth. In summary, a single photon sensor can recover 3D images very accurately in the dark. So now let's see what happens when there is sunlight in the scene. The light received by the sensor will still contain a peak, but now it also has a constant component due to sunlight. In addition to the source photons, there are many more sunlight photons that appear in the photon streams. This causes a problem because with high probability, the early arriving photon will be an ambient light photon. And because we only capture the first returning photon, this means that we will hardly ever detect the true source photons. This causes a distortion in the captured histogram. The true peak gets buried in the noise and is extremely hard to locate. The stronger the sunlight, the stronger this distortion, and the harder it is to locate this peak. Here's an example simulated result. The single photon camera can recover exquisite 3D details under no sunlight as seen on the left, but even with moderate level of sunlight, we see large depth errors as shown on the right. Note that this distortion cannot be overcome by simply increasing the laser power. This is because later arriving source photons will still be masked by early arriving sunlight photons. The current method to deal with sunlight is to block the light arriving at the sensor using an absorption filter. By blocking the sunlight photons, we are giving the source photons a better chance of being detected. But now the problem is that this same filter will also block the source photons. Therefore, although the histogram is no longer distorted, the signal to noise ratio is very low, and we still cannot locate the peak. So far, we have looked at two modes of operating a single photon camera for 3D imaging. On the one extreme, if we don't use any absorption filter, we get a highly distorted histogram. And on the other extreme, if we use a strong absorption filter, we suffer from low SNR. Our key observation is that these are just two extremes of a whole design space defined by the amount of light blocked at the sensor. It turns out that the optimal filtering amount actually lies somewhere in the middle. The intuition here is that the optimal filter blocks just enough light to eliminate most of the distortion while still keeping the SNR high enough so that the peak can still be located. In fact, we were able to derive an analytical expression for the optimal filter strength. Observe that this filter strength is directly proportional to the amount of ambient flux, which can be easily estimated in practice. Also note that the source power does not appear anywhere in this expression. This is because we are operating in the high ambient flux regime, where the number of sunlight photons far exceeds the number of source laser photons. Here's a simulation result comparing our optimal filtering method against existing methods. Optimal filtering achieves up to an order of magnitude improvement in reconstruction accuracy over existing methods with the same total capture time and the same source power. Now, the idea of blocking light does work in practice, but it seems a little wasteful. So one might wonder, can we do better? can we perform 3D imaging in ambient light without blocking too much light arriving at the sensor? It turns out that the answer is yes. Let's see how. Our key observation is that the probability of a photon getting detected depends on how far it is from the start. In particular, assuming the ambient photons arrive according to a Poisson process, the probability of photon detection decays exponentially with time. Conventionally, the sensor is turned on immediately after the laser pulse is transmitted. Therefore, the probability of detecting the photons at the true signal peak is very low. So what if we place the sensor start time just before the true laser peak? This will give the source photons a better chance of being detected. But the problem is that we don't know the location of this true peak. In fact, this is exactly what we are trying to estimate in the first place. This is a bit of a chicken and egg problem. So what are we going to do? Our main idea is that we are going to hedge our bets by having different sensor start times for different laser pulses. Since we have no prior information about the true depth, we will distribute the sensor times uniformly over the entire depth range. This way we can improve the chances of capturing those source photons in at least some of the pulses. By summing these measurements over many pulses, we get a histogram that looks like this. As we increase the number of shifts, the histogram starts resembling the shape of the true waveform, free from sunlight distortion. This is the key idea of asynchronous acquisition. Asynchronous acquisition averages out the effect of sunlight distortion and reliably recovers the true source peak. Compare this with the conventional acquisition scheme, where the peak is buried in the noise. Now, one way to achieve asynchrony in practice is to artificially delay the sensor start times with respect to the laser cycles. However, in practice, this is wasteful. A better way of achieving asynchrony is to let the photon detection times themselves determine the sequence of shifts. We call this photon-driven acquisition. The key idea here is that because the photons arrive randomly, it forces the sensor start times to shift randomly, and in the limit, we automatically achieve uniformly shifted start times for the sensor. We now show some experimental results. We imaged various scenes using our single pixel raster scanning hardware prototype. The first experiment shows a scene with a large dynamic range of albedos. This is a challenging scene because there is an order of magnitude difference in albedos between the darkest and the brightest pixels in this scene. With a conventional technique, we can either recover the dark object or the bright object, but not both of them simultaneously. With photon-driven acquisition, we can automatically adapt to the wide range of albedos and recover both simultaneously. In our second experiment, we imaged a white porcelain flower vase under very bright illumination, almost like sunlight, of over 20,000 lux. Our photon-driven acquisition method provides almost an order of magnitude improvement in depth reconstruction accuracy. This shows that we can perform single photon 3D imaging outdoors, even in the presence of strong sunlight. So far, we have looked at using single photon sensors in active 3D imaging applications where the camera has a laser source. However, in many practical imaging applications, the camera is completely passive. It does not have any active light source. So the next question I will try to answer is, can single photon cameras provide any advantages in such passive imaging applications? Now there are many single photon detection technologies out there, but for the rest of this talk, I will focus on single photon avalanche diodes, The reason we are interested in single photon avalanche diodes or SPADs is their ability to count individual photons with very high timing resolution. Let's look at a SPAD-based 3D camera again. And suppose that we remove the active light source, so there is no pulsed laser. And the SPAD runs completely passively, collecting ambient photons returning from the scene. Also assume that we have no synchronization source. So the SPAD is running in a free running mode. We call this imaging modality passive free running SPAD or PF SPAD. Because we don't have any synchronized light source, we can no longer capture any 3D information about the scene. So the question arises, what information can this PF SPAD provide about the scene that a conventional camera sensor cannot? Let's look at a single PF SPAD pixel collecting photons over a fixed exposure time, just like a conventional camera pixel. Note that there are two photon timelines here. The timeline on the top is the incident photon timeline, where the photons arrive according to a Poisson process, and the bottom timeline is the photon detection timeline. Now a SPAD can detect individual photons, but after each detection, it goes dead or blind for a fixed period of time called the dead time. During this dead time, it cannot capture any photons, and after the dead time ends, it is ready to capture the next available photon. So now let's look at the effect of dead time on the response curve of a SPAD pixel. By response curve, I mean a plot of the number of detected photons as a function of incident flux. At low flux levels, this response curve grows approximately linearly as a function of flux. As the photon flux increases, this response curve starts flattening out. This is because the SPAD pixel starts missing a larger fraction of the incident photons due to its dead time. Eventually, at very high incident flux levels, the response curve flattens out. The shape of this curve has two key properties. First, notice that it approaches an asymptotic saturation limit, but it never really gets there. So in theory, it never saturates. Compare this with a conventional sensor which suffers from a hard saturation limit due to its full well capacity. The second key property of the response curve is that it is invertible, with this nice closed form expression to estimate flux from the number of photons. The response curve looks a lot like a tone mapping curve used in high dynamic range imaging. It gives you dynamic range compression for free. If we plot the SNR as a function of flux, we observe that a PF SPAD can continue to measure extremely high flux values, albeit with reduced SNR. The ability of SPADs to operate at low flux levels is already well known. Our method combines this with the ability to operate at high flux levels to provide extremely high dynamic range, orders of magnitude higher than conventional sensors. We now show some experimental results using our single pixel PF SPAD hardware prototype. Our hardware prototype has a single SPAD sensor. Since we don't have an array of pixels, we raster scan the image plane of a variable focal length lens to make an image. Here we test an indoor tabletop scene with a bright Edison bulb casting a dark shadow on an alarm clock. There is 1,000,000 to 1 dynamic range here between the bright filament and the dark shadow. Our PF SPAD prototype captures both the bright filament and the numbers on the clock in a single exposure. Compare that to a conventional sensor with a long exposure. The digits on the alarm clock are visible, but the bulb filament is saturated. With a shorter exposure time, the conventional sensor captures the bulb filament, but the numbers on the alarm clock are too noisy to be legible in the zoomed in set. Here's another tabletop scene with 4 bulbs at different brightness levels. Once again, the conventional camera needs at least 2 exposures to capture this dynamic range, which the PF SPAD camera can capture in a single exposure. Single photon cameras are quickly becoming mainstream. In fact, some of these are even commercially available now. This presents an opportunity for our community to develop new vision algorithms to leverage the unique and exciting capabilities of these cameras. Our work takes some initial steps towards expanding the scope of these cameras beyond the niche applications where they are currently being used. Our work can enable using these cameras for a much broader range of extreme vision applications. Thank you for your attention.
Thank you, Atul, for the really nice talk. So again, please put your questions in the comments. I'll get started with one. So I guess I was curious with the one where you have the different start times, and that allows you to find the peak. Could you imagine doing this with a reconstruction algorithm simultaneously where you would have some sort of estimate of the current depth and use that to choose the next kind of start time more smartly? Or is that something, does that make sense, or does that not something that would help at all?
No, that absolutely makes sense. We started with the assumption where we know nothing about the true depth. But of course, in practice, you could probably do better if you start with a coarse estimate first. And then once you kind of know where the true depth is for a given scene point, you could more finely sample, meaning you could just sample in a shorter window of shifts instead of just going from scanning the entire depth range. Yeah, that makes sense.
And is dead time also a problem for that? Was that a SPAD as well? I wasn't.
Yeah,
sure.
that was also a SPAD. So in the photon-driven acquisition method, the way it works is just a free-running SPAD. So each time you capture a photon, you just stay off for the minimum amount of time required to reset your detector, and then you're ready to capture the next photon again. So yeah, there is still a dead time. And what that dead time does is, because it depends on when the previous photons were captured, and these photons are coming randomly, given a long enough exposure, you automatically achieve uniformly distributed shifts in the entire depth range.
Okay, so that makes sense to me. Okay, cool. And then another thing I had related to the dead times. So you were saying that when you use the photon SPAD response curve, it's never saturating. But I was wondering, if you have a photon that comes in right after the dead time, eventually it would saturate, right? Or am I just, is that not an issue?
So because photons don't arrive deterministically, even if you push the photon flux to a very high number, in theory, you will still have small gaps between when the previous dead time ends and when the next photon arrives. So in theory, the flux will have to be infinitely high to get this periodic thing where you get one photon precisely at every dead time.
I see.
But of course,
add some like infinite resolution, temporal resolution.
Exactly. So I was about to say, in practice, this is not true, because you have some quantization noise in SPADs also, because you don't have infinite time resolution.
Okay, that helps me understand a lot. And then I'm going to also say a question that actually I was a little confused about too, so it might just be good to have it for the video recording on what is the absorption filter you're using for the first work you talked about. Is it is it a color filter? Is it just a neural density filter? Or can you explain that?
Yeah. So for that part of the work, the absorption filter that we were referring to is just a neutral density filter. So we assume that we already have a color filter or a line filter to select for the wavelength of the laser light. But in practice, what we find is, even with that line filter, you still get ambient light leaking in, because something like sunlight is pretty broadband. So you still need a pretty strong neutral density filter that just is broadband, and it reduces the overall photon flux that's arriving on the sensor.
Okay.
So the absorption filter there is a neutral density filter for that part of the talk.
Okay. Well, thank you very much again. I think any other questions maybe we can answer in the comments box. But thanks again. And so we'll move on to the last part of this session, which is the final set of spotlight talks. And again, these spotlight talks are 3.5-minute talks on a variety of different work. You can put questions, you can ask questions to the authors of the work by either asking them in the Zoom chat, preferably by asking them in a private message so we can keep track, so it's easier to keep track of all the questions. Or if you are registered for CVPR, doing them on the CVPR internal website. There's also a question answer box there that the author should be monitoring as well. So, okay, I'll get started with the spotlights.
In this paper, we designed and built a novel virtual reality display that provides unprecedented immersion. Our proposed display improves upon multifocal displays in terms of the ability to generate occlusion cues. Multifocal displays generate virtual scenes by showing multiple focal planes simultaneously at different depths. This enables our eyes to focus on anywhere in the scene and thereby can produce natural accommodation cues. However, because the focal planes are transparent, the front focal planes are unable to block light emitted by the back focal plane. This means that light emitted from the back can easily leak through a front virtual occluder. The light leakage significantly weakens the occlusion cues rendered by multifocal displays. Let me show you an example. In this scene, there is a green dinosaur in the front and a blue grid in the back. We focus the camera on the dinosaur. As can be seen from the captured result, the front dinosaur is unable to block light from the blue grid. This weakens the occlusion cue and reduces the contrast around depth discontinuities. In this paper, we enable multifocal displays to generate occlusion cue and retain contrast near occlusion boundaries. This is a captured result on our prototype on the same scene. As can be seen, the proposed display successfully prevents the light leakage. Our key idea is that for most scenes, steering the light rays away from the occluder is enough to create the occlusion cue. In the example shown here, all we need to do is to turn the entire light cone by a small angle such that no light rays pass through the virtual occluder. Since no light rays can be seen by our eyes through the occluder, we create an illusion that the virtual object can actually block light. Since we're tilting the entire light cone, we call the method cone tilt. More importantly, since we tilt the entire light cone, we do not need additional angular resolution. Therefore, we return the spatial resolution. With cone tilt, we can create a nice occlusion cue that cannot be generated by a typical multifocal display. In the scene, there is a smiley face in front and a question mark with the text cone tilt as far. In reality, when we move our eyes left and right, we should see that the text reveals and hides behind the smiley face. Here, we show the captured results on a multifocal display and on our prototype. Here, the camera focuses on the question mark in the back. As can be seen, the multifocal display is unable to occlude the text. This even creates a false illusion that the text is in front of the smiley face, which is wrong. In comparison, on our prototype, even when the smiley face is defocused, it can still occlude the text in the back. When we focus the camera in the front, our prototype can also occlude the defocused background. Here is another example. Here are the rendered reality and captured results on multifocal displays and our prototype. Here we shift the camera between plus and minus 0.5 mm from the center. As can be seen from the third column, the occlusion problem cannot be solved entirely by removing the directly occluded content behind the leaf. Here is another scene. We show the captured result when we sweep the focus of the camera. Here is another scene. We show the capture result when we sweep the focus of the camera.
Hi, I am Tiankuang Zhou from Tsinghua University. In this presentation, I will give a brief introduction of our recent work on optical back propagation training methods and its applications. Light is very potential for computation with extremely high speed and energy efficiency. However, most of the optical computing methods are first trained on electronic computers before being deployed on optical systems, which limits the speed, efficiency, and accuracy of the computation. To overcome limitations brought by electronic training, optical training methods based on brute force search algorithms is proposed, but it is very inefficient for large search space. Gradient-based optical training is also developed, but with the strict assumption of losslessness, which is not valid for general systems. In our recent work, we propose in situ optical backpropagation training methods for diffractive neural networks. It comprises 4 steps: forward propagation, loss calculation, backward propagation, and gradient update. From optical reciprocity, the backward propagation can be physically realized by propagating the light field backwards. So, the forward and backward propagation can reuse the same physical setup. The optical fields are measured by optical interference and is later used for gradient computation. Imaging through scattering media is a hard problem in computational imaging because the severe distortion causes the original object hard to tell. With the proposed in situ optical training technique, we could adaptively train a diffractive neural network that corrects the wavefront distortion and restore the shape of the object at the imaging plane. After the network is trained, the whole process could be implemented at the speed of light. Simulation results show that the object could be recovered with high fidelity in this way. These are exemplary images from our simulation. We also find that increasing the number of diffractive layers could improve the performance of the optical network. Beyond the imaging, other applications are also demonstrated. One of them is object recognition. The diffractive neural network is trained to classify objects of different categories to different sensors with comparable classification accuracy as electronic training. The optical training can also train numerical multiplier. If we encode vector values on light fields, the diffractive layers could be trained as a matrix multiplier with very low computational error. To summarize, we demonstrate the in situ training methods of diffractive neural networks and prove the applications in computational imaging, machine learning, and numerical computation. By shifting the training process to the optical side, the energy efficiency could be increased by 2 to 3 orders of magnitude with faster speeds and higher precision. To further improve the speed and efficiency, we could miniaturize the system with recently developed tunable on-chip optical modulators. Thank you all for your watching.
In this work, we deal with the problem of photosequencing of motion blur, that is, recovering a sequence of sharp images from a blurred image. Recovering the sequence from a single blurred image can be hard due to ill-posed temporal ordering and erasure of spatial textures. We propose to capture 2 additional short exposure photographs to handle both motion ordering and texture recovery. While these 2 additional images might be noisy, they are practically free of motion blur. Hence, we exploit the complementary information from both short and long exposures to recover the underlying sharp image sequence. We computationally recover the photo sequence through a recursive blur decomposition technique, wherein the sharp image sequence is recovered through multiple splitting of exposure intervals. We learn this decomposition by training a deep neural net using images synthesized from high frame rate video datasets. Let's see our results for a few interesting scenes. In the left, we show our captured blurred image. The noisy images are not shown here but are available in the supplementary file. In this foosball scene, the ball is linearly moving at a fast pace. It hits the cube and slows down. The foosball players undergo rotational motion. Notice how the motion of both the ball and players are correctly recovered. The cavities on the player toys are reconstructed correctly too. Jellyfish is a versatile example to show our method's exemplary results. The smooth curvature of jellyfish's head is clearly recovered, and that is expected from any good method. In addition, notice the sharpness of the delicate tentacles in our result compared to the blurred capture. Skate result is interesting for its innate dynamics. A variety of motions from skateboard to the body to the hand are all correctly recovered. Our method correctly transfers textures of moving regions such as the hand, fist, and skateboard from the short exposure images and that of static regions from the blurred image without trading off sharpness. Other methods, including photosequencing using multiple blurred images, lose out on texture recovery. Now let's see a long sequence of our alternating short and long exposure captures. This is captured at around 30 frames per second. And we do a 15x increase in frame rate of the blurred images as shown in this beautiful result. We have included our results for a variety of scenes with interesting motions, ranging from complex human body motions to subtle movement of a ticking watch in the supplementary zip file. Thank you for listening to this video.
Reconstructing depth-varying scenes, such as the one shown here, is challenging for all lensless imagers. This paper reconstructs depth-varying scenes from lensless measurements by introducing programmable masks. First, let's understand why lensless imaging with depth is hard. In an amplitude mask lensless camera, the measurements of a point light source are shadows of the amplitude mask. When points are at different depths, the PSF become depth-dependent. As a consequence, reconstruction becomes difficult as we need to solve for both the depth and the brightness of the point sources. Consider this scene consisting of two depth planes. It can be modeled by a texture map and a depth map. The number of unknowns is approximately twice that of measurements, but it's a highly nonlinear inverse problem. While the scene can be modeled as a volumetric texture or intensity function, the number of unknowns becomes much larger than the number of obtained measurement, and this reconstruction becomes a severely underdetermined problem. To address the underdetermined reconstruction problem, we introduced programmable masks into lensless imagers to obtain more measurements. If we select the right mask pattern, we have a well-conditioned system with a large number of both unknowns and measurements. The key contribution of this work is using programmable masks for well-conditioned and depth-aware reconstruction. We show that translated masks can be used to bring a computational focusing operator into lensless imager so that we can reduce the size of the reconstruction problem to a single depth plane and dramatically improve reconstruction speed. We first illustrate the focusing operator with a simple mask, a pinhole. As we translate the mask, we obtain multiple measurements. We can focus on the near plane by shifting measurements according to its disparity and summing. We can obtain the same for the far plane. The focusing operator can be applied to lensless measurements with more light-efficient masks. We can still focus to emphasize measurements from the near plane, and similarly that from the far plane. So this is the reconstruction for the near plane and for far plane. To evaluate the proposed imager, we build a hardware prototype consisting of a sensor and a programmable mask, implemented with an LCOS sandwiched between a pair of cross-polarizers. In this scene, a plane with flower pattern is placed at an angle in front of the imager. The focal stacks shown here are obtained by reconstructing for different depths. The high-frequency artifacts for the static mask results caused by interference across depth are removed on the sweep cam results due to the focusing operator. We can estimate depth of the scene by assigning each pixel the depth at which it has the highest local contrast. As shown, removing the artifacts resulted in better depth estimation in textured regions. We also compare to the previously mentioned approach, jointly solving for texture and depth at each point. In summary, the proposed method can handle continuous depth scenes without relying on sparsity prior. Consequently, the reconstruction is simple and fast, and we can generate a dense focal stack of the scene. Finally, we can estimate depth from the focal stack. However, these advantages come with certain limitations. We do not model occlusion, specularity, or sensor's angular response. Additionally, sweep cam requires capturing multiple measurements, and hence a reduced time resolution. In conclusion, this work addresses the challenges of imaging depth-varying scenes with lensless imagers. For more details, please refer to our paper.
Hi Hi everyone, I'm Hani Gupta from IIT Madras, and in this work we are going to focus on guided super resolution from unaligned thermal and visible images. Capturing thermal radiation is useful in performing many tasks such as monitoring, surveillance, and healthcare. Thermal imaging is also a robust imaging technique as it works well in extreme visibility conditions and hence allows nighttime vision. However, thermal cameras are very expensive, and this restricts the widespread applicability of such cameras. The low-resolution cameras are relatively affordable, and most of them are accompanied by a high-resolution visible camera. Hence, using guided super-resolution along with low-resolution thermal cameras is a feasible option that allows convenient usage of thermal imaging. The problem with the existing guided super-resolution method is that they assume pixel-to-pixel alignment between the thermal and the visible guide images, which is very difficult to achieve because of the difference in the wavelength range. Hence, in this work, we propose methods for guided super-resolution that do not require pixel-to-pixel alignment between the input images. We propose two methods that perform implicit alignment correction along with guided super-resolution from the unaligned images. Our first method attempts to align the features obtained from the two input images in the feature space itself, whereas our second method performs alignment correction in the input space by jointly performing alignment correction and super-resolution. We first propose a CNN model for guided super-resolution based on dense blocks and attention-based feature integration. The architecture of the network is shown here. Among our two methods for implicit alignment compensation, the first one targets rectification of misalignment in the feature space. To do this, we propose additional constraints or loss terms that aim to reduce this misalignment between the features. These constraints include minimizing the cosine distance or maximizing the correlation between the features obtained from the two images. Adding these constraints to the loss function acts as a regularizer and forces the network to correct the spatial misalignment between the features. Our second method compensates the misalignment in the input space itself with the help of a misalignment estimation block that estimates an optimal translation map to warp the visible guide image. We formulate this task as a classification problem and optimize it in an end-to-end manner along with the super-resolution network. Next, we show a comparison between our base model and our two implicit alignment correction methods. We can observe a significant improvement in the reconstructions with the help of alignment correction. Misalignment between the input images can often lead to blurriness or artifacts, hence misalignment compensation plays a very important role in producing better high-frequency details and avoiding these artifacts. We also observe that alignment correction in feature space leads to better reconstructions as compared to the alignment correction in the input space. Here is another example where we compare with two existing guided super-resolution methods. We can observe that both our methods perform better, especially feature space alignment. Feature space alignment is able to reconstruct the object structures despite significant misalignment, which can also be perceived from the Groundtruth disparity map shown in the slide. In conclusion, we have proposed methods for guided super-resolution from unaligned thermal and visible input images. Our two methods perform implicit alignment correction in feature space and in input space respectively. Thank you for watching our presentation, and please post your questions on the workshop page. Also, please follow our GitHub page for updates regarding our work.
HeartCam, camera-based physiology monitoring in the wild. Imagine a car that could automatically stop if a driver has a cardiac arrest while driving. Changing blood concentration with each heartbeat causes small intensity variations on the skin, called imaging photoplethysmograms, IPPG, which can be recorded with a camera and processed to obtain vital signs, for example heart rate. Unfortunately, the IPPG signal is very subtle and prone to noise. There are two unique, large sources of noise during driving: drastic illumination changes and large head motion. We show that our near-infrared setup is able to reduce most of the ambient light variations present during driving. Most of the ambient light variations present during driving, including sunlight, can be reduced specifically at 940 nanometers. However, some sunlight may be passed through. We further reduce ambient light variations with dark frame subtraction. The camera frame capture is synchronized with the light source such that only every other frame is illuminated by the light source. The bright frames capture both the LED and ambient light, and the dark frames only capture the ambient light. The dark frames are subtracted from the bright frames to reduce the remaining ambient light. Most optical filters are designed for small incidence angles, but in a driving environment, the angle of incidence is often large, making the filters less effective. As the angle of incidence increases, the transmitted light is weaker and starts to shift towards shorter wavelengths referred to as blue shift. And as the angle becomes larger, the filter is no longer effective at blocking the sunlight wavelengths. We were able to account for the blue shift effects with a 975 nanometer filter, but the accuracy of heart rate estimation was not improved much because IPPG signals are very weak in further near-infrared and become more prone to motion artifacts. Our proposed near-infrared approach outperforms the state-of-the-art methods in RGB during realistic driving. However, accounting for blue shift with 975 filter did not improve the results, and since there were fast changes in lighting, the dark frame subtraction ended up causing artifacts that hurt the results. When a person moves a lot, 2D tracking often fails over time, making it hard to recover the IPPG signals. By illuminating a subject with a projected pattern, we can get their depth information and obtain 3D facial landmark positions to improve the tracking accuracy. We convert the depth image to a point cloud and estimate normal vectors for all points. We can use the depth information to better localize the facial landmarks as the person moves. We show that 3D tracking is more robust to motion than traditional 2D tracking and improves the results. So far, we have only tested this in the lab with moderate head motion. Even though camera-based physiology signals are easily corrupted by noise, we have shown that with careful hardware and algorithmic design, we can overcome illumination and motion noise, which opens up the possibilities of using this technology in realistic scenarios outside of the lab.
Hello everyone, I'm Do Honghui, a student from Beihang University. It's my great pleasure to introduce our research work about optical deep residual learning with deep vacuum neural networks. Optical computing has a huge potential to support high-performance computing. Because of the low power consumption, speed of light processing, and high parallelism. What's more, the optical layer fabrication capability is significantly enhanced in recent years, which greatly promotes the progress of optical computing. Recently, a new optical framework named the Deep Vacuum Deep Neural Network successfully performs the light speed machine learning tasks. It consists of multi-deep vacuum modulation layers and uses light diffraction property to connect optical neurons. However, those optical neural networks usually have shallow network structure, which greatly limits its performance. RedNet is one of the typical representatives of deep electronic neural networks. It effectively solves the difficulty of training deep networks by constructing residual connections. Inspired by RedNet framework, for the first time to the best of my knowledge, we proposed the optical residual learning by triggering the radio of the beam splitter measure and placing it in front of the diffraction layer. It not only enhances the learning ability of the network, but also alleviates the gradient vanishing problem in the complexity number field. Then, we cascade, upright, and inverted optical residual learning modules to construct a deep optical network. First, we analyze the computing ability of red G2N through the classification task. From the figure, we find that when the number of the layers increases, the convergence speed and accuracy of red G2N will be significantly improved. The highest classification accuracy was obtained by red G2N with 20 layers. That is 98.4% and 88.4% for the emist and fashion emist statistics, respectively. Furthermore, we demonstrate the performance of our framework for the super-resolution reconstruction. Based on the numerical experiments, whereas G2NN can learn more details and get better image quality. What's more, we can see that gradient problems cause the triggering of the plane G2Ns to be unstable and diverge when the logic number is larger than 20, where the G2N is still very reliable. In the future, we can configure the weights flexibly using programmable optoelectronic devices. Besides, we can also use free space diffract networks to improve the performance of super resolution imaging. That's all. Thanks for listening.
In this work, we show that lensless cameras are inherently capable of compressive video when using rolling shutter sensors. Compressive video is an approach that encodes multiple frames of a dynamic scene into one exposure, enabling increased frame rates within a fixed sampling budget. Computational reconstruction is then used to recover the video frames from the measurement. Our approach implements this space-time encoding using a diffuser and an off-the-shelf rolling shutter sensor. The final video is reconstructed using sparse recovery methods from compressed sensing. To do this, we take advantage of the rolling shutter capabilities of most CMOS sensors. As illustrated here, rolling shutter sensors expose each row of pixels over a unique time window. At the start of the exposure, only the top row is active, shown here in red. And as the exposure evolves, the exposure band sweeps down the sensor. This process distorts any fast dynamics in the scene as seen here in this image. Note that in our prototype we use a dual shutter sensor which reads from the outside in. To illustrate why rolling shutter causes problems with conventional lenses, consider a simple dynamic scene consisting of 3 point sources that flash at unique locations and times. A YT projection of such a scene is shown on the left. The rolling shutter exposure can be thought of as recording diagonal slices through the video as illustrated in this animation. The exposure band is shown in red and the captured measurement is shown on the right. While this process does preserve some temporal information, for example, when the magenta and yellow sources occurred, it does not capture any information about many points in the video such as the cyan source. Hence, it is not possible to recover the entire video just from the output image alone. We resolve this problem using spatial multiplexing, which we implement optically by replacing the lens of a conventional camera with a diffuser. This spreads light from each scene point over most of the sensor, enabling the exposure band to capture information about nearly all spatial points at all times. We model the diffuser's effect on the dynamic scene as convolution with the diffuser point spread function. The result is that each spatial point in the scene maps to a distributed pattern on the sensor. In the YT projection, the information is spread vertically, but each event remains localized in time. The effect on the final measurement is illustrated here by applying the rolling shutter sampling function to the multiplexed dynamic scene. Because of the multiplexing, the information from the cyan dot is no longer lost. This allows us to reconstruct the initial video from one exposure using sparse recovery methods. We demonstrate this approach in a prototype system consisting of a single diffuser and a commercial rolling shutter CMOS sensor. In this example, the test object is a multicolored spinning fan. After passing the raw measurement through the sparse recovery algorithm, the fan's dynamics are clearly visible. We reconstruct 140 frames at over 4,500 frames per second. Here is another example scene. The raw data is shown on the left and the reconstructed video on the right. Note that a similar concept is also at work in Kristina Monakova's spotlight on spectral diffuser cam. For more details, please see our paper published at ICCP 2019.
Patch scanning displays. Advent of emerging fields such as virtual reality, augmented reality, electronic sports necessitate even greater pixel densities and higher presentation rates. Consider a target image that is at 4x resolution with respect to a base spatial light modulator's input. A base SLM's subpixels are configured to display the input. Our method improves image quality and presentation rate of a base SLM. Here we show an example result from our method. and comparing it against a native input of SLM. To introduce our proposal, let us start from a basic example. Typically, smallest fraction in a display hardware is a pixel. We aim to change that by using patches instead. Here we show 3 patches that can help us in reconstruction of a target. We tile patches in an order and scan given patches over a surface. During a scan, we stamp each patches at the right time to reconstruct the given target. In our proposal, we identify patches for complex visuals. Identified patches are scanned over a surface using an optical scanner. As a result, an image is generated in temporally accumulating way. In our imaging model, patches are represented all at the same time on an amplitude-only SLM. For stamping a patch on a surface from a SLM, we rely on a locally addressable backlight. As our backlight is using incoherent illumination, non-negativity is a constraint in this problem. We overcome this constraint by showing that non-negative matrix and tensor factorization can help solving such a reconstruction model. In our prototype, we use a locally addressable backlight with incoherent illumination. We illuminate a transmissive amplitude-only SLM. We scan the outcome with an optical scanning mirror. We use 2 Raspberry Pis along with a Jetson Nano for computational needs. Our prototype is designed as a proof of concept. Different miniaturized variants is possible with the right engineering resources. Here we show a sample image reconstruction using our virtual prototype. Here we show a comparison of our reconstruction with respect to an input at a native resolution of a SLM. You will find more examples at the end of this video. We conduct image quality assessments for our method. Conventional metrics of peak signal-to-noise ratio and structural similarity metrics suggest a 2.5x improvement over a base SLM. Additionally, we use a learned perception metric closely approximating a human observer's choice. Our findings suggest that our method is 4 times closer to a target image with respect to a base SLM's outcome.
Today I am presenting our work titled Memory Efficient Learning for Large-Scale Computational Imaging. Computational imaging systems marry the design of hardware and software to create a new generation of modalities that image beyond what is currently possible. Recently, many methods have been proposed to jointly optimize or learn a computational imaging system's hardware and software. Taking a closer look, classic methods rely on knowledge from the physical system model, while deep methods rely on knowledge from training data. If there are errors in the physical model, artifacts will result in classical methods, while deep methods learn this relationship directly. Finally, classic methods require hand-tuned parameters, while deep methods automatically tune parameters using gradient-based updates. Physics-based learning combines the benefits of both, using data to learn what we do not understand, and incorporating the system model to reduce the amounts of data required. Physics-based learning incorporates the forward model process by unrolling the iterations of the classic image reconstructions optimizer to form the layers of the network, the output of which is fed into the loss function for training. For large-scale computational imaging systems, computing gradients for training is very costly in memory. To compute gradients using backpropagation, autodifferentiation stores many intermediate variables in an autodifferentiation graph. As an example, we consider a physics-based network that requires 500 gigabytes of memory for training, which is an order of magnitude larger than what modern GPUs can handle. Our method that I am presenting today reduces the memory required for physics-based learning by a factor of n, allowing us to train, for this example, using only a single gigabyte of memory. To illustrate our solution, consider this small-scale physics-based network. To perform our method, we first evaluate the physics-based network as if during test time, seen here in blue, not storing the larger autodifferentiation graph. To compute gradients, we recreate smaller autodifferentiation graphs for each layer one at a time, starting at the output of the network and working our way in reverse, seen here in red. We only store a single layer memory at a time, thereby saving a factor of n in memory. There are other methods that save memory, however they do so at the cost of worse computational complexity. A downside of our method is that it is approximate. While generally accurate, numerical errors from computing inverses can occur and accumulate. Let's take a look at some results. In this first example, we examined the prior for 3D multi-channel MRI by learning a 3D residual network to act as a proximal operator. Using standard backpropagation, this requires 40 gigabytes of memory, while our method only requires 10 gigabytes of memory. In this next example, we learned the best measurements to improve the temporal resolution for super-resolution optical microscopy, also called Fourier tachography. For this, a physics-based network is formed from a phase retrieval optimization problem. Using standard backpropagation, this requires approximately 500 gigabytes of memory, while our method only requires 3 gigabytes of memory. Finally, we look at learning the diffuser for the 3D diffuser microscope. A physics-based network is formed from the deconvolution optimization, and a phase mask is learned to maximize the retrieval of 3D information. Using standard backpropagation, this requires approximately 10 gigabytes of memory, while our method only requires 2 gigabytes of memory. In summary, memory-efficient learning can accommodate the scale of real-world computational imaging systems such as MRI, super-resolution optical microscopy, and the 3D diffuser microscope. Details and more can be found here. This research was made possible by the people pictured here and many members of the Waller and Lustig labs. Thank you.
Hello, I'm Christina Monikova, and I'm going to present Spectral Diffuser Cam. Hyperspectral imaging aims to capture a hyperspectral data cube in which each spatial XY position in an image also contains a spectral intensity across wavelengths. Knowing this provides information about material properties that are not accessible from a color image alone. This can be useful for identifying healthy versus sick plants, or cancerous versus healthy tissue, and many other applications. Snapshot hyperspectral imagers aim to recover the full spatiospectral cube without any scanning. Despite the lack of scanning, these systems are often bulky and require expensive optical components, confining them to benchtop applications. However, recent imagers have demonstrated more compact form factors. Here we present a novel snapshot hyperspectral imaging architecture that consists of a spectral filter array and a diffuser. Our system is cheap, costing only $5 for the filter array and diffuser at scale, and our system is very compact. The spectral filter array can be deposited directly on the camera sensor, and the diffuser is placed only a centimeter away from the sensor. The spectral filter array consists of 64 spectral filters, each with a narrowband spectral response and unique center wavelength. The filters are grouped together in an 8x8 grid that's repeated across the sensor, much like a Bayer pattern in color imaging. We'll refer to this 8x8 grid as a superpixel. This architecture allows for both uniform spectral sampling across a user-defined spectral range, as well as non-uniform spectral sampling with user-defined filter bandwidths and center wavelengths. This makes the system incredibly flexible, which we believe could be useful for task-specific imaging. Now let's look at the role of the diffuser. Rather than using a diffuser, we could put our spectral filter array on a lens camera, but since lenses map points in the world to points in the camera, if a green point focuses to a blue pixel, it won't be recorded. To fix this, we can stop down the aperture to reduce the resolution and spread information across a bigger spot, but this results in an 8x resolution loss in each direction. If instead we use a lensless imaging architecture like the diffuser cam architecture, the diffuser spreads out the information while keeping high-resolution features in the point spread function, so a green point will hit multiple filters. After computational recovery, it's then possible to get back a high-resolution image. So our imager captures a 2D measurement, and given knowledge of our imaging forward model, we can pose a compressive sensing-based optimization problem with a regularizer to recover the 3D hyperspectral data cube from our 2D measurement. After reconstruction, we can see that this example is a resolution target illuminated by a broadband white light source. A superpixel is the size of this yellow box, so we can clearly see that we get sub-superpixel resolution. We can also recover more complicated natural scenes like this color target. And for each point in the recovered image, we have 64 spectral channels across a 500 nanometer range. If you'd like to learn more, please check out our project page and paper preprint.
Hello everyone. I will now present our work on how interreflections can be helpful for reflectometry. By reflectometry, we refer to the process of acquiring the reflectance properties of real-world materials as represented by their bidirectional reflectance distribution function. Our main goal in this work is to show that this can be achieved by taking advantage of interreflection effects. For some insight, let's say we use a concave shape for reflectometry. Each image measurement will sum contributions from not only single bounce paths, but also from two bounce and higher order paths. The contribution of a two bounce path will be a function of two entries of the BRDF, one for each reflection event. A three bounce path will involve three entries of the BRDF and so on. Consequently, just a single image can provide us with information about a very large set of BRDF entries. However, the relationship between measurements and BRDF values is highly nonlinear and can no longer be trivially inverted. Our measurement setup is fairly simple. We capture a single image of a surface of known shape using calibrated directional illumination and an orthographic camera. We then perform analysis by synthesis. Given as input the calibrated scene parameters and the BRDF hypothesis, our simulator must be able to reproduce the high-order transport effects present in our measurements. The simulator should also compute derivatives of images with respect to the BRDF. We achieve both of these objectives by using a Monte Carlo differentiable renderer, which we have implemented on top of the bidirectional path tracer of Mitsuba. We consider a tetrahedron, imaged with an orthographic camera and a directional light source. The captured image will be the result of reflection at only three angles, and will provide us with only three constraints on the BRDF. We additionally consider the concave side of the same tetrahedron. A single image in this case will provide us with significantly more constraints on the BRDF. We use our optimization framework to recover a synthetic material represented using bases with different numbers of elements. When our basis has three elements, both convex and concave shapes provide sufficient constraints to correctly recover the unknown BRDF. However, as we increase the number of basis elements, the convex case becomes under-constrained and the BRDF recovery is unsuccessful. By contrast, in the concave case, the BRDF recovery remains just as accurate even when we increase the number of atoms. As we can observe from these results, what shape we use has a strong effect on the accuracy of BRDF recovery. This motivates two important questions. First, how can we systematically characterize how informative each shape is for reflectometry? And second, how can we design an optimal shape that maximizes the amount of information on the unknown BRDF available in a single image measurement? We show one simple procedure for producing such a custom shape through two design goals. First, we want our shape to provide strong coverage of the specular part of the bivariate space. Second, we want this coverage to be achieved through paths of no more than two bounces. We start off the design of our custom shape using a half sphere. For any given ray from the camera, we consider its specular reflection on the half sphere. The reflected ray will intersect the unknown part of the shape at some point. We select the unknown normal at this point to correspond to the mirror reflection. Repeating this process for all camera rays gives us a set of normal constraints. We show single-shot recovery experiments for a few BRDFs from the Merle database. Using our custom shape, we can achieve 11.2 times more accurate BRDF recovery than when using the convex sphere, and 2 times more accurate recovery than when using the concave sphere. Thank you for your attention.
All right, so welcome back to the last session of the Computational Cameras and Displays workshop. We're really excited to have Orly Liba speaking. Orly actually did her PhD at Stanford, where she graduated in 2017, and she's now a senior research scientist working on computational photography at Google. And she's recently been working on features for the Pixel smartphone, including some of the features that probably many of you know, like night sight, which I think she'll be talking about. And this is something that I've actually used on my own Pixel phone. And so it's been really exciting to see some of these features actually being shipped out to thousands and thousands of devices. So we're really excited to have Orly here to speak about her work. We're going to play the pre-recorded talk, and Orly will be on for live Q&A afterwards. So Orly, also feel free to say a few words while I pull up your talk here.
Thanks, David. It's really great to see you virtually. Hopefully next year's will be in person with everyone else at the workshop. Looking forward to getting some questions afterwards.
Great. And so, yeah, feel free to put the questions in the chat, and I'll go ahead and proceed with the presentation.
Hi, everyone. I'm Orly Liba. I'm a senior research scientist in Google Research in Mountain View, California. My talk, titled Computational Photography in Very Low Light, shows some of the work of the computational photography team. Our research is implemented on Pixel phones, Google Photos, and more. The first part of the talk will cover the basics of handheld mobile photography in very low light. This work was published and presented in SIGGRAPH Asia 2019 and was also the basis of NightSight, which shipped on Pixel phones in November 2018. Next, I will talk about the challenges of astrophotography and how we overcame them. Finally, I will describe how semantic segmentation of the skies can further improve the appearance of low-light images. This project was published as part of the NTIRE workshop at CVPR this year. Let's begin. The amount of light detected by the camera's image sensor inherently has some uncertainty called shot noise, which causes images to look grainy. The visibility of shot noise decreases as the amount of light increases. Therefore, it is best for the camera to gather as much light as possible to produce a high-quality photo. Different strategies have been used to overcome this. Photographers typically increase the lens aperture in low light. However, smartphone cameras usually have a fixed aperture that is small, and the aperture size is limited by industrial design considerations, like the phone's thickness. To capture more light, you could also lengthen the exposure time. However, unless you have a tripod, this can lead to motion blur, and carrying a tripod everywhere is inconvenient. You can also use a flash to illuminate the scene, but only if the subject is close. Even then, this can lead to displeasing and unnatural results. There is another method, though. You can also collect more light by capturing multiple frames and averaging or merging them, which has a long history of treatment in literature. This is called burst photography. In 2016, we published a paper on a system called HDR+, which leveraged burst photography for high dynamic range imaging. The frame merging that it did was robust to motion between frames and was efficient enough to be launched on Google Pixel phones as the default camera. Now, for imaging in even lower light, we're presenting several improvements to HDR+, leading from this dark and somewhat noisy image to this bright, clean, and sharp image. The new system was launched on Pixel phones as a separate camera mode called NightSight. There are 4 main improvements in NightSight over HDR+. First, a system called motion metering analyzes viewfinder frames and changes the exposure time based on the amount of motion in the scene, adaptively trading off noise and motion blur. Second, we've improved upon the frame merging in HDR+. It retains HDR+'s motion robustness while also further reducing noise in static parts of the scene. We also have a learning-based auto-white balancer to do a better job of white balancing in heavily tinted scenes that are more common at night. Finally, we have a special tone mapping that brightens the image while retaining the feeling of nighttime. The result is that our system captures clean, sharp photos of low-light environments using only a few seconds to capture the burst and less than 2 seconds to process it on a mobile phone. First, motion metering. The basic idea is to measure the scene motion in real time so that we can adapt the exposure time to it. In relatively static scenes, such as the one on the left, we want to use longer exposure times to increase the amount of light captured. In dynamic scenes, such as the one on the right, we use shorter exposure times to reduce motion blur. The ISO, which is correlated to the noise in the image, is changed in the opposite direction to keep the overall exposure the same for a particular scene. Relative to not having motion metering, this system produces a result with lower noise and more detail in the static scene, and less motion blur in the dynamic scene. So, what does not having motion metering mean? That is, how is exposure time typically selected? This is usually done by selecting a curve in this space of exposure time versus target sensitivity, where sensitivity is just the exposure time multiplied by the ISO. Here, the x-axis is proportional to the scene brightness, with bright scenes on the left and dark scenes on the right. The y-axis is the corresponding to exposure time, where the bottom represents short exposures and the top represents long exposures. The way to read this curve is by starting from the lower left. As the scene gets darker, exposure time starts increasing along the first slope. The ISO remains constant here at its lowest possible value, which means that the exposure time cannot go any higher. In other words, the upper part of this chart is inaccessible. When the exposure time flattens out, it implies that the ISO is increasing. A camera designer would hold the exposure time here in order to bias the camera's behavior towards less motion blur, but more noise. In very dark scenes, the exposure time usually reaches an upper limit and levels off. Now, when the camera is ready to capture, an auto-exposure algorithm estimates the scene brightness and chooses a particular sensitivity. The curve is then used to determine the exposure time. This curve is called an exposure schedule. In contrast to the static schedule, motion metering uses a dynamic exposure schedule. If the measured scene motion is low, the slower schedule is used, which chooses higher exposure times. If there is a lot of scene motion, the faster schedule is used. The final exposure time and ISO can do better job at trading off noise versus motion blur compared to the static schedule. We want to use a dynamic exposure schedule, but we need to find a way to measure the scene motion in real time. In particular, this needs to be done efficiently, minimizing power draw on the mobile device. Our solution leverages optical flow on the sequence of raw viewfinder frames. However, there are two key differences that help us improve efficiency. First, we only measure the magnitude of the flow field. This is because the direction of the motion blur does not affect the final image quality. We also compute the magnitudes on downsampled version of the raw viewfinder frames, as high spatial resolution is not required to ultimately select the exposure time. So how do we compute the magnitude of a flow field without computing direction? Starting with the optical flow brightness constancy equation, we realize that we can rearrange it into an inequality relationship on the motion magnitude, which is on the left-hand side here. This inequality says that the lower bound of the motion magnitude between two images is the ratio between the intensity difference at a pixel location in time divided by the magnitude of the spatial gradient at the same location. It reaches equality when the motion is in the same direction as the gradient. This bound can be computed in closed form at every pixel in the image pair. There's one more thing to consider here. What happens when the gradients are near zero? Since it's the denominator of this expression, the gradient can become highly sensitive to noise, which decreases the accuracy of the bound. To overcome this, we only compute motion magnitude in regions where the gradient is significantly above the noise level. Since we're operating on raw images, the noise level sigma can be computed efficiently from a simple Poisson plus Gaussian noise model. Let's see how this works in practice. Here's an extremely zoomed-in view of a pair of raw viewfinder frames that have been downsampled. These have small amounts of motion between them, primarily from handshake. Zooming out shows the full view, so now you can see how small the motion is. But we want to be able to measure it and adapt accordingly. Computing the lower bound produces this motion magnitude field, where brighter pixels indicate higher magnitude. However, we see the motion is overestimated in large parts of those images, denoted by the white areas. This is expected since the gradients at these locations are low relative to the noise. To overcome this, we use the noise mask, shown here as a binary image. The white areas tells us where the gradients are above the noise floor. Applying the mask leads to the following magnitudes, where now very few locations have overestimated magnitudes. Additional downsampling and outlier rejection leads to the final motion magnitudes. We found that bounded flow compares favorably to other optical flow methods when only the flow magnitude is considered. We used the Intel benchmark dataset to compute the mean absolute error in motion magnitude for bounded flow and other optical flow methods. Bounded flow's motion magnitude accuracy is second only to a CNN-based optical flow method we evaluated called FlowNet. However, bounded flow takes 2 orders of magnitude less time to run. There is more involved with motion metering, especially in terms of how the flow magnitudes are converted to a dynamic exposure schedule. See the paper for more details. Now we'll talk about how we merge the frames of the burst. Frame merging is needed to reduce temporally changing noise. As you can see, multi-frame bursts always have some motion in them. Therefore, we need a merge algorithm that adapts to motion in order to reduce noise while avoiding motion artifacts. This is a major challenge. As you can see here on the left, too little frame merging leaves noise, while on the right, too much merging causes motion blur. As part of HDR+, Hassan et al. Developed tile-based alignment and Fourier domain merging to reduce noise while avoiding motion artifacts. Our system improves the previous merge method by introducing additional motion awareness and improved denoising in low light. Note that motion-robust merging can be done in various ways. For example, Wronski et al. Developed multi-frame merging for super resolution that is an effective merging method for low light and works in the spatial domain. The merge process is essentially a weighted average in the Fourier domain, in which averaging occurs separately in each frequency band. The contribution from each frame in each location is proportional to 1 minus A and is calculated for each frequency band omega. A is the classic Wiener function, in which D is the difference between tiles in Fourier domain. Sigma is the noise standard deviation. The most important thing to notice here, C, which we call the temporal strength, is a tuning parameter that scales the noise and lets us control the amount of merging and the robustness to motion. This is a plot of the contribution of the tile to the weighted average as a function of the difference between the tiles. On the left, we can see that when the difference between tiles is small, we can safely increase merging and reduce noise. On the right, when the difference is large, for example when there is motion, we reject their contribution to the weighted average to avoid ghosting. That's how HDR+ achieved motion robustness in merging. Now let's look at a different temporal strength. As the temporal strength increases, the amount of averaging increases. In HDR+, we used a single value for the temporal strength. As I'll show you in the next slide, this is not sufficient for low-light imaging. To achieve better denoising and motion robustness, we'll use a spatially varying temporal strength, which is low in regions with motion, as in the pink curve, and high in static regions, as in the green curve, to allow more merging and denoising. Let's look at this low light burst, which has a lot of motion. This is the result of using a low temporal strength, such as in HDR+, which maintains detail. However, noise is still high because this is a low light scene. Here's the temporal strength when it's high. We average more and therefore we see motion blur in the face. Let's look at this crop in a static region. On the left, where the temporal strength is low, there is remaining noise because merging is not sufficient. On the right, the noise is reduced when we use a high temporal strength. However, a higher temporal strength results in motion blur on the dynamic face. We would like to increase merging and denoising in the static regions where there is no risk of motion artifacts, while also retaining details in the regions where we have motion. In order to do that, we introduce a new algorithm calculating motion or mismatch between tiles and a spatially varying temporal strength. The mismatch M between the tiles is also a Wiener function, but now D is the difference between tiles in the spatial domain. It is actually the residual calculation of the alignment process. Using the mismatch maps, we compute F of M, the temporal strength factor, which scales the temporal strength. The result is a spatially varying temporal strength, which enables more merging in the static background, shown here in green, and less merging in dynamic regions, shown here in blue, to reduce motion artifacts. Here we can see the result. Using a spatially varying temporal strength, we get the best of both worlds. We have less noise in static regions and less blur in regions with motion, like the face. Additionally, in the regions where merging is reduced, we increase spatial denoising to create a more uniform noise distribution across the image. Now we describe another important component of our system, auto-white balance for low light. White balance, the application of gains to each color channel of a captured image to make white appear white, is a well-studied problem. Our brains do this naturally, but computationally it is difficult to predict the color of the illumination and separate it from the color of the object. For example, what is the real color of this face? As you can see, predicting the illumination and the white balance gains of an image is an ill-posed problem. This is why we chose to use machine learning and build off of fast Fourier color constancy, which we have extended for low light scenes. Why is low light more challenging? In low light, the images have more noise. To address this, we train on real images that have real noise rather than on synthetic data. And we've created and tagged a new dataset for low light with around 3,500 images. Tagging here means that we tune and choose the white balance gains that produce the best colors in each photo. Additionally, in low light, there are various highly colorful illuminants, such as colored lights, campfires, and so on, which result in images with practically zero signal in one of the color channels. Images with missing color channels cause ambiguity in training the color constancy model. To address this, we've developed a new error metric for training the color constancy model, the anisotropic reproduction error. This metric takes into account the distribution of RGB values in the image and correctly ignores errors that have no effect on the appearance of the image. These are the results of our updated learning-based auto-white balance algorithm compared to the camera default. As you can see, the colors on the right appear closer to as we perceive them. Putting it all together, this is the result of the HDR Plus baseline on 13 frames. Adding our new tone mapping makes the scene brighter, allowing the viewer to see more detail while preserving global contrast. However, noise becomes more apparent and overwhelms visible detail in the darker parts of the scene. Using motion metering allows us to increase the exposure time without introducing significant motion blur. Here we are using an exposure time that is 5 times longer than the default exposure time. The resulting image is less noisy and more detail is visible. Adding motion adaptive merging allows us to increase temporal denoising in static regions, further improving detail. Let's zoom in to see the difference. We can see less noise on the right. Finally, we apply the low light auto white balance gains, making the colors in the scene match our perceived colors. And here are the results side by side. And a few more results across a variety of scenes. In learning to see in the dark, an end-to-end convolutional neural network was trained to produce high-quality photos in low light from a single frame. We compared the results of their network to the results of our system. Our system shows more detail and less noise compared to the alternative. Using a burst for noise reduction is much more effective than using a single frame. Here is a second example in which our system shows more detail. Additionally, the processing time of the network described by Chen et al. Is estimated to be around 10 seconds on a mobile GPU, which is above our 2-second budget. Low-light photography still has various limitations. For example, autofocus still fails in very low light, but it can be addressed by increasing the exposure time of the focus frames. Real-time preview is challenging due to the longer exposure and processing latency, which have to be within 15 frames per second. And brightening the image could over-brighten the sky to create a night-in-the-day effect. We addressed this issue in the follow-up work on sky optimization, which I will review in the following slides. This past year, we extended exposure further to improve imaging in even lower light and shipped astrophotography to enable capturing the stars and the Milky Way. This photo was captured with a mobile phone, the Pixel 4, with an exposure of 4 minutes. This is how the photo looks straight out of the camera app, with no additional post-processing. In fact, it shows more detail and color than a person can see with the naked eye. To capture enough light, we extended the capture time per frame. This requires the phone to be stable on a tripod or leaning on a rock, for example. We detect that the camera is stable using the device's gyro readings. We combine the signal of the gyroscope with motion metering to assess the device's stability. Because we're sensitive to small motions, something we have to take into account is vibration that comes from tapping the phone to trigger the shutter. This settles down quickly and doesn't compromise the final result, so we shouldn't let it interfere with motion metering. Smoothing and masking the gyro signal enables that. The long exposures this approach allows are crucial for extreme low-light scenes. For a fixed time budget, we should capture as few frames as possible, because each frame introduces more read noise. Here's an example in which per frame capture time is extended from 1/3 of a second to 1 second, The total capture time increases from 5 to 6 seconds, and the image quality is improved significantly. The stars in the sky are now clearly visible. Exposures that are too long result in motion blur, and the stars become short lines. Empirically, we've seen that limiting the per-frame exposure to 16 seconds avoid these streaks. Our motion-robust frame averaging is able to merge the frames without artifacts. Another challenge is that in long exposures, dark current causes a significant signal. Pixels with high dark current appear as warm pixels and are visible as tiny dots. These pixels can be detected as outliers in the burst and corrected by replacing their values with the average of their neighbors. Now we'll see how low-light images can be further improved by processing the sky separately from the rest of the image. The brightness of the sky influences our perception of the time of day. Brightening the image as we did in night sight causes a night into day effect, which is confusing. For example, this photo was captured after sunset, but it doesn't really seem like it. We can bring back the feeling of dusk by selectively darkening the skies. The sky has predictable features and it is mostly uniform. This makes noise more visible in the uniform regions of the skies, but it also means that the skies can be denoised more aggressively. An additional aspect in which the sky is different in the foreground is that at night it is illuminated by different sources. For example, the foreground can be illuminated by streetlights, while the sky is illuminated by moonlight or diffuse light from the ground. These sources can have different colors. However, our color constancy algorithm assumes a single light source, which can cause errors in color predictions when there is more than one source. In this photo, the illumination source is predicted such that after applying the white balance algorithm, the color of the face looks natural. However, the sky, which is illuminated by a different source, appears magenta. When we predict the illumination source based on the skies, they appear blue after applying the white balance algorithm, but the skin of the person has a greenish tint. Spatially varying white balance can produce natural colors on both sky and foreground, as can be seen in this image on the right. Here is an overview of sky optimization. To train the model, we need annotated training data. The first step to creating the sky segmentation dataset involves manual rough annotations of over 100,000 photographs that had been captured at all times of day and night, in a wide variety of environments. The rough annotations are then refined using inpainting and guided filtering in order to make them more accurate. We then train a CNN and use MorphNet to optimize the architecture so that the final models can fit within the size constraints provided by the camera app. To enable fast processing, inference of sky segmentation on device is done in low resolution, and then we upsample the mask using a guided upsample approach. Finally, we apply the image processing steps: tone mapping, contrast enhancement, noise reduction, and spatially varying white balance. A key component of our algorithm is a weighted guided filter used for snapping the edges of the mask to the edges of the image and calculating matting. It uses a confidence map, calculated based on the inferred sky mask, to ignore pixels from the sky mask which are uncertain, meaning that their probability to be sky is around 0.5. And this is the result. In fact, we use the weighted guided filter twice, once to improve the annotations for training data, and again to upsample the inferred mask in the camera pipeline. Without a good mask, we get halos. These are very early results before we had a good segmentation model and refinement. Notice the halos inside the tree. A good mask should be very detailed and also have continuous values, meaning that it represents the amount of sky in each pixel. This representation is required to accommodate semi-transparent objects and the slightly blurred edges around objects. Let's look at the process of creating the dataset. Accurate annotation of the tens of thousands of images needed for training is not feasible. Therefore, our manual annotations are rough and do not include the boundaries. We annotate the sky and non-sky regions. Pixels that are without annotations are labeled as undetermined. To estimate the probability of these undetermined pixels to be skies, we use density estimation in painting. Density estimation uses the distribution of RGB values of the annotated sky pixels to calculate the probability that each undetermined pixel belonged to the sky pixels. Here we take advantage of the limited variability of RGB values in the skies. Finally, we applied the guided filter to reduce noise in the annotations and align the edges to the mask to the edges of the image. Now that we have a training dataset with accurate and continuous sky masks, we train a segmentation network. We use a free-stage unit architecture and apply the process of MorphNet to find the optimal architecture under the size constraints. MorphNet can discover architectures that are more efficient by jointly learning the model structure along with its weights during training. We follow the previously described two-step approach of first shrinking and then expanding the model. Following this optimization step, we obtain a model that is more accurate and 27% smaller. After that, we quantize the model to float 16 to further cut the model size by half without sacrificing accuracy. Here are some very challenging cases showing the high quality and accuracy of the mask. This is the inferred mask, and this is the mask after refinement. And another example. Now we apply image processing algorithms to improve the appearance of the skies. Sky darkening is performed by applying a tone mapping curve on the brightness of the image after HSV decomposition. A different curve is used to increase the contrast of the stars in the Milky Way in astrophotography. The sky mask also allows us to perform sky-specific noise reduction. Unlike foreground objects, which may be highly detailed and exhibit diverse fine textures, the sky tends to be fairly uniform, although it may contain stars and clouds. Knowing this, we can increase the denoise strength in the low-mid frequencies to remove noise blotches while retaining the high-frequency details of the stars and keeping them sharp. To implement sky-aware auto-white balance, we modify the color constancy algorithm to be spatially varying. The baseline algorithm is based on fast Fourier color constancy that was used for night sight, except that now we have two models. One that looks at the full image and was tuned to optimize the foreground, and another one that was trained to optimize the skies and receives the sky mask as input. The result is two sets of white balance gains. We then use the sky mask to alpha blend between them. Here we see additional examples in which the sky mask is used to reduce noise, darken the skies, and change the color to a more natural tone. To summarize, in order to capture very low light scenes with a mobile device, we use a combination of traditional methods, such as extend the exposure time to capture more light, along with computation, such as motion metering and motion adaptive frame averaging, which are used to reduce motion blur, tone mapping for nighttime scene, device stability detection, and warm pixel removal. We also use machine learning for learning-based auto-white balance and semantically aware image processing of the sky. All this needs to run on a mobile device with limited resources and with time constraints. I'd like to thank the organizers of the CCD workshop and thank you for listening.
Well, thanks again, Orly, for the really excellent talk. And our next speaker is Shumian Sen. Shumian is a PhD student at Carnegie Mellon University, and she's been working in the areas of computer vision and computational imaging. And her paper on non-line of sight imaging actually won the Best Paper Award last year at CVPR, which is a really incredible achievement out of the, I think, over 5,000 papers that were submitted. And so we're really looking forward to her talk. Again, we'll play the recording of the talk, and then Shumian will be on for a live Q&A afterwards. And Shumian, you're also welcome to say hello or say a few words while we bring up your talk again.
Yeah, thank you, David. Hi, everyone. I'm Shumian. I'm currently a PhD student at CMU working with Professor Sheinin and Professor Yanis Geolukas on non-line of sight imaging. It's a pity that we cannot meet in person this year. I'd like to thank the organizers for putting together such a great virtual workshop, and hopefully we can all meet next year. Yeah, thank you for inviting me here.
Thanks. And we'll go ahead with the talk.
Hello everyone, my name is Shumian Xin. I am a third-year PhD student at Carnegie Mellon University Robotics Institute, working with Professor Srinivasa Narasimhan and Professor Yanis Gil-Lucas on computational imaging. In this talk, I am going to talk about non-line of sight imaging and our CVPR 2019 work on using Fermat paths for non-line of sight shape reconstruction. In most traditional computer vision problems, people assume the scene of interest is directly visible. We refer to this as line of sight imaging because the scene is directly within the line of sight of the sensor. In this setting, if people would like to reconstruct an object, they will use well-designed techniques such as structure light and photometric stereo. However, all of these techniques will fail when the object is not directly visible. For example, when it is blocked by some occluder and cannot be observed directly. The goal of non-line of sight imaging is to recover such hidden objects that are not directly within the line of sight. The idea here is to utilize surrounding surfaces, for example a diffuse wall, and observe the hidden objects indirectly through their reflections on this wall. This setting is called non-line of sight imaging. In fact, humans are unconsciously conducting non-line of sight imaging all the time. For example, when hidden objects are reflected through mirrors, or when there exist sharp shadows casting from hidden objects onto visible surfaces. Now, the difficulty of non-line of sight imaging comes in when there is no visible shadows casting from hidden object, or when there's no mirrors but only diffuse surfaces. In such a case, to enable high-resolution non-line of sight reconstructions as if they are directly visible, I will discuss later in detail how we capture a new type of data that are called transient measurements, and how we use them to do reconstructions based on a theory that we call Fermat paths. I will structure my talk in the following way. First, I will do an overview of non-line of sight imaging. Next, I will describe how we capture transient measurements. Then, given these transient measurements, I will talk about a theory we call the Fermat paths that are useful for high-resolution non-line of sight shape reconstruction. Let's get started. First of all, why do we care about non-line of sight imaging? What I'm showing here is non-line of sight imaging, if it becomes practical, has many potential impactful applications. For example, one medical application is seeing inside human body. With non-line of sight imaging, doctors will be able to see inside the human body non-invasively to detect and diagnose suspicious tissue instead of performing endoscopy by inserting a tube inside the human body to capture high-fidelity images. Another potential medical application is seeing through the skin. In this case, skin is composed of multiple layers of tissue. With non-line of sight imaging methods that can help see through the skin deeply and accurately enough, more skin diseases can be diagnosed non-invasively. Another important application is search and rescue. In a collapsed building due to an earthquake, survivors may be trapped behind heavy rubble. Non-line of sight imaging can help rescue teams explore these hard-to-reach areas so that they can intervene only when necessary. The last application is robot navigation. Robots rely on what they sense to decide their next moves. Non-line of sight imaging can help in this scenario by making what's visible to robots not just the scene in front of them, but also many of the surroundings that are occluded from them. Here are the two categories of non-line of sight imaging methods, passive and active. Passive methods do not introduce new light sources into the setup and will only capture light that are already bouncing in the scene. Active methods, on the other hand, usually use highly controlled light sources to inject photons into the scene, and then capture the photons that come out of it. Most passive methods analyze the subtle shadow cast by the hidden scene. Because there is no control over the lighting, passive methods do not have sufficient information to recover the accurate 3D shape. They're able to recover only the rough motion trajectory or blurry blobs indicating where the hidden objects roughly are. The results from active methods, on the other hand, show that they're able to recover much more geometric information. In fact, in the active case, to reconstruct these detailed non-line of sight shapes, people usually also use time-resolved sensors to measure so-called transient measurements that provide additional temporal information, instead of just intensity images from RGB cameras. In our work shown on the bottom left, because we want to do high-resolution non-line of sight shape reconstruction, we used a pulsed laser as the highly controlled light source, as well as a time-of-flight sensor. Next, I'm going to show you in detail how we capture transient measurements with our active imaging system. The imaging setting I'm showing here is a confocal setting. Throughout my talk, I will discuss only the confocal setting for simplicity, but our theory and method are not constrained to such a setting. So at each scan point on this visible wall, the time-of-flight sensor records a so-called transient measurement like this, which is essentially a histogram of photons binned by their travel time. So what we will measure here is a histogram with some finite temporal resolution. In one of the experimental setups we have, the temporal resolution is 4 picoseconds, corresponding to 1.2 millimeters. Now the laser illuminates a point on the visible wall by releasing an ultra-short light pulse. When light hits the visible wall, it will scatter in all directions. Some of the photons will go directly back towards the sensor, and this captured photon, according to its travel time of light, will contribute as one count to the histogram. There will also be photons traveling towards the non-left-side objects, get reflected to the same scan point, and are captured by the camera. Because this photon travels through a longer path in the scene, thus it contributes to a latter part of the histogram. If we repeat the process of releasing photons and measuring their traveling time for millions of times, we will eventually get a smooth transient measurement like this. Now that we know how to measure one transient at a scan point, the whole scanning procedure is done by densely scanning the visible wall point by point. At each scan point, we get a transient measurement, and eventually the data we have will be a spatial temporal tensor that we call transient measurements. Next, I'm going to show you how we use these transient measurements to do non-line-of-sight shape reconstruction based on a theory that we call the Fermat paths. First of all, what are Fermat paths? For simplicity, I will explain in a 2D visualization, but everything will hold in 3D as well. And for convenience, we flip the 2D setup upside down, so now the visible wall is down below. Also, I will assume the non-line-of-sight object is convex, but I will show you later that it works for hidden objects of arbitrary shapes. First, notice here that I colorized the transient measurement in blue and red respectively. As you've seen earlier, the blue part corresponds to photons that travel from the laser to the visible wall and directly back to the sensor, while the red parts are from the photons that bounce 3 times in the scene, first on the wall, then on the non-line-of-sight object, and finally on the visible wall again. Because the blue part contains only the information about the visible wall, therefore we can always calibrate the system and get rid of this direct signal so that we can focus only on the photons that carry information about the non-line-of-sight object. Therefore, I will not be showing the actual light source and sensor acting as if photons directly start from and end at the scan point. Now let's focus on the part of transient that encodes information about the non-line-of-sight object. Our first observation is that the transient measurement is discontinuous at a few locations. In this example here, the discontinuity happens at the very start of the transient, which we mark as yellow. What is the geometric meaning of this discontinuity? Well, it simply corresponds to the shortest path between the scan point and the non-line-of-sight object. We can prove that this kind of path that correspond to transient discontinuities are paths that satisfy Fermat's principle. We call these paths Fermat paths. Fermat's principle is a fundamental principle that characterizes how light travels within a scene. It says light travels through stationary paths, meaning that these paths can be locally shortest, locally longest, or saddle point paths. In the case of a convex object, it will be the shortest path, like the one shown here. These so-called Fermat paths are of 2 kinds, paths corresponding to specular reflections or reflections on the object's boundary. For the first kind, specular paths, they will align with the surface normal direction. For the second kind, they will correspond to the object boundary. In fact, for non-line-of-sight objects of a general reflectance, such as a diffuse object, there will also be photons that travel along paths that are not Fermat, such as the gray ones here, and they create the smooth part of the transient. We can further prove that Fermat paths and their lengths has a few important properties. First, Fermat paths are a function of only the geometry of the non-lensed object, and not its reflectance. This means as we change the reflectance of the non-lensed object, the location where the transient is discontinuous remains the same. In the object BRDF video I'm showing here, as we change the reflectance from very specular to purely Lambertian, the transient measurement also changes. But notice that the discontinuities always stay at the same position. Second, from just looking at this one transient and detecting its time discontinuity tau, we have already got the following information. The non-lensed point information and also its normal information corresponding to this sphere, and up to 1 degree of freedom in angle. What's so special about the sphere? Well, this is the sphere with the scan point as its center and half the Fermat path length as its radius. And the information we have for now is that there must be a non-lensed point lying on the sphere, because the back and forth traveling time from the sphere to the scan point satisfies the time discontinuity we detect. And its normal should also align with the normal of the sphere at that point. Another piece of information we have is partial curvature information. In this case, we know this Fermat path is a local minimum path, which means locally there shouldn't be any paths shorter than this Fermat path. In other words, locally the non-lensed surface should be outside the sphere, which indicates that the curvature of the non-lensed surface at that point is larger than the curvature of the sphere. Next, I'm going to show you how we resolve the spherical ambiguity, or equivalently the 1 degree of freedom in angle, so that we can reconstruct a non-lensed point and its normal exactly. To resolve this ambiguity and be able to reconstruct a non-lensed point exactly, we will need more information than just one timestamp from one transient. We need to consider more transient measurements and to look at how the discontinuity changes as we move the scan point. The process is the following. At the current scan point, we measure a transient and detect a discontinuity. As we scan the next point on the wall, we measure another transient and detect a discontinuity within it. And we repeat the process for all the points we scan on the visible wall. By tracking where the discontinuities happen at these scan points, we can express discontinuities as a function of scan points, tau discontinuity as a function of x. Now that we have fit a function, tau discontinuity of x, next I'm going to show you how we conduct differential analysis on this function. More specifically, from first-order analysis, we will be able to resolve the spherical ambiguity and pin down the point and its normal exactly. And from second-order analysis, we will compute the exact curvature. Let's start with first-order analysis, which let us pin down a non-lensed point and its normal exactly. Recall that we already have a spherical constraint saying there is a non-lensed point on the sphere of radius half the Fermat path length around the scan point. Now to find the point exactly, we derive an additional geometric constraint that we call the Fermat flow constraint, which is a rate constraint. I will prove to you in a second that this rate constraint can be computed in the following way. We first compute the derivative of the function tau discontinuity of x at the same scan point and form a 2-vector in the way shown on the right. Basically, this derivative is the x component, and the square root of 1 minus the square of this derivative will be the y component. This 2-vector will point towards the non-lensed point. And now that we have both the spherical constraint and the additional rate constraint, we can reconstruct the non-lensed point and also its normal, simply through a sphere-ray intersection. Now, where does this Fermat flow constraint come from? How did we relate the derivative of tau with respect to x to this rate direction? To understand this, we need to look into the theory and properties of sign distance functions. There is a parallel between the two, the sign distance function and the Fermat flow constraint that we have in here. What is sign distance function, or in short, SDF? An SDF is a function on the entire domain given the surface, or in another term, the zero contour, such that at each point xy in the 2D domain, the function value d of xy is the minimum distance from this point to the given surface, or equivalently, the distance from this point xy to its closest point on the surface, which we denote as s of xy. And this sign distance function satisfies three important properties. First, on the surface, this function equals to 0. This is pretty straightforward. On the surface itself, the distance function equals to 0. That's why the given surface is also called the zero contour. Second, it satisfies the so-called equivalent equation, which says if we compute the spatial gradient of this function anywhere within the 2D domain, it will have norm 1. And this property means if you think of sign distance function as a propagating wavefront, it is propagating at a constant unit speed. Third, another property of this gradient is that not only will it have norm 1, it will also directly point towards the nearest surface point, s of xy. Again, if you think about it, it means this propagating wavefront is propagating along its normal direction. Now, the important thing to notice here is that when we measure these discontinuities, as I explained earlier, we are measuring the distances from each scan point to its closest point on the non-left-side surface. So essentially, what we are measuring is a slice of the SDF, a one-dimensional sampling of this two-dimensional function. Now we want to utilize the important properties that an SDF has, that its gradient has norm 1 and points to its closest point on the surface to conduct the first-order analysis. According to the third property, if we knew the gradient exactly, then it points towards the non-left-side point that we would like to reconstruct. But we don't know the gradient because we are not measuring the sign distance function everywhere. We only have its 1D sampling. That's where the second property, the equivalent property, comes in handy. If we write it out explicitly and compute the first term of the gradient, which equals to the gradient of this 1D function, tau discontinuity of x that we measure, then for the second term, we can directly use the equivalent property to infer it. So even though we only have a one-dimensional slice of the SDF, it is sufficient for computing the gradient of the SDF on the wall. This computed gradient is exactly the Fermat flow constraint that I showed before. This is why there is a parallel between the sign distance function and the Fermat flow constraint. And through this first-order analysis, we have resolved the spherical ambiguity and reconstruct a non-left-side point and its normal exactly. Similarly, we can do second-order analysis on the slice measurement of SDF to estimate the exact curvature of the non-left-side point we reconstruct, the curvature of s of xy. There's the math on the right side, but I won't go into the details. The key thing to note here is that there are some other nice second-order properties of an SDF, and by using these properties in a similar way as the first-order analysis, it allows us to compute the exact curvature of the non-left-side point, given only a slice measurement. Until now, we've only looked at convex objects for simplicity. In fact, it works for all shapes. Remember that Fermat principle says light travels through stationary paths. In the case of a convex object that we've seen, it will have a locally shortest specular path. Now, if the non-left-side object is a concave object, the Fermat path will be a locally longest one, corresponding to the sharp fall on the right in the transient. In this specific case, there is a boundary path in blue, which is another Fermat path. Fermat paths can also be saddle point paths. In 3D, the local shape would be a saddle, meaning it is a local minimum along one direction and a local maximum along the crossing direction. Finally, as the shape becomes more complicated, the corresponding transient will also have more discontinuities, but they will all correspond to some Fermat path in the scene. In this case, they are all specular paths, 2 convex and 1 concave. Now, with the algorithm at hand, next, let's take a look at the reconstruction pipeline. I will also show you the experiments we did to verify the effectiveness of the Fermat path algorithm. Here are the entire scanning and reconstruction pipeline. Just like a LiDAR, we scan the wall point by point. In each transient measurement, we use the first sharp rise at the beginning to reconstruct the visible surface. And then we take the tiny signal behind that corresponds to the non-left-side object, detect discontinuities, and together with the first and second order analysis, we can recover the points, normal, and curvature information of the non-lens-side object. With this scanning pipeline, we first did experiments with a picosecond resolution imaging setup consisting of a single photon avalanche diode, which is a single photon time-of-flight sensor, a pulse laser, and scanning optics, the galvos. In this setup, the scanning area on the visible wall is 80 by 80 centimeter, and there are 64 by 64 scan points within this area. Using our very low power laser, each scan takes about an hour. With other higher power lasers, this can be reduced to a few minutes. This system has a resolution of 4 picoseconds or 1.2 millimeters. We scanned small 3D printed objects for which we have ground truth shapes. Our reconstructions match the ground truth and at an average error of 2 millimeters, which is very close to the sensing resolution limit of the system. Here are some more reconstruction results of tabletop objects. Because our method is purely geometric, it has a few advantages. First of all, the reconstructions are of high resolution. They're comparable to even reconstructions in a line of sight setting, where the objects are directly visible. Second, we can handle arbitrary shapes, both convex and concave. Third, our method can deal with various materials, including glossy objects, translucent, and purely specular objects. One thing to notice here is that purely specular objects are traditionally considered difficult to reconstruct, even when they're directly visible. We also did experiments with an optical coherence tomography system which captures transient measurements of femtosecond scale temporal resolutions. In this experiment, we reconstructed a US cutter which is placed at 1 centimeter away from the visible wall, and we densely scanned a 4 by 4 centimeter area on this wall with about 1 million scanning points. In fact, we did the same experiments in 2 non-lens-side scenarios. We have seen the first looking around the corner setup. Now we call the second setup looking through a diffuser because an optically thick diffuser is blocking the view of the sensor. And in our specific case, we use a piece of paper as a diffuser. In both cases, the light source illuminates a point on the visible surface, wall, or diffuser, and this illuminated point scatters light in all directions towards the non-lens-side object. So these two scenarios are essentially equivalent. Here are the non-lens-side reconstruction results of a US cutter in comparison with the ground truth obtained by a line-of-sight scan. If we look at a cross-section of the reconstructions, we see that our algorithm can accurately reproduce micron-scale details of the coin, even when it's fully occluded. Here's the comparison of our Fermat path method to other active non-lens-side methods. Because our method takes only the time information to estimate the shape of a non-lens-side object, it is purely geometric and surface-based. Surface representation usually has higher resolutions and is BRDF invariant. However, it is less robust to complex scenes and noise. Volumetric methods, on the other hand, discretize the non-lens space into voxels, solve inverse radiometric problems, and therefore has the opposite pros and cons. To summarize, in this talk, I've introduced to you a new imaging scenario where the scene of interest is not directly visible. We call it non-lens-side imaging. In such a setting, if we would like to reconstruct the accurate shape of an object, we need a new type of data called transient measurements, which also provide temporal information. I then talked about how to do non-lens-side reconstruction using these measurements based on the theory of Fermat paths. The takeaway message here is that non-lens-side imaging is an exciting technique that's even beyond the capabilities of human eyes. And what makes this all possible are modern imaging systems, tailored algorithms, and the increasing computational power. Thank you very much for your attention.
Great. Thanks for the really fascinating talk, Shumian. Just a really great new method to actually directly recover the surface from the non-line of sight measurements. So we have a question here in the chat from Hiruka, who says, fascinating work. And are there examples or more examples from real life scenarios where you could use this technique?
Yeah, that's a very great question. So currently, non-line of sight imaging even though the results seem pretty amazing, but they are actually all done in, all experiments are all done in a highly controlled lab setting, with the pulse laser being the only light source. So if we want to move the entire non-live-side imaging system outside to real world, there are a few challenges. The first one is scene complexity. So all of the experiments I showed are all reconstructions of single isolated objects, but you can imagine if I want to reconstruct a cluttered office full of furniture and objects, the light transport within that kind of a scene would be more complicated. There will be a lot of occlusion, interreflection, scattering, and in that case, the transient measurements won't be the smooth, nice transient measurements I have in the slides. It will be very complicated, and detecting discontinuities with that kind of transient measurements would be very challenging. So we're currently exploring the ways to more robustly handle complicated real-world scenes. To address that issue, we're exploring the possibility of combining our non-live-side reconstruction method, the Fermat password, with other such as volumetric non-live-side imaging methods that perhaps have lower resolution, but is more robust in handling complicated scenes. And another challenging thing in a real world setup is the very low signal to noise ratio. So all of the previous experiments, as I said before, was done in a dark room. So, but if you can imagine, if you bring the system outside, the strong ambient sunlight will be the main limiting factor. So in that case, the non-live-side photon will not only be overwhelmed by some direct photons from direct reflections or direct photons, but will also be overwhelmed by very strong ambient sunlight. And in that case, detecting those non-live-side photons would be very challenging in the first place, let alone doing a reconstruction based on them. So we're exploring some perhaps new imaging, non-live-side imaging schemes to increase the light throughput to extract more useful non-live-side signal from outdoor settings. Yeah.
Okay, excellent. And one more question in the chat. The question is if the surface profile of the wall is assumed known, and maybe I can just add, if there are more complex like non-planar geometries, would there be a way to account for that in the Fermat flow framework?
Yeah, theoretically, our method works for all kinds of line of sight walls. So it can be planar and can be non-planar, as long as we first reconstruct the line of sight wall first and then do non-line of sight reconstruction based on that. So like I have in the pipeline slide, we first use the first sharp returning photon like LiDAR does, use that first to reconstruct the visible surface. And then once we have that visible surface, theoretically, we can do non-line of sight reconstruction with that calibrated visible surface.
Great, yeah, makes sense. Okay, so I'd like to thank Shumian again for this wonderful talk. And I think we may have some further questions, but perhaps Shumian, you might be able to answer these offline. Yeah, and so we can proceed to our last speaker, Alyosha. And I'm really actually pleased to introduce Alyosha Efros. He's a professor at the University of California, Berkeley, and has worked on data-driven computer vision, as well as computer graphics and computational photography, and is the recipient of numerous awards, including the ACM Prize in Computing in 2016. And I think many of you know Alyosha and are familiar with his work, and he's really a pillar of the community, and we're very fortunate to have him speak. So I think Alyosha actually just joined. If you'd like to say a few words, we're going to pull up your video and then play the recording, and then we'll have you on for live Q&A. And you're welcome to unmute or show your video and say a few words if you'd like to right now, as we pull up the video.
Hi, folks. Yes, I would, yeah, I'm happy to answer questions. But now that I did the recorded video, we might as well play it because who knows if I'll be on time second time. So let's just do the video, and I'll be back for questions.
Oh, okay, great. Thanks, Alyosha. So without further ado, I'll pull up this video here.
Hello, my name is Alexey Efros, and today I'm going to talk to you about using machine learning to detect image manipulation. So image manipulation is really an old problem. It's as old as photography, really. So the first known image manipulation, the victim was the widow of Abraham Lincoln, whom some photographer claimed he was able to retrieve her husband from the dead, and there is a shadow of him over behind her. But of course, it's just a simple overlapping of two negatives. Lincoln actually was really a big the first kind of a popular popular subject for manipulation. For example, here is a classic Lincoln portrait that I'm sure some of you have seen in schools if you grew up in America. And actually, this is a total fake. In fact, this was a portrait of John Calhoun, but after the war, he wasn't in high regard. So, and they needed a portrait of Lincoln standing up. So they basically took a sitting Lincoln, took his head, and made this rather famous portrait. Okay. Of course, image manipulation is a beloved tool of dictators. There is a wonderful book called The Commissar Vanishes that I can recommend highly. It is sometimes, not very often, but sometimes it has been used as a political weapon. This is a very famous case of Kerry being presumably photographed with Jane Fonda at an anti-war rally. That was made a big deal. It was reported in the New York Times, but actually it was completely false. It was a composite of two completely separate photographs. Okay. But also image manipulation can be used as a biting satire. I highly recommend you check out on Twitter Trump replaced by Penguin series. It's quite lovely. Or a creative video, right? The whole movie Forrest Gump is one big fake. And of course, there are the real deep fakes, something like this. Okay, I think, not sure if you have heard this, but he said, "I never met Forrest Gump." But of course, this is not actually a modern deepfake. This is a SIGGRAPH paper from 1997 by Chris Bregler et al. Called Video Rewrite. So even that is nothing really new. So what is new? What has changed? Why are we suddenly all worried about deepfakes and GANs? Well, really what changed is the ease with which we can produce these things. It's really the creation of and modification of visual content has been very democratized. And so there is a whole field called photo or visual forensics that tries to figure out, authenticize a given photograph or a given video to try to combat this issue. I'm not going to give you a whole overview. If you're interested, Hani Farid, who is a foremost authority on the subject, has a whole book on this from MIT Press called Photo Forensics. I highly recommend it. What I'm going to talk to you today is three of projects that in my lab that try to do a little bit maybe more specific versions of this image forensics problem. Okay, first is we wanted to see if we can detect images that had been generated by convolutional neural networks. Okay, and this is a paper that's going to be presented in this conference, CVPR 2020. So, what we're really interested in is to create something that could be a universal detector. So basically, you give it any image generated by a CNN, and it should say, yep, this is not real. Okay. So what we did is we got a whole bunch of different methods, some GAN methods, some low-level kind of methods, low-level vision. We have a deep fake. We have some perceptual loss methods. So a whole bunch of different ones. And then we basically, what we want to do is we want to, well, what we originally want to do is to say, okay, let's train on all of these and then see if we can predict some newfangled method that's going to, come out in next year's CVPR and should be able to detect that, right? That's that would tell us that we're really doing some generalization. Now, of course, that it would take a year to have to see if our paper worked or not. So instead, what we did is we picked just one algorithm, progressive GAN. We trained our method only on the outputs of that algorithm, and then we tested it on all the remaining ones to see if whatever it has learned about this particular CNN generated method would translate into the others. And this is not an easy problem because there are many differences across all these methods, not only the architecture and an objective, but also even the data that it was trained on. The data sets that these methods use are actually quite different. Some are indoors, some are outdoors, etc. But the hope is that there will be some underlying commonalities that will enable generalization. Okay, and why did we feel like there is some chance that this would work? Well, if we look at the average Fourier magnitude of the real images across the different data sets and across the different methods and data sets and the fake ones, you can see that on average those magnitudes are quite different. They're of course different across the different data sets, across the different algorithms, but they're quite different between real and fake. Okay, so remember this is averages, so this might not mean that we could tell apart any given one, but at least we feel like there is definitely signal in here. They are not the same. The top row and the bottom row not the same. So there is hope. Okay. So what did we do? The simplest, stupidest thing possible. Okay. So we took our progressive GAN. So you take a random number and you generate an image, and then do it a bunch of times, and so you have these images generated by your progressive GAN, and then we also took a whole bunch of images that were real images that the progressive GAN was trained on. Okay, and then we made a classifier, a binary classifier, that would look at either the generated images or the real images, and it was basically trained to say real or fake. Binary classifier, very simple, real or fake. Okay, and that's basically it. Now, this actually looks like a GAN if you squint, right? There is a generator, there is a discriminator. The only difference is that normally the generator and discriminator, they're trained jointly and they're kind of competing adversarially with each other. Here, the generator is locked. It's already a pre-trained generator. The method is already done. So we are training the discriminator to completion on a fixed generator. So the discriminator can actually do a much better job because it's not being fought against. Okay, and also we could make it a much bigger, much nicer generator because we didn't have to deal with this whole adversarial stuff. Okay, so now we lock our discriminator, our detector, and now we give it different images, also synthetic images and real images, but from other methods that we use. Okay, and then we want to see how well does this detector do at detecting real versus fake. Okay, and so very simple idea. And so here is our results. So for the ProGAN images on a new held out test set of the ProGAN images, it does perfect. It does 100%. Here the chance is 50%. It does 100%. It is perfect, which is maybe not super surprising. It's still nice that it does that, right? It could have completely failed, but it's basically it was able to generalize to other data produced by the same algorithm. Great. But of course, what we really care about is how does it do on the other methods. And here you can see that it's actually doing not so bad. It's definitely, all of them are above chance. Some are better than others, but you know, they're doing something. But some of them are not maybe doing that great. So can we make them do a little bit better? Turns out that yes, we can. What we can do is we can add what are called augmentations, data augmentations at training time. So as we train the original algorithm on our program data, we can add some manipulations to the training procedure. For example, we can take our images and we can blur them, or we can JPEG them in different ways and put them as positives and as negatives, these manipulations. So this kind of makes the detector work harder and try to be robust to these kind of blurrings and JPEG artifacts. And you can see that just doing that increased our performance almost across the board. So even the methods like Gaussian that we weren't doing well on at all, we're basically almost at the perfect now. Okay. Now notice that there is a couple that actually the data augmentations that made it worse. So deepfakes and super resolution both didn't do very well. Super resolution, it makes sense because super resolution is all about the high frequency information. And so if you apply some blurs, it will lose all the high frequencies. And deepfakes, there is a lot of stuff happening in deepfakes. It's not just the CNN part. There is also, you know, aligning and mapping and matching and other things like this, which are also kind of high resolution. So it also kind of makes sense that it dropped. Okay. Now, something that was kind of cool and unexpected was that we, well, yeah. So first is that there was quite good generalization. I guess what was cool and unexpected was that if we looked at what happens if we apply a particular perturbations to an image at test time, not at training time, but at test time. Okay, so let's say we take an image and we blur it. Okay, and so here we blur it, and this is the sigma. So sometimes blur quite substantial. And so what we see here that the vanilla algorithm with no augmentations, the more you blur the input image at test time, the worse it performs, and then eventually it basically becomes chance. Okay, that's maybe not that surprising. What's surprising is that the performance of the algorithm stays at 100% when you apply blurs if it was trained on blurry images. Okay, so the reason this is kind of unexpected is that what this means is that the fingerprint, the signature that tells us that an image is fake, that it was produced by a CNN, is not just high frequency information. It's not just high frequency noise, that it's actually sitting in all frequencies, including very low frequency, because look at this, we're blurring it with like a sigma of 4, and it's still able to tell apart the real images from these generated images. So that means that whatever that fingerprint that the CNN is putting into the image, it's not just at the highest frequencies, it's actually all across frequencies, which is quite interesting. And we weren't really able to figure out like where it's sitting. We weren't able to see it, but it's there. And so hopefully some of you may be able to figure this out. What is it actually that the CNNs are screwing up? Yeah, so lower frequency bands. Okay, now we also tried some other generalizations. So for example, there is a thing online called whichfacesreal.com. It gives you two faces, and you're asked you to guess which one is real. Now I'm pretty sure that this one is real. So it's out of the distribution data set. The data set is generated by StyleGAN, JPEG images, unknown processing, and our performance is still pretty good. It's 93% on a completely new thing. Now humans are, I think, also pretty good. I think humans are maybe about 80-85%, but it seems like we're doing better than humans. So in conclusion, this suggests that CNN-generated images seem to have quite a lot in common, and these artifacts are detectable by a very, very simple procedure, very simple classifier. Indeed, we actually, after they submitted the paper, StyleGAN2 came out, and we just ran it out of the box, and it was 99% correct. Now we did use some tools, some tricks. So we did, add lots of augmentations, and the training we trained for a very long time, several weeks. It's quite important. But other than that, it was pretty standard. Now, of course, this situation might not persist. Today's GANs actually never converge, right? So the discriminator always wins, whereas in a real convergence scenario, the discriminator should be losing at the end. So if the GANs ever actually figure out how to converge, we might be in trouble, because in that case, the GANs might produce distributions of images that are indistinguishable from real ones, and then I don't think there's anything we can do. But this is definitely, we are far from that. Indeed, for now, I don't think GANs are really our biggest problem, because most of the GANs, even humans can tell that they're fake. So I think our biggest problem actually are not the deep fakes, but the shallow fakes, something like Photoshop. So what do I mean by that? So let's look at this image. Okay, so this is an image of Lavrov, Russian foreign minister, hanging out with the North Korean dictator, and he's not looking very, very happy. And so when they showed this, when they gave this information on Putin's favorite news program that evening, look at this. He's much, much happier, right? So what happened? Well, Photoshop. Okay, we don't know, but most likely Photoshop is what happened. Good old Photoshop has some amazingly powerful functionality, especially for human faces. They have a tool called Face-Aware Liquify, where you can basically just move a little bit, just a little simple warping, and you can just warp things around and able to do quite a lot of things. Okay. And so in this paper, again, with our collaborator from Adobe, just like the paper before, we decided to try to detect these kind of shallow manipulations. And what we decided to do is to just use Photoshop as a weapon against Photoshop. So we took Photoshop and we made it create a whole bunch of fake images by just randomly playing around with the parameters of this Face-Aware Liquify tool. And so here are some of the examples of this. And you can see that they're actually very, very good. They're very subtle and very good. In fact, humans are, in this case, basically a chance detecting which one is real and which ones are not. But our detector was able to, again, do a very good job on this fake, real versus fake detection. And it's really just, just take a CNN detector and just train it on the real images versus the fake images that we just generated. That's it. Very, very simple. So there's a bunch of numbers. I'm not going to bore you there. And of course, also data augmentation was a big help. But what we could also do, just instead of just this binary fake or real detector, we could actually try to see where things were changed. And to do that, what we did is we actually computed an optical flow between the real image and a modified version of that image. And so here is the optical flow. And then we trained a different network to predict, given a manipulated image, predict the optical flow field that would bring this image to become the natural one. Okay. And so here is some examples. So this is the input image. This is the ground truth optical flow, and this is our predicted ones. And you can see that we're doing pretty well. But more than that, what we can do now is we can take this predicted flow and we can do kind of like an undo button. So we can, here is our input image. This is a manipulated image. And we press undo. We predict the optical flow. We reverse this flow, and we basically try to unwarp the image. And here is the unwarped image. This is our little undo button, okay? So this is the input, and this is the undo. And this is the original image. So if I flip between predicted, undo, and original, you can see it's not exactly the same, but it's quite close. Here's another example. Input image. This is our undo, and this is the original image. So again, undo, original. Okay? Okay. Finally, let me spend 5 minutes on our oldest work in this area, where we wanted to detect splice detection. Okay, so splicing is when you take two images and then you put them into one image, something like this. Okay, so we wanted to detect this kind of splicing events. Okay, so here is an example. This is an image that is a splice. This is where the car can come from, and this is where the rest of the image comes from. And what we want is we want to detect this splice. Okay. Now, we thought we could just use supervised learning, but that's not really possible because we just don't have enough data that is labeled to be splice data. There's just not that many, artists who are actually doing this for a living and giving us the information. So it's a very unbalanced problem. So instead of we decided we're going to treat this as a self-consistency, unsupervised anomaly detection problem. Okay, using self-supervised learning. And our basic idea is we're going to look at pairs of patches in the image. And so here is a couple of patches in the image. And if this is a spliced image, that those patches come from two different images. And the two different images were taken by two different people, taking two different cameras in different conditions, etc. So the hope is that those two patches are going to have a little bit of a fingerprint that's going to be different between them. They're going to be inconsistent in various ways because they came from two different imaging pipelines. Okay? And so if we can learn that, then we're good. So what we can do is we can take these two patches and say, okay, these we hope could be inconsistent, whereas something like these two patches are, they should be consistent. Okay? Now, how do we do this? Well, the simplest thing we can do is we can basically just take a standard Siamese network formulation. We can give a network with two branches, and we can give it a pair of patches from the same image. And then we want to train it to say that these two patches are consistent. So make basically, again, a binary classifier, consistent or not consistent. And then take patches from two different images, and those should be inconsistent. Okay, and then we train this kind of binary classifier, and then we're good to go. Well, unfortunately, this doesn't really work very well because a lot of the times things are going to be too easy. So, for example, let's look at these two patches here: one from the top image, one from the bottom. Now, it's obvious that they're not from the same image, right? Even just looking at the color histogram will tell you that. You don't need to do any fancy schmancy forensics. It's very, very clear. So that's the problem. A lot of our negatives are going to be very easy negatives. So it will be take a very long time for this network to learn anything useful because most of the negative data is going to be just too easy. So instead, what we decided to do is to realize that actually at training time, we not only have the original images, but we have their EXIF tags. So we have the metadata for each image that says a whole bunch of different things: camera make, camera model, focal length, whether they're flash used, etc., about 100 attributes. Okay, and these are recorded with every photo that you take. And we thought, we can use that as our self-supervised training data. Because often a lot of these attributes are not going to be the same. If you take two random images, a lot of those attributes are not going to be the same. So what we're going to do is we're going to try to predict. We're going to again have our Siamese network, but instead of predicting whether two patches come from the same image or two different images, the patches will always come from two different images. But what we're going to be predicting is which of their EXIF tags are the same like for example, camera model in this case is going to be different, whereas white balance is going to be the same. So now for every two patches, we can train for a whole bunch of different prediction heads. You know, we have 100 attributes, we have 100 heads, and we can train whether there is a consistency across all of them. Okay. So basically, we're going to do same or different for all the different EXIF attributes. Now, the first thing to see is, you know, is this even a task that's doable, right? Can we train a classifier like this? Well, for something like, you know, GPS tag or you know, time of day tag, we are basically no better than chance. So this is not possible, which is not surprising. But you could see that for something like the focal plane resolution unit or lens make, it can do pretty well. It's in the high 80s. Actually, the highest one is what's called user comment, which is where a lot of the software like Photoshop put their little comments. So it's able to tell if an image was edited or not. Okay. So now what we can do is we can take a pair of patches now in the same image. We can run them from our dataset, and then we can see if those two patches are consistent across all of those EXIF tags. And if they're not consistent, then there is some good chance that perhaps, now just two patches is maybe, you know, too noisy. So what we're going to do is we're going to have a fake image, and then we're going to do a whole bunch of pairs of patches. Boom, 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 boom. Then we're going to have an affinity matrix, basically seeing which pairs of patches are consistent with each other. And if this is a fake image, then we're going to see, if we do something like mean shift or on normalized cuts, we're going to see that there's a part of this affinity matrix that's very different from the rest. And that can tell us that there's something is not right, something is not consistent. Okay, so here I'll show you some examples. This is the input image, and this is the Groundtruth manipulation, and this is the detection of our method. Here's another one. Guess what's being manipulated? You'll never guess. It's that dude in the background. Here's another one. This is my favorite one. So the guy at the top has been manipulated, but actually also the shadow has been manipulated. But whoever did the Groundtruth didn't notice that, but our algorithm did. So here's another example. And this is actually an example from my old SIGGRAPH paper, and it was able to detect automatic manipulation. And for real images, thankfully, it does not fire. The one at the top, for example, if you don't know, this is Barack Obama's long form birth certificate that our software says is totally legit. Now, of course, it doesn't always work. So in the top image, the oversaturated sky is giving it some trouble. And if you're actually just moving things around with the same image, then it's the same imaging pipeline. So our algorithm says, yeah, that's fine. Although, you know, it's of course not. Okay. So to conclude, generating and editing visual content is nothing new. Computer graphics has been added for 60+ years. And, you know, you cannot imagine, you know, action movies without computer graphics right now. What's new is that the tools are more automated. The visual creation and editing is democratized. And so it is worthwhile trying to think about ways to try to detect this. And deep methods are definitely something to worry about, you know, in the future. But for now, probably Photoshop is our bigger problem. So that's what we're trying to do right now. Okay, thank you very much. It was lovely to present to you.
Thanks so much, Alyosha, for that talk and taking the time. Okay, so I see that there have been some questions asked in the chat, and you've actually answered some of them already, but we have a new one here from Joel, who says, thanks for the fascinating talk. And would you be able to comment on the possibility of training again, specifically to fool these kinds of tests via penalty terms? So kind of a arms race of detectors and GANs.
Right. So, I mean, there there is definitely, you don't even need a GAN to fool these things. There, you can fool them with all these adversarial attacks. And in fact, we put our paper online in I think like February or March, and then in May there is already a paper that says, oh, haha, we fooled you. I think it's by Hani Farid and his collaborator. I'm not so worried about this, I think, because it's one way to do this in principle, but like in practice it's much harder. And also, if they have access to our stuff and they can break our code, our thing, we can also having access to their stuff. It's very likely that we will be able to just use their technique, whatever technique, as extra augmentation and probably be robust to that. I think the more interesting story is what will happen if GANs actually work, if they actually converge. Because I think the dirty secret is that no GAN today has ever converged, right? Convergence of a GAN is when the discriminator is basically a chance, that the generator is able to fool the discriminator, and the discriminator is basically a chance performance. That never actually happens, right? At even the fanciest GANs, the discriminator is still able to tell the reals from fakes. So until that happens, I think it shouldn't be that hard to tell the two apart. Now, when that happens, then suddenly I think it will be impossible to tell them apart, because that's kind of the thing that the GANs are trained for. So I think the reason we are succeeding is because the GANs are not converging. Now, the question is whether they will ever be able to converge. Nash equilibria are very hard to get, and I think there's several theorists who think that it's just not ever going to happen. And if it does, then I think we're really in trouble, because then they will be able to produce distributions that are indistinguishable from real data.
That's very interesting. Okay, we have a few more questions coming in. This one from Ulugbek, who says, and I think you mentioned a statistic on this, but do modern deep learning-based image forensic methods outperform human experts? So if you have someone who's like an expert who has looked at a lot of these generated images, are they still better than the deep learning models?
I think we don't really have any statistics on this, and I think that I think there's really only two experts, Hani Farid and Hauli, and we can ask them and see, okay, what do you think? I don't think we have any real neighbors. What we know is that it's still pretty easy, even if you're not an expert. So this website I mentioned, the real or fake face, I get about like 85%, and I'm legally blind, and like a lot of people get 100% on this. Okay, compare this to the shallow fake I showed, where humans were basically a chance. And I think even if you're like a super expert, you will not be that much better than chance. I think that's where the computer methods are definitely shining. For deep fakes, I think they're just not good enough yet to even really have any major contest. So yeah, I think, but they're getting better every month. So we'll see.
I actually had a question on with the Photoshop manipulations. I was actually surprised that the model could figure out what was going on, because like, what is the signal there? Is it because it's trained on lots of faces, it understands the layout of the face, and can therefore find asymmetries or things? Or why would that even work?
Good question. So in the paper, we actually have some ablations to try to figure it out. Part of it is low level. So what we did is we actually tried it for a non-face. Actually, we tried it for like random images. So we warped random images, and we could still get some signal. So just the low-level warping operation, the bilinear interpolation and probably some anti-aliasing, maybe some blurring, those things, Photoshop does them in a particular way, and that way leaves some sort of a trace, some fingerprint. So part of it is low-level stuff, but what we definitely didn't get as well as if we did it on faces. And so part of it does seem to be that it might be learning something about, how a natural faces, a natural, Duchenne smile versus a face smile. It's probably getting some of that as well. So we know that it is getting signal from both, but it's not clear. It's maybe 50-50 at this point of low level versus high level.
Okay, got it. Thank you. Okay, a few more questions. We can take a couple more here. Can you comment, this question from Usman, can you comment about conditional GANs versus unconditional GANs? Is there any reason to think that an image generated by one could be more realistic than the other one generated by the other?
My opinion is that the conditional GANs they look way better to me. It's a much simpler problem. You're starting with something that's already real, so it's all you need to do is not screw up. So I think that unconditional GANs look better to me than conditional GANs look better to me than unconditional. We didn't see any difference in performance on our method. And in fact, like one hope I had was that the performance on this task, or real versus fake, might be able to tell us, which methods look better than others. And we actually have a figure in the paper where we kind of sorted the resulting images by their score on our real versus fake test, and there is no correlation. Unfortunately, it's not looking at anything that humans perceive as being, it's not paying attention to the stuff that we humans pay attention to. It's something completely different.
Right. So this also goes along with Katie's question. Presumably, these different networks have different artifacts that they're introducing, maybe even at different frequency bands. Is there a way that you can use network interpretation or interpretability techniques to figure out what these artifacts are, or maybe find them?
I was kind of hoping you guys would help us. I mean, this network interpretability thing, it's not really doing so well. I mean, we tried to figure it out. We couldn't. We tried a few methods and we couldn't really make any heads or tails out of this. As I said, like, the most surprising thing to us was that the artifacts were at all scales, that they were not just at the high frequencies. That to me is like super surprising and kind of weird and also really cool. But I'm kind of hoping that, somebody who is like trained in signal processing and, good double E background, that's what we need to really figure out what's going on. Yeah, we tried a few things and we have no clue, but I'm kind of hoping somebody is going to figure this out, because it is really, one possibility is that it might have something to do with just the nature of convolution. So that the fact that everything is produced by convolution somehow, encodes some, there's some subspace that it's able to generate and is not able to get out of that subspace. I don't know. We tried, Richard Zhang is on the paper, so we tried, making sure that the anti-aliasing was done right and everything. We couldn't really figure what was going on, but I think it's a great problem.
Yeah, this is it's fascinating that you can blur the image so much and still be able to tell.
So there's something sitting there. So there's something, and what it is, it would be wonderful to figure out.
Okay. Well, we have a couple more questions, but unfortunately, in the interest of time, I think we'll have to cut it there, but really appreciate you taking the time and sending the recording as well on short notice. So thanks again for being with us, Alyosha.
Well, thank you very much. I'm very happy. Thank you.
Thanks. All right, so with that, the workshop is going to conclude. We just have a few more notes and announcements that I'll bring up in just a second here.
I just want to thank you all so much for joining CVPR's 2020's Computational Cameras and Displays workshop. It was an amazing day of truly fantastic talks. And I also can't wait to learn more about the spotlights that we heard about earlier in the day. But it's really all of you who have participated. I was just amazed to see how many people we had signed in throughout the day. Asking questions, taking the group photo, participation like this really made it possible for us to, although we're separated, kind of brings us closer together as a community. So thank you again. I want to pass it off to David.
Thanks, Katie. So I'd like to also thank again one more time our sponsors and of course everyone who participated in the workshop and specifically our sponsors Adobe, Algolux, and Google for helping to make this possible and their generous support. And with that, hopefully next year we'll be able to meet again in person, and we hope to see you at CVPR next year in Nashville, Tennessee. Thanks, everyone.
Thank you.